like, I guess a year and a half ago. We loved doing the ZK Summit 9 here, and so we decided to host it here once again. I want to quickly introduce myself. My name's Anna. I'm the host of a show called the Zero Knowledge Podcast. I'm a co-creator of a project called ZK Hack, and I'm a co-founder of a company called ZKV. I'm just laying these out because these are 3 different companies. A lot of people mix them up, but they are distinct teams, distinct orgs, distinct business models. A little brief on what they are. ZK Podcast is a podcast. Has anyone listened to the ZK Podcast, maybe? Yeah. ZK Hack is a learning hub. Is anyone in the ZK Hack Discord? We have some people. ZK Hack also produces ZK Mesh. It does a bunch of hackathons. And then ZKV is a validator running on over 12 networks. We actually have, like ZKV also does like industry reports. Outside, you can actually pick up the State of ZK report, which is a quarterly report that ZKV produces every quarter. So throughout this presentation, I'll be mentioning some of the initiatives of these projects, so that's why I wanted to introduce them. Okay, so ZK Summit, specifically, is produced by the Zero Knowledge Podcast. And we currently have 342 episodes and counting, which is kind of cool. This is the team behind the podcast. If you're not familiar, it's Rachel, Henrik, myself, Tanya, and Jonas. And we have our wonderful co-hosts, Kobe, Tarun, Guillermo, and Nico. And Nico will actually be hosting this stage with Tanya today. I do this every time. I basically, we calculate kind of like what are the top listened to episodes. And almost every time I do this, there's a new episode or 2 who join the list. So this time it was Return to MPC with Nigel Smart. And very new, the Groth 16 IVC informal verification episode with Jens Groth made the list for this edition. We have a YouTube channel. This is where you can find the podcast, although the podcast has no video. It's just like a static screen. But all videos for this event, as well as some other videos related to the ecosystem, can be found there. We also have a jobs board. Actually, for this event, we have a lot of our sponsors who've added new jobs to the jobs board, so I really recommend checking it out if you're looking for your next opportunity. Also, if you're a team looking for good talent, we've heard like stories of people hiring amazing people. We're actually trying to collect testimonials. So also, if you're a team who's hired through the jobs board, come find me later because we'd love to talk to you. This is the website. You can find all those links from the website. This is our Twitter we're going to be using. A quick note about the podcast, and I made the announcement earlier this week. I'm taking a short break from the show starting October 16th. I've been running a weekly show for 7 years, or almost 7 years, which is kind of crazy. And I want to take a pause, probably not full pause, because I have a few ideas for a few select shows I want to release in the next few months, but we are going to take a little break. The reason I mention this is that we have another series I kind of want to promote. ZK Hack has recently dropped ZK Whiteboard Sessions Season 2. And while I'm taking a break from the show, we're going to be releasing ZK Whiteboard Sessions every 2 weeks for the next 3 months. Has anyone seen the ZK Whiteboard Sessions Season 1? Great. Has anyone seen the first module of Season 2? Oh, wow, just a few people. Okay, so go check it out. The hosts for this edition is Nico and Tracy. And the first module is called What is Zero Knowledge Like Actually? We thought that it would be good to actually define it properly in the series. So do go check that out. All right, now a little bit about the event. So ZK Summit, we've been doing this since March 2018. The event has been hosted in Berlin, San Francisco. It's been online. It's been in Amsterdam, Lisbon, London, Athens, and now Lisbon again. And this is a spot where we get to hear about cutting-edge tech. And honestly, there's been like presentations on these stages of systems that maybe we didn't know it at the time, but they went on to become standards, to become really, really important. So it's great to be here with all of you to hear, about the latest cutting-edge research. Here's a few picks from previous editions. We have ZK 6, 8, 4, 3, 11, 11, 10, 2, 7, 8, and 9 was actually here. So this is from this stage. Yeah, and any more info you need, you can find over at zksummit.com. You are currently at the Lisbon Congress Center. One note, if you're staying around here, I very much recommend visiting the Lisbon city center. It's, to me, one of the most beautiful cities in the world. And I think, even though this area has some cool stuff, it has a beautiful view of the bridge, really check out the center. But yeah, we're very excited to be back here. For the stages, we have 4 tracks today. We have a main stage, side stage, breakout, and workshop. We also have the co-working upstairs and a sponsor area that you've already walked through. I think this map actually exists out in the hall, but just to go over it, we're currently in the main stage. Maybe just to note, the workshop room is a little bit harder to find. If you go to the info desk, there's a little hallway behind it. That's how you get to the workshop room. And it's only got 20 seats, so if you really want to see a workshop, be sure to get there early. I think in the past we let people kind of pack in, but this time we're going to cap it. So if there's something you really want to catch, make sure you get there early. Upstairs, we have the side stage, the breakout room, as well as a co-working area. And this is the program. I'm not sure if we had a chance to correct it, actually, but we had 2 talks cancel, so I just want to highlight those. The one at 10, we've now moved to 11, so that talk, Vanish Ray, she's still speaking, but we've moved that up. And in the afternoon, we had unfortunately one speaker not be able to attend at 4 o'clock, so that has also been removed. Oh, actually, so then my bad. There is a talk. I should not have blanked it out. Okay, we have a recording of that talk, so actually, forget what I just said, only one talk is missing. We have a wonderful program. It's been really fun putting this together. I think we had, I didn't actually count the final tally, but it's something like 110 to 120 applications to speak. We only had 35 spots. It's been really hard to choose, but I'm very, very excited with how this turned out. Cool. Every stage also has some hosts, so Nico and Tanya are hosts of this stage. They're going to be moderating it. The side stage has Henrik and Gaylord. The breakout has Cohen and Quentin. If you're a speaker, be sure to contact your stage host just so that they know who you are, and especially before your talk, just let them know that you're in the room. As mentioned, all videos for this will be on the Zero Knowledge Podcast YouTube channel, and I actually maxed out, I think, the number of videos I can put on a playlist for ZK Summit. So now there's 2 ZK Summit playlists. We have ZK Summit 1 through 10, and then it will be ZK Summit 11, 12 onwards. This is the password, and I hope everyone's already gotten this. If not, I'll give you a second to take a photo. I think there's signs around with QR codes, so you should be able to log in quite easily. And now I want to invite Andrew to the stage to share a little bit about the NFC cards that you'll find in your lanyard pouch.
Thanks, Anna. Yeah, so all of you should have an NFC card in your badge. It's in your pouch. And the way you can actually get started with this is you tap your own badge to your own phone, and that allows you to register for it. And then once you've done that, you can go walk around and tap other people and collect their contact information. One of the coolest things you can do in the app is we have a bunch of different topics in cryptography, ranging from MPC to ZK-TLS to TEs, and you can rate whether or not you think each one of these is underrated, overrated, or fairly rated. And when you meet someone, you can figure out what hot takes you have in common, which is pretty sick. And it's all private, so unless you both agree, then nothing gets shared. So thanks so much, Anna.
So we did this actually at ZK11 as well. We had the cards, but at the time, basically what will happen, every time you meet someone, you can actually make that connection, and you can collect those connections. We have a leaderboard for the number of connections you've made, and last time I got really competitive and was like, I'm gonna be top of the leaderboard, but there wasn't really anything to win with the leaderboard. So this time around, ZKV has joined efforts with Cursive to basically offer some prizes. So if you make the most connections and rank first on the leaderboard, you're gonna get 250 USDC. If you rank second, you get 100, and third, you'll get 50. Thank you so much to the Cursive team, though, for building it. It's really been an amazing effort, so thank you. Maybe we'll give a little round. I want to say thanks to them. Yeah, so have fun with them, and you can win prizes. I'm going to set the cutoff time to be 6:30. So that's the moment where we're going to snapshot it. So it won't go all week. It's really just for the day. And if you are on the leaderboard and you see yourself ranking, go talk to the ZKV team. There's a booth, just so they know who you are, so that we can get in touch with you for those prizes easy. All right. So, yes, I want to say the ZK Summit this is something I don't know if everyone realizes, but like, unlike some of the other events in the space, like the ZK Summit is not backed by a foundation or a token or a single network. This event is built from the ground up every single time. We actually could never do it without our amazing sponsors joining us. And for this edition, we have two return sponsors in the form of Risk Zero and ZKV, and 2 new sponsors, Irreducible and Veradice. I want to say thank you to all of our gold sponsors for joining us. We really couldn't do it without you. Let's give them a round. We also have our silver sponsors for this edition, also return sponsors Anoma, Fenbushi, and Neil Foundation. Thank you to the silver sponsors. And our community sponsors for this edition, Argument, Alio, Brevis, Fluent, Snarkify, Lagrange, and ZK Verify. Thank you to everybody for joining again. We really do try to keep like the ticket prices. I don't know if any of you got the early bird tickets or student discounts. We try to make them relatively affordable, and this is why we really rely on our sponsors. If you're interested in sponsoring future events, please get in touch. Here's the team that brings you ZK Summit 12. We have Agni on Ops, standing right there. Agni, thank you again. Let's give Agni a hand. She's like the main. We had Natalia and Hania supporting on Ops as well. On the programming committee, we had myself, Nico, Philip, and Kobe. And then helping on AV, we have Henrik, who's also the editor of the show and will be editing the videos after. So thanks to everyone who put this together. So here we have our hashtags and our Twitter account. I think I'm at the question point. So if you applied for an early bird ticket, you would have seen this question. So every time we do a summit, we always ask a question. And we always get great answers from the crowd. Weird answers, like brilliant answers, strange. Yeah, anyway, we get a lot of answers, and we always select a few to share with you. So this time around, the question was, how would you explain random oracles to a friend? It is a pseudo-random hash-based black box number generator. I would first explain hash functions and then explain random oracles as the ideal version of a hash function. Hash functions for nerds. How would you explain random oracles to a friend? Theoretically useful, inherently impractical. Imagine a magical box that can answer any question you ask it. You write down your question, put it in the box, and out pops an answer that seems completely random, but is actually determined by your question. This box is kind of like a random oracle. Ask me anything you want, and I'll respond whatever I want. I lost all my friends after I tried to explain them what nullifiers do. So great throwback to ZK11 on that one. A random oracle is what every hash function wants to be when it grows up. Oh. It involves a black box and a gnome. We got a lot of these, actually. I couldn't, and someone just wrote no. Okay. Google's random oracles. How would you explain random oracles to a friend? I don't know, I'm the friend, to be honest. So whoever wrote that, there are a lot of people in this room who can help you out with this. So I hope you'll ask around. And actually, this could be a good icebreaker for the card swaps as you're making friends with those NFC cards. So I am doing something I've never actually done before. Usually at this point in the summit, we have the platinum sponsor come up and share basically a 5 to 10 minute talk. We don't have a platinum sponsor this time around, so instead I wanted to use this time to share a little bit of like history. So I want to do a very, very, very brief history of ZK research and history of ZK applications. One of the reasons for this is if anyone is newer to this space, the words we use, the terms for research papers and proving systems and applications, you may not know where to place them. And so my hope with this is to just give you a bit of a framework to understand where these words come from. So we're going to start on the ZK research front. And believe me, this is going to be very brief. So we're going back to 1982. ZKPs are invented by Goldwasser, Macaulay, and Rakoff. In 1985, they first appear in a publication. Now I'm going to fast forward 30 years, almost 30 years, to 2012. So in 2012, the term ZK snarks is defined for the first time as succinct, non-interactive arguments of knowledge. But as I learned yesterday in a conversation with Jens and Ariel, snarks are older than 2012. There are two papers that I didn't include, one in the 90s and one in 2010, that actually first described the concept for snarks. But here in 2012 is when they're first defined as snarks. 2013, we have the Zero Coin paper, which merges blockchains and the snark concept for the first time. It's followed the year later by actually a lot of the same authors, but adding more authors to create the Zero Cash paper. The Zero Cash paper goes on to influence the founding of Zcash and Zcoin. In 2016, we have Groth 16, which is published. You will hear throughout the day the term Groth 16 mentioned often. This is what it is. It's like the paper that is foundational. It's become a form of a standard. As I understand it, there is a standardization process happening around Groth 16. I think at this point it's the most implemented paper in our ecosystem. And I'm very excited that after my talk, I actually have the author of this paper, Jens Groth, coming on stage to present. Okay, following on, 2017, we have the Fry paper. Fry, this is when it comes out, but you see it being very influential also in the snark world further along. 2018, Starks and Bulletproofs. I'm going to take a little pause because I want to interject the history of this event at this moment. In 2017, there were 0 ZK events. And then in 2018, there were 4. So I think of that year as sort of the start of the ecosystem part of the story. I don't know if, I just wanted to list those 4 because it was kind of exciting. In March 2018, we had the first ZK Summit. In May of that year, we had the first ZK Proofs event. In July, we had ZCon 0, and in September, we did our second ZK Summit. You might wonder why we're at ZK Summit 12. We actually have not been running it for 12 years. We've been doing 2 a year, and then we skipped 1 year. So anyway, just a little bit of backstory. Okay, back to the research. 2019 was considered sort of, I think the end of 2019 especially, there was this boom in research. We had Snarktember and Snarktober, where just week after week we were getting breakthrough research coming out. Sonics introduces universal trusted setups, followed by Plonk, which, again, a standard. You'll see this throughout also some of the naming of future proving systems, but a lot of Plonk was incredibly influential. You have Aurora, Redshift, Spartan, Marlin, all that year. In 2020, we have Fractal, and then Halo and Halo 2. Halo 2, again, being implemented quite often in many different ways, lots of teams who worked on it. We have Plookup, which was I think it was the start of the lookup argument train of research. We had Quarks, and we had Plonky 1. In 2021, we have Nova, which introduces IVC, and Folding, which we're going to hear actually right after this, 2 talks focused on that. We have Breakdown, Snarkpack, Faflonk, Splonk, and the variations on the word plonk never end. There was a pause. I feel like there was a moment where people thought, okay, maybe we should put this away. But I know it's back. I know it's not. It's never going to go away. I heard yesterday also from Ariel that Splonk is not technically the name of that paper, but it's been kind of given the name, and it's a good one. 2022, Plonky 2. We have Plonky 2, which, again, has been implemented many times, is a form of a standard. We have Hyperplonk, Supernova, Culk, and CQ, all in the lookup argument, or those 2 are in the lookup argument thread, and then Kimchi. And now I'm at 2023. And I have to say, 2023 and 2024 are hard to say what the real important research will be. Looking back, we can pick out the ones that really stood out and lasted the test of time. Here, we don't know, but I'm going to list the ones that that I would highlight for 2023, 2024 today. So Bochum from the Matter Labs team. We then had 3 works focused on optimizing the IVC concept with Hypernova, Protostar, and Protogalaxy. We have Binius, looking at the small fields, and I know we have the irreducible team here, so behind the Binius work. We have Jolt and Lasso, which utilized SumCheck. And now, this year. And it's very hard to predict which of these will stand the test of time, but here's what I have. Polymath, Stack Proofs, Plonky 3, Circle Starks, Garuda and Pari, Stir, which was presented at ZK 11, and Whir, which is going to be presented today. Both looking at that Fry protocol that was introduced back in 2017 and optimizing on that. So that is the end of my short history of ZK research. If I made a mistake, let me know. If I missed something, let me know. These are definitely, this is the second time I present that timeline, and it's actually changed a little bit since doing that presentation. This is a work in progress. I hope to actually give this talk again sometime in the future. Now, I'm going to share with you the history of ZK applications. And here, I'm not going to go quite as granularly, like year by year, but look more like at an era. So back in 2016, this was the map of ZK. We had payments, private payments. We had 2 projects working on that, Zcash and Zcoin. There may have been other projects working on zero-knowledge research, but I tried to focus on teams that are still around today and share kind of like how they've evolved and where they've gone. So I'm going to fast forward now 4 years to 2020, and I remember thinking in 2020, wow, there are so many use cases now. We have payments, private payments, we have scaling, we have ID, and we have games. So on the payments front, Aztec is founded, and I'm putting Aztec for now in payments. I know they move, but they were private payments at the beginning, as far as I know. L2s are introduced with ZK Sync, and Mina was using recursive ZK to compress a blockchain for the first time, also kind of like using this scaling idea. IDEN 3 had identified the ID use case, and we had our first game in the form of Dark Forest. So just these 5 categories, the L1, the L2, the ID, the games, and payments, I wanted to share what it looks like today in 2024. So here is what our ecosystem looks like today, and this is probably not complete. In payments, we have new players like ZK P2P, Dymo, and Pay. Aztec is still privacy-focused, but I think I've now put in the L2 category. We had a number of new L1s. ZK-focused L1s joined the fray. On the ID front, IDEN 3, which had originally pioneered it, became Polygon ID, and now Privado.id. And obviously, all these other ID systems emerged. A lot of them actually involve like scanning passports and really different ways of thinking about ZK and ID. And there's all these new games, a lot of which I haven't actually explored yet, but as we were doing this research, we learned that ZK is now in a lot of on-chain games. But the map is bigger than this. These are just a few use cases. Here is what the larger map looks like today. So we have all sorts of applications for ZK. We have the hardware, we have the ZKML, coprocessors, verifiable compute, cross-chain, prover networks. And I have a category down here just called miscellaneous tools, because I don't know how to define them yet. And actually, one thing about maps like this, whenever I've seen someone else do a map like this, I've often been like, that's wrong. Or, I wouldn't put that there. That seems like it's in the wrong place. And then now that I've created one of these, I totally understand why this is. At any given moment, any of these teams may be pivoting. There might be new teams emerging. They might rebrand. They might decide to do like 2 things at once. They might disappear. There's all sorts of things that are happening. It's very much like a living map. And for this reason, ZKV, who's one of the sponsors today, I don't know if you guys noticed, but there's this map of ZK out in the lobby, which looks like this. It's been printed, and there's magnets. We want to hear from you where you think these teams belong. So please go interact with that. Move those teams to the spot you think they belong. One of the challenges, though, I'll just point out, is there are teams that actually exist in like 3 of the quadrants. You could have a coprocessor prover network ZKVM. So what do you do? And I think what we're going to ask you to do is try to figure out what are they most, what are they most well known for, where do you think they're like putting most of their energy, and place them in that quadrant. We also left a few empty quadrants because we know that there's new ones coming. As mentioned, I have this like miscellaneous one, but if you know how to define a category for some of those teams in miscellaneous, please let us know and we can add them. Yeah, we're going to be taking I think the team at ZKV is going to be taking photos throughout the day to try to just capture what you guys think, and I hope you have some fun with it. Cool. I think that is, how am I doing on time? Whew, good. Okay, so that's the end of the history of zero-knowledge research and the history of ZK applications. Yeah, as mentioned, these are works in progress, so I really would love to hear from you what you think was good, what you think we should maybe write different for future presentations. I just want to highlight for all of you the side events to this event. If you haven't yet checked it out, on our website, on zksummit.com, there's actually a link to the side events. I'm going to share a little bit about tonight's side event, but tomorrow there's 5 events kind of happening one after another. You do have to sign up for them, so you may want to do that during the day just to make sure you're on the list. I do want to just flag the ZK Hack Meetup, which is the ZK Hack project. That is happening on the 10th, so if you're still in town, it would be great to see you there. And this time around, we have an official after party, which is brought to you by Pei and Celestia. Thank you guys for putting this together. I don't know where the Pei folks are. I don't know if they're here yet. Oh, yeah. Thank you for putting together this after party. I think you need to sign up. As far as I know, there is limited space, so it's best if you sign up, just so that they have you on that list. And this is happening at 8:30 today. So yeah, thank you guys for putting that together. All right, these are the hashtags, and please do tweet at us, let us know that you're here and share what you can. Maybe just a note, though, these events do tend to have people who are somewhat privacy conscious, so try not to take photos of people's faces unless they overtly want you to take photos of them. I know that people on the stage, you can definitely take photos there, or your team, or people you know if they're cool with it, but just maybe be aware that some people might not want to have photos. Yeah, all this info is over on the ZK Summit. Once again, here is the program as it is on your lanyard, just with that small correction. So, on this stage, I'm very excited that after this, we have Jens Groth coming up to do his talk on memory checking in IVC-based ZKVMs. On the side stage, we're going to not open it until 11, so don't go to the side stage yet. On the breakout, we have Arno Cube presenting Sonobi. And on the workshop stage, on this floor, we have Bobbin and Philip from Polygon Maiden. So I'm going to actually, I think I have, let's right at time. I'm going to actually give us all 2 minutes to decide where we want to go, and then we'll kick off with our talk with Jens Groth. Thank you guys so much, and welcome to ZK12.
Check, yeah. Hello, hello. Thank you. Can I please get everyone to get their seats quickly? We're about to get started. Please have a seat. Thank you very much. Great. Thanks for being with us on the main stage. As Anna said, our first talk is by Jens Groth about memory checking in IBC-based ZK-VMs. Could I please get a bit of quiet in the room? Hello? Hello? Thank you very much. Jens, please take it away.
Thank you. Yeah, so I'm going to talk about CK-VMs, and I'll give a bit of introduction to these concepts since there's a lot of teams and projects that are building CK-VMs and working with IBC and so forth. The problem I'm going to talk about is in CK-VMs, if you use incremental verifiable computation, you slice the computation in multiple parts. Those parts may be computed by different provers. And then the question is, how do you check that they have a consistent memory throughout that computation, right? Because there might be a write in one place and a read in a completely different place of that one. And it's a topic I've talked about before, but there's a new twist. We've been exploring this concept of multiset hashing and how efficient one can prove multiset hashing. And it's one of the techniques that one can use to do memory checking. Okay, so it's something that people have worked on before. There's a standard techniques based on Merkle trees, which is not very efficient. But then there are also some efficient techniques. The multiset hashing technique was actually came out in a paper in 2018 by Set et al. Called SPICE. And then there are other techniques, two-pass offline memory checking, which is quite recent. And if you want to know about that one, you can check out my talk on CK proof, which was talking about that topic. And there's also a nice idea by Bunce and Chen in the paper Proofs for Deep Thought, where they're doing a Peterson commitment to the full memory and then just making an update of a delta, the changes of the memory in each step at a low cost. Okay, so I'll start by giving some background to CK-VMs and the problem that we are looking at in memory checking. So let's start without the CK. So a virtual machine is a machine that can take as input a program, an explicit input X, and another input W, and then it outputs some result. And the question we are asking ourselves when we're building CK-VMs is, how do we know that this output Y is actually true? So the idea in a CK-VM is that you would also output a proof that this has been computed correctly. And then there will be a matching verification algorithm that can take as input the program and the input X and the output Y and prove and check whether this is correct or not. And it's important actually here that then the reason I split the input in two parts, right? So the W input is not part of what the verifier sees. And that's part of why you can have succinct proofs that are much shorter than the computation, that you don't actually give that to the verifier, and therefore the verifier doesn't have to read it, and the computation the verifier invests doesn't have to depend on the size of W. So this means that we can have proofs that are succinct, that are really small, really cheap to verify, and cheap in the sense that the verifier has to look at the program and the explicit input and the output and the proof, but not W. Okay. If we peek inside the CK-VM, typical design is that you would have the virtual machine that produces an execution trace of every step that it executes and produces the output. And then you have a prover that looks at that execution trace and then proves that there exists a valid execution trace. So every step in the execution trace corresponds to a correct execution of an instruction. And those execution traces may be big, right? And computing proofs is an expensive operation. So one strategy could be that you would want to slice that up, and you would have multiple provers. You would have many machines that are proving that this execution trace is correct. Okay, so let me dig into a little more, technically speaking, what happens here. So this is incrementable verifiable computation, concept that was proposed in 2008. So think of this function VM as a state transition machine. It's all like takes what is the current state, it produces a batch of cycles, and it outputs so like what is the next state of the machine. And you can sort of do that in a sequence, and there may be some auxiliary inputs as well, right? And at the end you would output Y, okay? And there's sort of like a lot of details into how you actually prepare that, right? So for instance, maybe it's a big program and big input X, right? And you wouldn't want to give everything in one go, so maybe you instead you have some sort of like digest of that. And then you're not actually giving, so like keeping that as state, but you're instead so like inputting that along the way as part of the auxiliary inputs, omega 0, omega 1, and so forth. So you can, for the purposes of this talk, think of the omegas as so like this is the execution trace that we're drip feeding into the CKVM. And then you would have a prover that sort of like proves that the first iteration has been computed correctly. And the next prover would sort of like consume the proof from the first prover, and so like the next slice of the execution trace prove that is correct, and so forth, right? And that way you accumulate these kind of proofs, and you get a proof in the end that everything is correct. So let's look inside now. What is it that this machine does, right? So think of this as we have a virtual machine. It has a CPU, and it has a random access memory. And one way we could think of this, so like the naive approach, and what people were doing in the early days when they were looking into zero-knowledge proofs for execution of programs, is that you have the state is everything that you have in the virtual machine. So it would have like a snapshot of what are the register values of the CPU and so forth. It would have like the memory and so forth, right? And then you execute it, and it outputs the new memory and the new state of the CPU. Now this is super expensive though, right? Because now you actually have to keep track of the full memory in each of these transitions, right? And who knows how many cycles, maybe you're executing a few cycles, and then it's really costly, proportionally speaking, to keep track of the full memory, right? And you have to place constraints when you're proving that this is a correct transition that constrains all of the memory, right? And a lot of the memory cells will just be unchanged, but you have to say this one is equal to what it was before, this one is equal to what it was before, and so forth. So the natural idea now is, okay, let's try to externalize the memory. So the state now will just be the state of the CPU, what are the register values and things like that, and where is the program counter at. But now we give the memory accesses as external input. So it would say, look, I was writing this value to address 3. I was reading this value from address 17, and so forth. Okay, and this reduces the cost for the prover, right? Because now we just have to keep so like the relatively small state of the CPU, so like what are the registers values and things, where's the program counter at, okay? but everything else has been externalized, okay? So you only pay for what you use, right? So you still have to prove something about the memory accesses you do make, but you don't have to prove something about the rest of the memory. Okay, so let's be naive and go with that straight away, right? What happens? Okay, so now the initial state is just the CPU state, and that's what we are progressing. And now we've externalized the memory accesses, so the memory would be, so memory 0 would be a batch of memory accesses, some reads and some writes. Memory 1 would be some accesses again to the memory, and so forth. And we're basically giving that as advice to the CPU. Okay, and now we can run the prover, and we can prove that all of these transitions are correct. Now there's an obvious problem here, right? Which is that if you're cheating prover and you're running this system, right? You get sort of like to choose what is the external inputs you would feed to each of these things that the provers are proving. So you can feed them an inconsistent memory pattern, right? So you could have, for instance, a memory where you're saying to the CPU, yeah, you are writing to this address, this value here. And then a few steps later, you can say, oh yeah, and you're reading from this address, and by the way, it's this value here, which is a completely different value. Right? And you will get out the wrong output from the computation. But none of the provers will know that something is wrong because their local view, everything looks great, right? I mean, you have some state of the CPU, you have some memory accesses that you're getting from the external, and you're doing the right transition, right? So the proofs will look great. And the problem is just that you're proving things that about the local transitions, but you're not proving that globally speaking, the memory is consistent. So that's a problem of memory checking, and people have come up with several different techniques to address that. So the high level of these ideas is we want to insert some memory protection for the CPU, right? So we still want to prove that the CPU transitions are correct and they're progressing correctly, but then we need to give them some protection that also the memory accesses they get to see are actually correct. So we can imagine augmenting the state of the CPU, ZI, with a digest of the memory, right? So think of this for now just as like a hash or a commitment to the memory. And then when we give the transition function these kind of memory addresses, then let's also give it some information so it can check that these accesses are correct. So let me give you, okay, so the big picture here then is, okay, so now with these additional checks, with these additional digests, when we do this incremental verifiable computation, now we also have memory protection, and now when we get out the correct proof for the result, we know that both the CPU has executed correctly and also all the memory accesses are consistent with one global random access memory. So let me give you an example of how this could be done. Okay, so think of a Merkle commitment to the memory. So we start by committing to the full memory in a Merkle tree, and we give the root as the digest, as input, right? So part of the state. Okay, that's just like small hash value, so it's a very small addition to the state. And now whenever you are accessing the memory, we will not only give the accesses to memory, but we will also give Merkle paths to the root, right? Now it's something you can, for every access to the memory, you can check that this is actually consistent with the memory that's committed in that Merkle tree root. Okay? And the cost as well, so on the logarithmic size of the memory, right, is sort of like the length of this path, right? And you have to check each of those, right? And that's sort of like, you know, if it's a large memory and you're only doing a few memory accesses, then that's going to be cheaper than having constraints for the full memory. So this is great. It works. However, it's inefficient, right? Because for each access to the memory, the prover now has to prove that it's seen a Merkle path to the root of the tree. And proving hashes is expensive, right? So it costs a lot of constraints. So we implemented this with Poseidon, which is like a fairly CK-friendly type of hash function, right? And we're talking about like hundreds of constraints that we have to implement and to check this path here. So the question is, can we do better? Okay, and the answer is going to be yes. So let me give you first a little bit of background as what it is that we really want to prove in order for the memory to be consistent. So here's a common technique that is often used, is to think of a read set and a write set that tracks all the memory accesses. Okay? And we will think of the execution as first we will do some initialization. That's just where we're writing what is the initial memory. In this case, I only have 2 addresses in here, right? Then we'll have the execution, okay? And when we do an execution, if we load a value, then we would read that value, and then we will write that value back again, okay? So for every access to the memory, we both do a read and a write. If we store a value, then we will read a value, and then we would write the new value that we're storing. And the reason we're doing this is that, well, every time we write something to a cell, then we update what is the timestamp when we accessed and what was like the last time this cell was used. So when we have a always read and then write pattern, we make sure that every cell has been written just once before that was the last time it was written to, and then we sort of like read that and then we write a new thing, right? So we're always making sure that the read set sort of like trails the write set. And then when we are done with the computation, then we'll just have the final read of everything and discard that. And the reason we do that is that we can actually now check that the memory consistent it is equivalent to the constraint that the read set is equal to the write set. Okay, so you have some local checks, so you'll check locally that, for instance, whenever you load a value, then you should be reading that value, but you have to write exactly the same value back, right? You cannot change the value. Whereas if you have a store operation, then you would read a value, but you can write something different back. So there are these kind of local constraints, okay? And then if those local constraints are satisfied, and we also have that the read set is equal to the write set at the end, then we know that the memory is consistent throughout. The question is now how to check that, right? Because these read sets and write sets, they also grow really big. Okay, so that's not something we want to store inside the CKVM. And for that, I'm going to talk about using multi-set hash functions. Okay, so something that was proposed in the CK context by Set et al. In 2018. So a multi-set hash function takes a set of values from a message space, okay, and produces a small digest, okay, and should have this compression functionality that digest should be really small regardless of the size of the multiset. The other property we want is that if we have a couple of multiset hashes to two sets, we should be able to compute the multiset hash of their union. Okay, and remember these are multisets, so all the elements are counted with multiplicities. They may be repeating in the set. And finally, we should have collision resistance, that if we had two different multisets, then it should be hard to find them, so they actually map to the same thing. So let me give you a standard construction for that. So we're using here a group G, okay, and think of this like a standard prime order group, where the discrete logarithm problem should be hard. And then we take a hash function, and you may think of that as a random oracle for now. So, and then we just go through all the elements in the multiset, hash them, and we add together these hashes, right? Because hash outputs group elements. Okay? And it has the compression functionality, right? Because now, regardless of the size of the multiset hash is just one group element. It's also pretty easy to see that we have the incrementality property, right? So if you want to, if you have the multiset hash for one set, you have the multiset hash for the second set. When you add those two, right, then you're just taking the sum of all the hashes in both of the sets. You get the multiset hash of the union of those two sets. And finally, you have the collision resistance property, right? If you have two multiset hashes that are equal to each other, well, the first one is just the sum of hashes in that set. You can subtract then the hashes in the second set, and that should be 0. And if those two sets, well, if the two sets are identical, yes, obviously you get 0, right? But if they're different, then when you count with multiplicities, so those are the A's, right, you would actually get a non-trivial sum to 0. And if you model the hash function as a random oracle, that means that now you have some group elements where you don't know the discrete logs and you have made them sum to 0, right? So now you've broken the discrete log problem. So how can we use a multiset hashing to check memory? Well, the idea is now that instead of directly keeping track of the read set and the write set, we will just have the digest of those. We will have the multiset hash of the read set and the write set and keep updating that. Okay? So on the right-hand side here, we have the digest of the read set and digest of the write set. The digest of the read set, well, we've not actually read any values, so that's just 0 to start with. The write set starts with the first initialization we do, and then we hash that, right? And then we keep on updating whenever we do one of these operations. We update those two sets accordingly. Okay? And at the very end, right, if the read set is equal to the write set, then those two digests, they match. And if the read set and write set is not equal to each other, then by the collision resistance property, the digests do not match. So that gives us a guarantee that the read sets and the write sets match in the end. And the cool thing is that this is like, you only keep track of the group elements, right, these set hashes along the way and update those, okay? And even if you have different workers that are doing different slices of the computation, then that's still fine, right? It's just a local operation. I'm getting some digest, and I'm updating that digest, regardless of what has happened elsewhere in the execution. So multiset hashing is a way to allow you to check that the memory is consistent just with local operations, and then this multiset hash digest that you're evolving over time. Okay, so how does that usually work? Well, you have the group. That could be an elliptic curve. Let's say it has a prime number of points for simplicity. We can generalize that. We have a cryptographic hash function that maps into the field FQ, and then we typically have a map to group function that maps into the group. right? And then the hash to group function is the composition of those two. So that's the standard construction. And it's an expensive construction, right? Because what is the cost here? Well, you have to do this hash function first, and then you do sort of like a mapping, okay? And that hashing function is an expensive operation, right? This is a cryptographic hash function. So now you have to compute and verify a hash in every step. And this is where we're sort of like starting to think then, okay, what are the minimal requirements that we want from this hash function, hash to group function? We want it to have collision resistance, right? Because if you have two elements that hash to the same value, then it's very easy to find multisets with just singleton elements that hash to the same. But maybe we don't need cryptography for that. Maybe we can just use an injective map, right? So that's sort of like the idea we're exploring here. Okay, so can we just use that map to group function instead of having a hash, okay? And of course, this requires that the message spaces of modest size, right? Because if it was arbitrary large elements, then, well, you do need a collision-resistant cryptographic function for that. But if it's a small size set, then maybe actually the size of the set is smaller than the group, and it's possible to have an injective function and get collision resistance through injectivity. And interestingly, when we do memory checking, then we do actually maybe have small sizes, right? So think about like what would in practice be the size of like you have an address, you have a value, you have a timestamp. Well, maybe there are 32 bits, 32 bits, 32 bits, or something like that. That's 96 bits, right? That is modest size. So we are actually in a situation where we could use just a hash function for modest size sets, for modest size elements, right? And therefore maybe injectivity is something that we can use when we're doing memory checking in ZKVMs. So there's one other thing that we need to be careful now when we don't have like this hash function inside to make things look random. And that is you may also be able to find two elements where we're mapping to the inverse of the element, right? Because in an elliptic curve group, it's very easy to just take the inverse of a point by flipping the y coordinate. So we actually need, and if you can find that right, then you can also find a non-empty set that maps to the same multiset hash as the empty set, right? Because M1 and M2 would, the multiset hash of those they would just cancel out, right? And you would get 0. Okay, so we need to be careful about that. So we actually need a map to group function which is injective with respect to the x coordinates, right? So it's sort of like resistant to the sign flip. Okay? And interestingly, we can show that if we have those two properties, then we can actually get just use the map to group function, and it is secure in the elliptic curve generic group model. Okay? Let me see. I have 2-3 minutes left? Yeah, okay. So I'll just very quickly give you sort of like a feel for what could this function look like, okay? So it's pretty straightforward. You take the message, you add a little tweak to it, and you try to use that as the x-coordinate, right? And the tweak is there because not all the x-coordinates, only half of them are actually good x-coordinates, so we need the tweak to just make sure that we get something which is a valid x-coordinate. And then the function also needs to make sure that we cannot flip the sign. We suggest if q is equal to 3 mod 4, that we just make sure that y is the quadratic residue, right? Because only one of y or minus y is going to be a quadratic residue. And you return that point. Okay, and let me, okay. And, okay, so what are the constraints we need to ensure this? Well, we need to make sure that X is actually something that matches a point in the group, right? We need to make sure that X is a valid jump with this tweak. We need to make sure that the Y coordinate is unique, so we cannot flip the sign. Okay? And all of those are pretty straight, simple constraints to verify. Okay? So using this kind of multi-set hash to map to group function, then we have a deterministic map that can be used to sample such points. Okay, there's one more thing to be a little careful about, which is that you could imagine that the prover, instead of using the smallest tweak, used a different tweak. And this is why I'm switching from map to group functions to map to group languages, because actually it turns out that it doesn't help the provers if they're cheating that way. And that means that we don't have to go through the trouble of proving that the tweak is the smallest possible one, right? It just has to be one of the valid tweaks. Okay, so the construction, if we instead use the map to group function, looks like this, just as before. And as you've seen, we only need a very small number of constraints to check that a map to group function is evaluated correctly. Okay, and with that, I'll stop my talk. Thank you.
Thank you very much, Jens. Unfortunately, we won't have time for questions, but Jens, if you're okay with it, maybe people can find you just outside the room. Thank you. Our next speaker is Ariel Gabizon from Aztec Labs, who's going to present about going from IVC to RCGs. Let's give people a few seconds to make their way in or out, and then let's get started. I'll be sat here, and I'll wave at you. Thank you very much. Oh, sorry. You ready? Yeah. Cool. Ariel, please take it away.
Use this one. Yeah. Okay. Thanks. Right, so I always get a haircut that conveys zero knowledge about where my bald spots are before I talk about zero knowledge. So, okay, so let me give you a small outline of the talk. First, I'll start with some simplified details about the Aztec smart contract system. This will lead us to define a notion called repeated computation with global state. That's, then we'll go over how to deal with global state using log derivative methods. And I'll end by highlighting a theoretical issue I want theoreticians to look into. So Aztec is about private smart contracts. So like Ethereum, a contract has functions, but since everything is snarkified, every function, say A and B, have some verification key that matches the function. And what can functions do? Well, one important thing they can do for this talk is that they can call each other. A function can call a function in the same contract or a different contract. So let's spend a few minutes thinking about what does it mean for like snark circuits to call each other. So for example, let's say we have this execution. We're calling A with args A. Somewhere in the middle of this execution, it's calling B with args B. And we want to make a proof of such an execution. So the basic idea is A's public input will contain the verification key of B and the arguments of B. And you may be wondering why is this an issue at all to prove such an execution? Like, don't we have such stuff? And we sort of do. Like, what's a little different in the Aztec scenario is that the functions are already individually snarkified. So A has VKA, B has VKB, and we're expected to use those keys. Okay, so here's what this could look like. So we'll construct a proof for A, called the proof pi A, where the public input now contains the arguments to A, but also the verification key of B and the arguments to B. And now we'll construct a proof for B, where the public input is just the arguments to B. And we'll have a verifier check the proof for A with key VKA and public input XA. We'll have the verifier also check proof pi B for with verification key VKB and public input XB. And since this V will use the same args B and VKB for checking A and checking B, this corresponds intuitively to A calling B. That's the basic idea. Okay, but now we want to massage this to a more uniform form. So we want to think of these different steps as iterations of the same function. So we'll have this function f, where the inputs of f are the current vk, the current public input, which again consists of the current arguments of the current function, the next verification key, and the next arguments. And by the way, this is sort of an arbitrary choice for simplicity, that like the current function is calling at most one other function. It might be even more natural to think of it as calling several. In the code, it's 4, the maximum. And also, another argument of f is the current proof, pi, and the current stack of functions to be called. And now what does f check? So it checks that the element at the top of the stack is the current vk and the current args, and it'll pop it off the stack. It'll check that the proof pi with public input x and the current vk accepts. And it'll push to the stack, to the top of the stack, the next function, the next vk and the next args. Another sort of simplification here for presentation is, so here it looks in step 2 that pi is like a full snark proof, and we're verifying a snark proof. In the actual protocol, the step 2 is just what's called folding a proof of correctness, or really just folding the witness. So, like, if you want to make it closer to what's actually going on, pi is, you can think of it as just is really as a witness, as the actual original witness. Yeah, but for simplicity, you can also just think of pi as a proof. All right, so this is just this F is like a way to, when we have a sequence of calls, just a way to think of those and in each call is right for a totally different function potentially, right? Because different contracts have different functions. But this F is like a way of thinking of this, process of one function calling another is just iterations of the same capital F. But we so far, we forgot to deal with global state. In addition to functions, a contract in Aztec will have notes representing its state. For example, the notes N1 and N2. And in addition to calling other functions, a function, while it's executing, can add, read, or delete notes of its contract. So to enable these global state operation, we'll add to the public inputs. So far we had the current arguments, the arguments and the VK of the function you're going to call next maybe. We'll also add to the public input the note operations you're doing. So for example, here like the call to A and these operations, they will have timestamps. So for example here, the call to A is reading note N at timestamp 8. And the call to B is creating or adding note N at timestamp 3. And now the problem to deal with is, so when we're verifying the proof to A, we see this note operation, read note N at timestamp 8. But while we're verifying this proof, we can't be sure that in some future IVC iteration, we'll indeed see the note N created, and moreover created with an earlier timestamp. Right? We don't want to read notes that haven't been created, and we also don't want to read notes at an earlier timestamp than when they were created. So at a higher level, the order of proving here is different than the order of execution. Since, like I said before, the functions have already been individually snarkified, right? In execution, we start with A, go into B, finish B, go back to A, finish A. But since the functions are individually already snarkified, we have to prove it in a different order. We have to do all the proof for A, and then all the proof for B. So in execution, the node n was created before it was read, but in proving, we're only going to get to that creation of the node n later in the proving process. So to conveniently deal with this setting, we define the notion of RCG, repeated computation with global state. At a high level, or even a less than high level, RCG is very similar to incrementally verifiable computation, IVC, which you've probably heard of a lot. But there's two differences. So the first difference is that in RCG, we know the endpoint. The computation ends before proving starts. So if in the original IVC paper, Paul Valiant is talking about a computation humanity is going to be doing for generations, here we're assuming the computation has ended before the proving is started. So then, well, you could say, okay, so then is it like IVC at all if it's already ended? So why is it even similar? So the desirable property in IVC is what people, they call complexity preserving sometimes, that the prover memory, even if the computation has many steps, the prover memory depends on the memory of the one step. For example, one execution of this function capital F we had below. So in RCG, we still want to sort of have that property, but we relax it. So we say the prover memory should mainly depend on the memory for one iteration, but it's also allowed to depend on the size of the global state. So let me walk you through a simplified version of the actual definition. So we're going to have, to define an RCG relation, we're going to have a transition predicate and a final predicate. And now we're going to say these transition and final predicate, they define the relation of pairs XW, where X, so what is X? X contains the final state, sort of, Z final, and the number of iterations, N. And W contains 3 vectors, Z, W, and S, where intuitively, Z is going to be the different states we go through. W is going to be the witnesses that get us through those states. And the S's are the chunks of the global state we use in each iteration. So we say that XW is in the relation if, well, we end, Zn is Z final, so we end in the desired final state. For each I, the transition holds, so f of zi minus 1, wi, zi, si is valid, is accept. And the final predicate if we insert into it all the s's from all the iterations, it outputs accept. Right, so this third thing is like where we have this additional ability that we wouldn't have in IVC. We are allowed to test some final predicate of little, we think of them as relatively little chunks from all the iterations. And again, the point is, you could just say, okay, just build a snark for this relation. Why do you call it RCG? Just build a big circuit. And again, the point, the IVC-like kind of point is, we say a snark is space efficient if the prover requires space. I'm not formally define here the size of f, but requires space which is roughly the size of one step plus the size of the global state. That's the memory that we allow the prover to use. So, like I said, this is a simplified definition. I will raise one little hole in this simplified definition that maybe has occurred to some people here. Maybe we want to hide the number of iterations when we do the ZK snark. So in the actual relation, this n is not part of the instance x. What's part of the instance x is some bound c on n, and n is part of the witness. Yeah. Okay, so to illustrate this point, so let's see how we use, an example of a sort of RCG to deal with these memory operations. We're going to add to the add operations. We're going to add the number of times. By the way, if you don't have deja vu, is because I prepared these slides according to previous talks of Jens. So we're going to add to the add operations the number of times a note was read. So that's this numReads field. We're going to add to the read operations. We have the timestamp where the note was read. We're going to add to the read operations the timestamp where the note that's being read was added. So that's this AT. And now what are we going to check? So in the transition function, we're going to check for each read that AT is smaller than T, that the alleged time of creation of the note was smaller than the time we're reading it. And now we're going to sort of use the fact that we're allowed more memory in the size of the global state. So the prover is going to store all the node operations from across the iterations. And it's going to hash them to get some challenge beta. And so now, right, so our goal is to check that every time you have a read, you're reading a note that was really added and also added at an earlier timestamp. So this check AT smaller than T sort of checks that if this node is legit, that the timestamp of addition is smaller as needed, but But right, it could be that when I have this read n ATT, it could be that there actually does not, I'm not going to have an operation add like n AT. It's just, so we need to check that all the alleged creations of notes really happened. And that's going to be done by this fractional sum. So, right, we're going to check that the sum of the reads of this expression, think of the node as just a value in the field. We're going to have this sum over the reads of 1 over n plus beta times AT, the alleged time of creation of the nodes. And we're going to compare that to, we're going to sum now over all add operations from all iterations. And we're going to compare that to now, for each read, we put in the numerator the alleged number of times the note was read, and we divide that by n plus beta times t, plus the timestamp of the add. And you can see that if some attempt to cheat was made, like there's a read operation for a note that doesn't exist, then with very high probability over beta, this sum won't be equal. Five, okay. Okay, so that's some details from the construction, and I want to end by highlighting a theoretical issue that I think could benefit from scrutiny. So in this paper, to make our proofs easier, or easy, or at least easier, we use what I call the recursive algebraic group model that was implicitly introduced in this paper, Analyzing Nova by Li and Seo. I hope I'm saying that right. And let me explain to you what this recursive algebraic model is. So let's talk about the original AGM. What was the idea there? The idea there is that if I have some structured reference string of elements of the group, then when an adversary outputs some A in the group, they must also explain how they got to this A by the SRS elements. So they must output also a vector of scalars C, such that this A is equal to some CIVI. Okay, but now let's say these group elements, we're representing them as pairs of field elements. So fix some representation function of G by pairs of field elements. And now suppose that the algebraic adversary outputted this vector C, and it just so happens that for some two adjacent indices in this vector of scalars C, Ci plus 1 is a valid representation of some group element B. So you could ask, you could ask, well, shouldn't the algebraic adversary now also give us explain to us how he got to B using the SRS? And some would say, no, you shouldn't do that. But the recursive algebraic group model says, yes, you should definitely make the adversary's life a bit harder and your analysis a bit easier. And yes, you should you should demand an explanation of how to also make B from the SRS elements. So the recursive algebraic adversary now must also output C prime, such that B is some C prime IVI. And then you ask, well, what if C prime, there's some two indices that are valid, does he have to do it again? Yes, that's why there's recursive in the name. So the recursive algebraic adversary must keep outputting these vectors of scalars C until his output vectors with nothing there, no two adjacent elements there are. Right, and as a sanity check, you could say, well, won't you always by accident there'll be some ci plus 1 like this and there'll be an infinite loop? Well, it shouldn't be because, right, if f and g are of similar size in the elliptic curve case, it shouldn't happen by accident that, you know. So this is the question I want theoreticians to look at, because I really like writing proofs with this thing for IVC. So I want people to look into, is this legit? And yeah, so that's sort of a shout out for that. Yeah, and so thanks for listening. Thank you.
Thank you very much, Ariel. We have a bit of time for questions, if you have any. One over there. Oh.
Hi, Ariel. Great talk. In the recursive AGM, algebraic group model, is it necessary that Ci and Ci plus 1, they are consecutive? Like it could be any two.
Yeah, that's a great question. It is a little ad hoc to look at all adjacent pairs. The reason why you can't look at all subsets is there's an exponential number of them, and then you will be in a situation where, oh, just by chance, something is a representation and the adversary will be in an infinite loop.
Any other questions? All right, so let's thank our speaker again. We will now go on a break until 12. So feel free to go get coffee and mingle, and we'll be back here at 12. Thank you. All right, welcome back to this second session on the main stage. Our next speaker is Albert Rubio, and he's going to be talking about circumbosses, the power to structure ZK circuits. Please take it away, Albert.
Thank you for the introduction. One second. Okay, so I'm here, welcome everybody. So I'm here to present this new feature of Circum. And I'm expecting that all of you know a little bit of Circum, otherwise it won't be easy to follow. But in any case, just to show that we are adding an important feature from the point of view of Circum as a programming language. Okay, so just a bit of context of what is Circum intended to help us in a zero-knowledge protocol. It's just this part that is in black, which is we have to build a circuit and be able to run this circuit. Okay, so this is where Circum help us. Okay, and so Circum is a DSL that has this special way of working, which is to explicitly provide the constraints of the circuit. Okay, so all is explicit, and then you can also provide an efficient way to compute the witness if you need, and in many cases this goes together. So circuits that we can use to build our new circuits on top of it. And this is encouraged because we can trust on these circuits and then we build on top of this, and in many cases we can get really safe circuits just because we build on top of things that we know are safe. Okay? So we have this nice ecosystem of tools and so on, but when writing circuits programs with Circum, we have a little bit, we are lacking types like in other languages. Okay, so because currently until yesterday, the only types you had in Circum were signals and arrays of signals. Okay, so of course you can do everything with that, but well, it's not the best way to work. Okay, so what I'm going to present here is that we will now be able to define new types, make collections of signals, and so on. So then what's the compiler doing? The compiler produces both things. The circuit, which is a constraint system in R1CS, and an executable in WebAssembly, currently in WebAssembly or C++, that can be used to run efficiently the circuit. Okay, so this is what the compiler produces out of the Circum code. Okay, so now let's motivate the problem. So this is just a piece of code from the library, from the baby jab circuit, and this is the other for this elliptic curve. And here you see that what we want to express is an addition. So 2 points added give a new point. Okay, but since we have no types, what we can do? So we have 4 inputs and 2 outputs that are just signals. Okay, because of the names, maybe you can figure out what is the meaning. So the first 2 are the 1 point, the second are the other point, and so on. Okay, but nothing is really making this as each pair as a whole, okay, as something that you know it goes together. Okay, so this what you can do, and then what happens? That you really want points, but you have signals, just signals. Okay, and even worse, in fact, they are signals. In this case, in the twisted Edwards form. Okay, so but they're just signals. Okay, so we are not seeing this anywhere, and it's not going to be checked in any place by the compiler. Okay, so we need, after this, we need better types. Okay, to structure the information, and then also to increase security, because if we add new types, then the compiler can check these types. Okay, and then we know that what we are passing is of the appropriate type. So this is what we pretend to do this. And here is what we get with buses. Okay, so buses are like structs in other languages, but we are programming circuits, so then we have buses, because bus is the name in a circuit. So from now on, we will use buses. And buses, the nice thing is that all can be mixed up from now on. So you can use you can define buses using signals, arrays of signals, and other buses, combine it with arrays of buses, whatever you like. So everything can be used in an orthogonal way. Okay, so the other thing that we don't have currently, but it will come, I hope, in few time, is recursion in the definition of buses, because we have to decide how to handle the null or something like this. Okay, so then buses define new types. Okay, and then type checking prevents from mixing different types. Okay, so the security is obtained like in other programming languages from now on. Okay, since you have types, so the compiler will type check everything, and you will avoid maybe using signals that have not a real meaning you expect. Okay, so this is the point. And then very soon we will release a new version of the Circum library, which is the circumlib, using all these buses and change completely. I will talk about this a bit later. So what we believe is that a complex Circum program in production, and we have seen many projects that use Circum in the introduction, so must use these buses to increase readability, because if you want to audit your circuit, buses will help a lot, and also to increase security. Okay, so let's do a little bit of practice with this. So the very easy example. Okay, so suppose that you want to compare dates or whatever, and we have the problem as before. Okay, and then you can use names of the signals to help a little bit, but this is not much. Okay? Later you can say, well, no, let's put it all together because then it will be clearer. But I'm not sure this is clearer than before. Because now, what's the day? The 0 or the 1 position? Okay? You don't know, and it's impossible to know. Okay? So it makes not much sense to do it like this. Okay? So what can we do? So, of course, use a bus, use a struct. Okay? Then you define it like this. And from now on, you can now define templates, you see, using this, like before we had signals. Okay? So it's simply as simple as this. Okay? Note one little difference. So there is just a tiny difference. Before, it was the input and the output keywords were in the middle. And that is quite ugly with buses. So we decided to change a little bit the syntax, and from now on, the recommended syntax is to put the input word, keyword and output keywords first, and then the type, and then the name. Okay? But the old style will be still valid. It will compile and no problem. Okay? But just take this into account. It's nicer if it is written like this. Okay, let's go a little bit further. What can we do with buses? Not only this simple thing. We can now have parameterized buses like we have parameterized templates. Okay, so this parameter is something that will be known at compile time. And exactly the same you have for templates, you will have it for buses. And then here what we do is just we define this array of dates using this parameter. And the nice point is that then everything fits well with the templates, because, for instance, here I can define a template with a parameter n that uses an input uses the same parameter, and then everything will work well with the sizes of things and so on. Okay? And then, of course, then you can call another template with the same n, but then I pass the field of the array of dates, and everything matches the types, and everything compiles. Okay? In general, I would say that clearly this looks nicer and it's far more readable. Okay? Otherwise, there will be all this amount of signals around, all mixed. You have to choose whether you have arrays of arrays or many arrays. So it's just much cleaner and easy to read. Okay, now we go a step further and we mix buses and tags. Tags is something we introduced kind of 2 years ago. And we were having a bit of subtyping with tags, and now we'll have types and subtypes. This is what I want to present here with this mix of buses and tags. So the point is this, that tags provide a simple form of subtyping. Okay? We don't have inheritance and things like this, but we get a little bit of subtyping with tags, but now it's really far more powerful combined with buses. Because now we have types, and then we can just get a little bit of subtyping with tags. And then what happens is that we create new types with buses, and we define subtype relations using tags. Okay, so you see here that then when you define a bus or use a bus, so tags can be inside and outside, and with different meanings. If you have it inside, they somehow are restricting every instance of this bus. I'm saying that this field has this property, okay? So I'm restricting what should be in the bus. And if I add it outside when using the bus, then I'm restricting the particular instance of the bus, okay? So I can do it both. I can define something that I always want to have this property in a field, I add the tag inside the bus. But if it's something that maybe sometimes I need it and sometimes I don't, then I add it outside when using it. Okay? So the point is somehow that before we were only with signals, we were only able to express tags properties of a single signal. Now, since we can put a tag on a whole bus, we can express properties of a combination of signals. Okay? So it's much nicer in this sense. And later on, if you add verification techniques and so on, it will go much better because we can check the semantics of a whole bunch of signals that go together. Okay, so let's see it in the example of dates and going a bit further than this. So this is what I mean by tags inside. Okay, so I here say, for instance, don't be much worried about the semantics of these tags and why I'm using max bit for day, and just to show that you can use different tags and as many as you like, none, 1, 2, different things for different signals, okay, whatever you like. Okay, so this is just meaning that there is some bound restriction on the signals you can get there. Okay, so there is one thing. But then suppose I create this bus which is profile for an ID, and then for a bunch of dates, meaning whatever. And then what I want to add for dates is that this is a valid date. Okay, so then I add this tag saying this is a valid date. And what's that? So I can have a template that creates a valid date from, and what's the meaning of creating a valid date? It means adding constraints that ensure that the date is valid. Okay, we are creating circuits that ensure things. Okay, so we can do that. And look, if I do the template without any assumption on the input signals, then I add here constraints and so on, checking all the properties. The properties of the day, the month, and then also the global properties of if the month is this one is January, then it should be between 1 and 31. If it's blah, blah, blah. Okay? But the difference between the input and output and the fact that whether I already know some property or not. Suppose that because this is used in some context, I already know all these tags from outside. Then, if I know that it should be like this, then I have it in my circuit, and I don't need to recheck it again. You know, if you have built circuits many times, since you're not sure whether you know or you know something or not, you keep adding the same constraints again and again and again. So using types and subtypes by means of tags, we avoid a lot of recheckings of things, and which end up with a better and more efficient circuit. Okay, so now, what's the impact of all that in the circumlip? So, well, huge. Okay? But I will just show a little bit. So what we are doing in this one while writing is adding buses and tags everywhere, or in many places, and also making it compatible with different primes. Remember that initially we only have this BN prime, and then circumlip was intended to be used with this prime. But now we have kind of, I don't remember, maybe 6 more primes or even more. And then what happens with the circumlip is not adapted to this. So we are just ensuring all the circuits that we can being compatible with every prime. Okay, so of course you will use which prime are you exactly using and so on, but you can make it. And this will be a nice improvement. So the nice thing is that we have added these buses and tags, and still we have been able to prove and formally prove that in most cases the number of constraints remains the same. Well, when using minus 0.1. Okay. By the way, which is now the default. Until now, the default was 0.2, but from this release on, the default is 0.1, because many people is using Circum for Plonk, and then 0.2 is not the way to go. Okay, so from now on, this is the default. Okay, so keep it in mind, because it's important. And of course, looking at the new circumlip will help to understand and get ideas about how to use and where to use this. So let's show a simple example of one single example of this use. Okay, so let's come back to this baby jab electric curve. So you have the others and so on for the twisted Edwards form. Okay, look there, point. It's just like this. You have 4 inputs and 2 outputs, no meaning apart from X, Y used in the name. And then you have the version, the Montgomery, the others for the Montgomery form. And all of a sudden, now it's no longer 2 signals, but an array of dimension 2. Okay, so as the creator, I was not there. So, and you have this, okay? So, for instance, this difference. But even more, if then you look at the conversion from Edwards to Montgomery and back, so here you see, you have even this kind of, well, it's not a type inconsistency, but inconsistency, but you have there express the point with 2 signals, and here's an array of dimension 2. Okay, but it's all the same because I have 2 signals. Okay, but it's not helping to read, and also it's clearly error prone because you can mix things that you don't want to mix. Okay, so let's do it with buses, which is far more natural. Then I have a type for Edwards point. Okay, so 2 fields, and that's it. And then, oh, what a nice thing. Okay, you see? This P1 point, Edwards point, P2, Edwards point. Oh, now I go to the Montgomery form, another bus. Okay, so Montgomery point. Then, oof, nice again. You look, it's clearly different. Okay, and you will never mix both because you cannot pass one type to the other because the compiler would say no, would say type error. Okay, and now look. It matches perfectly. You get a converter that takes an Edwards point and produces a Montgomery point. Okay, and same reverse. Okay, so now it's readable, and thanks to the type check, you have type safety. Okay, so it's clearly more reliable. Of course, it's far more readable and more reliable. Okay? You understand a bit more what you're doing. But now let's do this with tags. Then the point is this subtyping. So because we've seen that they're all points. So should we have these 2 points? Well, a proposal is no, use only points, and then use tags to distinguish them. So here, you see, you have points, and then you have the tag Edwards. And in the other way, we don't add a new boss, but we use the same, but we add the tag Montgomery. Okay? Now you cannot mix them again, because you will check whether you have the tag and you or not. And of course, except if you, for some reason, decide to add yourself 2 tags, which you, I mean, still it's possible to make mistakes like in other languages, but on purpose, you have to define a type for something that you really don't know if it is fulfilling the properties or not. Okay, so there is the kind of things that will be prevented thanks to types in this context. Okay, so then what we have is this, and this, and then when you have the conversions, everything matches again, because here I will get this Edwards point, then I get an output point with the Montgomery tag that I will be able to use there in the other because it has the tag. Okay, everything matches types, and it works nicely. Okay, of course, all this is checked by the compiler in the type check, and it has no impact at all in the amount of constraints and so. Okay, if you need to add some extra constraints because you need to be sure that the conditions that you have associated to the type are met, then you add constraints. Okay, but there is what you should do. It cannot be that you assume that something fulfills a property, but you don't add constraints, because then, of course, maybe what you produce with the windows will fulfill it, but someone can send you a proof that is not fulfilling this, and you will just say, okay, good. So then, with tags and buses, we get readability, type safety, but also we are far more reusable with the code, because maybe we have operations for points that are always the same, and we can reuse it in both cases. Okay, so it's just the standard situation with subtyping. Okay, it simply helps in reusability. So finally, what we have in this, as I said, in this new circumlib, we have added these buses, tags, and make it compatible. And the nice thing is that what we pretend is that if someone builds circuits on top of the circuits from the circumlib, can be in the safe side, in the sense that we can even certify that if you only use the templates of the circumlib to create new buses or to add tags and so on, then you are sure that the properties are fulfilled. And you're using properly the baby jab elliptic curve and so on. Okay? So it's these kind of things. You're not making mistakes in this sense. You're using things properly, and you can trust all this. Okay? So you are safe just by default because you're building on something safe. So we'll, later on in the future, we will really give a precise definition of this. But this is what we intend to do, to have circuits that are safe by construction. Okay? And, well, we are still improving and extending it, so it will be ready very soon, but it's not yet. So conclusions. So Circum is really one of the most widely used languages for zero-knowledge protocols. As I said, many of the projects that were shown in the intro are built using Circum. And, but until now, we're missing these extra types or this type system, a proper type system in the language. And this is what we are providing with in this new release. Okay, these buses that provide us the way to structure circuits. It provides a far more convenient type system, and then we can ensure this type safety. And also, we believe that it will help auditing GKE projects. And the new circumlib will take advantage of all this. Thank you.
Thank you very much, Albert. Do we have any questions? Oh, great.
Yeah, so at one point you said that Circumlib 2 was using some kind of formal verification. What exactly did you use, and how did you do it?
Well, I said what I said is that what we have formally verified. I mean, you know, there are circuits made of many, sometimes thousands of constraints even for the Circumlib, for just a simple part, just using one of these circuits in the Circumlib. Okay, so then, imagine that you want to check that introducing all these, you are not having an overhead in the number of constraints. Okay, so you want to check, and also you want to check that you are seeing the same, because the Circumlib was already audited. Okay, so imagine if we just don't know if they are the same after changing, we need to audit again. So what we have verified for most of them, and the ones that they don't fulfill the property of being exactly the same as before, is because we already know that we have added some extra constraints, okay? Because we know it in purpose. Or we have removed some constraints because of the tags. We know that this was already checked, so then we don't need to add them. But apart from these situations, we have proved that the circuits before and now are the same, but simply are defined and described in a much better way, okay? More readable, and also nicer in the sense that you can use them in a safe way, okay? So this is the key point. So this is what we have verified.
I think we have time for one more question.
Could you perhaps compare and contrast what sorts of things can go in buses and what kinds of things can go in templates? For example,
Sorry, in buses?
Is it possible to put something like a constraint or a witness generation procedure inside of a bus, such that all instances of the bus have that, or not?
No, so that would, okay, nice question. So thank you. So there is the point where we have code inside the bus and is producing constraints. So we are not allowing any code inside the bus by now, but probably we will. But only to the finally, so for instance, if you want to have this recursion, it would be good to have, using the parameter, deciding whether some field is there or not. And then you can have a nice form of, because the notion of null in a circuit is not easy, okay? So it's a weird, it has a weird semantics. But if you can add code, you can have a conditional saying, well, if n is 0, then you don't have this field, okay, for instance. And then you can probably add some code this way. I don't think we will like to add code in the sense that if you have some bus, it will just directly introduce a set of constraints. We are not planning to have this.
Great. Thank you very much. Let's thank our speaker once again. And welcome to the stage our next speakers, Vivek and Andrew from the Cursive team, who are going to talk about building cryptographic apps for human connection.
Okay, hello everyone. My name is Andrew. This is Vivek, and today we're going to talk about building cryptographic apps for human connection. So first off, why combine cryptography and human connection? Why are they such a good fit? Well, it really comes down to two things. Human connection is centered around discoverability and depth. Discoverability means finding more quantity of connections, more opportunities to connect with people. And depth is about making each one of those connections more meaningful. First off is discoverability. So many social apps today are using a push-based model. So big algorithms or advertising feeds tell you what you're going to look at. You don't really have control over what you see. And in addition, these feeds are based on maximizing how much time and money you spend on the apps. On the other hand, cryptography offers a few advantages here. You own your own data. So you get to choose how you interact with these apps. You get to choose who gets to see your data, and also what types of connections you're able to find. Now, depth is another facet where a lot of social apps today are lacking. If you look at popular apps like Tinder or Instagram, these are all centered around you making a public profile that's based on who you want other people to see you as, rather than who you actually are. They're not centered around connection, they're centered around your public persona. In addition to that, none of this data is verifiable. You can basically put whatever you want on your Tinder, you can put whatever you want on your Instagram, and you're crafting an image for other people to see. And as a result, this leads to a lot of fake data, a lot of fake profiles, and a lack of genuine connection. Cryptography helps this in a few ways. First off, it makes sure data is verifiable, that it has a source of provenance to it. In addition to that, because now you have access to private data, you can include a lot more meaningful sources of information within your profiles. You can include data that is more personal to you and reflects who you actually are. In addition to that, compute primitives like MPC or FHE ensure that you can still create meaningful primitives on top of this data. Okay, so why do we care right now? Why is it so important to build apps with cryptography at this moment? Well, there's really two reasons. One of them is technological, and the other one is social. First off is the technology side. As many of you might have experienced last year at ZK Summit, we actually did a similar experiment with these NFC cards that you all have. But actually, a lot of the tooling we have access to today, it simply wasn't there a few months ago. Things like non-interactive, multi-party FHE, and Trinity, both of which Vivek is going to talk about later on in this presentation, they simply weren't production ready at the time. So a lot of the primitives that we really depend on are now here, and they're ready to go. In addition to that, primitives like ZK email and ZK TLS ensure that we can actually use this data today. We can take data from Web 2 silos, make it portable, and include it in our applications. Finally, consumer devices are getting a lot better. Client-side proving is becoming more important. Tools like NOR, tools like MPZ, Phantom Zone, all these are designed for computational loads on commodity hardware. And they ensure that we can actually do more meaningful computation in the devices that are in your pockets. Okay. Now, the other side of this is social. It's about how social media apps have developed and evolved up until today. This is a really interesting Twitter post, and it's about how in a recent marketing campaign, Facebook didn't mention the word friend a single time. They just didn't say it. And instead, they were talking about feeds, they were talking about content, and all this other stuff. But the original values of friends and connection that Facebook started with simply aren't there anymore. Social media today is about attention and not connection. But at the same time, people are searching more and more for connection. Maybe these are a little small and you can't read it, but to summarize, people have fewer friends today than they've ever had, and they're spending more time alone today than they ever had before. So people are looking for more types of connections, but social media isn't giving it to them. So what can we do about this? What tools do we have access to? Specifically, how can we use cryptography to help enable human connection? The first tool that we can use is cryptographic NFC cards. All of you are experiencing this right now. You all have these NFC badges as you entered the event. And NFC is really great for one useful primitive, which is verifiably digitizing physical interactions. I can prove to you that I actually met you in person by collecting a tap from your NFC card. There are roughly two different types of cards that we experiment that have cryptography on them. The first one is an ECDSA-based card, and the second one is a message authentication code, or MAC-based card. So we're using the second kind, which I'll explain more about later. But roughly speaking, these both use cryptography to secure physical interactions. At a high level, the ECDSA cards are signing cards that actually have an internal nonce, which increments upon every tap. And in addition to that, they actually custody signing keys within the chip. So whenever you get a signature, whenever you tap one of these ECDSA cards, it increments a nonce, and it signs that nonce and gives you back the tap. On the other hand, the MAC-based cards use a shared secret. So basically, the server has a secret that's shared with the card. And when the card generates this incrementing nonce tap, it just generates a MAC for it, and the server verifies this tap to ensure that the tap is valid. So why do we use one card versus another? Well, at a high level, these ECDSA cards have two really important properties. They're fully decentralized because the card actually custodies the keys. So interestingly enough, these cards actually just act as full wallets. They custody signing keys, they can sign arbitrary data, they can sign arbitrary transactions. And so they act as full wallets. But on the other hand, these cards are somewhat difficult to use. Namely, they're expensive, they cost a lot more than the MAC-based cards, and they're also much slower. And this is the main reason why we use these MAC-based cards, the NTAG 424s for ZK Summit. It's because the tap experience is way better, takes less than a second, versus these signing cards would take multiple seconds to generate a signature. And that's actually because these signing cards are generating a signature on the chip. It's a low-power environment, and hopefully that technology can improve in the future. Okay, so to summarize, NFC is a really great educational tool. It's really tactile and physical. When someone is introduced to NFC for the first time, something we hear a lot is, oh wow, this actually feels real. It feels like you're actually getting something when you tap an NFC chip. And that's how cryptography should feel. It's really engaging, and it automatically elicits human connection. When I tap you, I have to be in the same physical vicinity as you. I have to be right next to you. And so we're engaging in a physical ritual when I actually get this tap. But at the same time, NFC is not super expressive. It kind of can only express one thing, which is that we have this physical relationship. So we were looking for more ways to have programmable computation on top of this NFC data layer. And that's where we got to ZK proofs. And specifically, we use ZK for verifiable data and being able to prove things about your social graphs and about your own personal private data. So our tech stack is roughly this. We use baby jub signatures for NFC taps. That's what the chips give. They're ZK-friendly signatures. We use ZK email and TLS notary to be able to export Web2 data and be able to use it within our applications in a verifiable manner. Grot16 proofs for efficient client-side proving. And we use Nova and other folding schemes for folding multiple signatures together to be able to generate summary proofs of an entire event experience. So at a high level, these are some of the experimentations we've done in the past. At DevConnect, we did events gated upon taps. So you meet the event organizers, get taps from them to actually join their event. At ETH Denver, we had prizes based on generating ZK proofs of engagement, meeting certain people, or going to certain events. ZK Summit last year, we did a Spotify Wrapped-like experience where you could fold all your signatures that you generated throughout the event into one single folding proof that represented your whole event experience. And finally, at a recent residency, we experimented with ZK email and basically allowed you to import your calendar social graphs from your email, as well as verifiable events that you are going to attend in the future. And this allowed you to ask other people within your calendar social graph to see, hey, am I going to any events with you in common? Am I going to see you anywhere in the future? Okay, some quick reflections on ZK. It's useful for importing personal data. You can do it in a verifiable manner. But largely speaking, ZK is still limited within this social app use case. It doesn't allow full expressivity, and it's largely a single-player thing. I'm proving things about myself, about my own data, to other people. And it's great for these low-trust environments where I want to limit what I send to other people. And this is really interesting because comparing ZK versus other tools that we'll experience later on, ZK is centered around minimizing the amount of data that you share, versus something like MPC and FHE, as we'll see, really allows you to maximize the amount of data you share and look for more connection and share everything because it can be done in a safe and privacy-preserving way. So that leads us to our first multiplayer tool, which is private set intersection. All of you can experience this on the app. If you go meet someone, you can see what you have in common. And what this enables is for someone like Alice and Bob who've never met to actually see what similarities they might have. How this works is that Alice and Bob's interests are both encoded as interest vectors, and this PSI primitive allows us to find the indices where both of them share something in common. So in this case, Alice and Bob meet each other, they filled out their interest vectors, PSI allows them to discover that they both are Lana fans and also are going to Coachella to see her. This expands naturally to the multiplayer setting, where Alice, Bob, and Charlie want to discover times to meet. They want to find out when they can all interact with each other and hang out, and so they all share their calendars, but they do so in a privacy-preserving way. Here, PSI is used to find similar times where all three of them are all available. And this leads to more effective social coordination in general in the multiplayer setting. Now, some general thoughts on PSI. It allows you to use privacy in an offensive manner. So oftentimes we think about cryptography as defensive tools used to secure your data, keep something private, prevent you from getting hacked. In this case, it's offensive. It actually allows you to share more because you can do so in a safe way and therefore discover more meaningful social connection. In addition, it's pretty easy to understand and explain. PSI is largely centered around, hey, like, let's just find out what we have in common. It's a very simple thing that people do anyways. But ultimately, at the end of the day, PSI is still largely a limited primitive. It is just one interaction that you can do. It's only, hey, like, let's see what we have in common. And what we realized when we were building it is we wanted to look for more expressive forms of computation, more things that allowed you to do comparisons or averages, and Vivek is going to talk to you more about primitives like that.
Yeah, so this naturally brings us to more general multi-party computation, and the specific scheme that we've spent a lot of time and resources in is multi-party FHE. And the reason for this is that we're mostly building in consumer settings where liveness and compute are both kind of like bottlenecks. Liveness here represents the number of back and forth rounds between two parties. Because people put their phones away, that basically stops the computation from happening if it takes multiple rounds. So multi-party FHE has really favorable kind of rounds compared to stuff like secret sharing and garbled circuits. And the other nice thing is that it kind of offloads computation to a server. There's two main modes that we've worked with multi-party FHE in. The first is interactive. And so basically there's an initial MPC to set up a collective public key amongst a group of folks. So this collective public key is generated such that no individual party knows its corresponding private key. And so everyone can basically feel safe to encrypt their data to this collective key. At that point, you can send all of your data to a server, and the server can do different operations. In this case, it's just a multiply, and get some output, all encrypted to this collective public key. And then finally, there's a second MPC process to decrypt this data. And so, again, this is really nice because you basically can offload all this compute to the server, but there are a lot of rounds initially and in the second phase. So as Andrew mentioned, PSI is available in this app, and actually it is built using multi-party FHE because it happens to be very efficient. And one thing you might notice when trying it is that we actually require both of you to opt in at the same time, so it's kind of a synchronous process. And the reason for this is that there's probably like 7 back and forth rounds, and it's really difficult to build a good UX unless you require both parties to just kind of sit there and let the whole compute finish. And we've tried in the past where sort of it's more asynchronous, but then yeah, if someone puts their phone away, then basically the whole computation is blocked, and it can just take a long time for any sort of like results to populate. One thing we'll highlight actually with the PSI is you can also in the app put in cryptographic hot takes. You can get overlap on that, and you can sort of safely share those things. Update from these ZK11 mocks. The second mode we've started to work with is something called non-interactive multi-party FHE, which I think is not quite a thing in the literature. It's something that was pioneered by this group called Gauss Labs that we work closely with. And it basically gets rid of this initial MPC, where instead the server generates a shared key and key switches different parties' data to the shared key itself. And so this is nice because it skips this initial MPC, but also each party only needs to encrypt their data once. They just encrypt it with their own public key, and then the server can handle basically this key switching operation to bring it to the shared key. The rest of the process continues as normal. The server does some compute. There's a collective decryption process, but you do save a bunch of rounds here. So we actually built this at a recent conference called Frontiers in San Francisco, and the setup there was essentially private job matching. So a candidate and a recruiter could post basically a job profile and a job description privately. And every time you sort of met someone, we basically run this computation in the background to see if there was overlap in your kind of the sort of encrypted data you uploaded. And we found this interesting because as a candidate, often you want to be looking for better opportunities, or at least search what's out there, while you're still employed at a specific place. And it's really difficult to do this in like a public fashion because you don't want to mess up any relationships with existing employers. And so this setup basically enabled this sort of stuff to happen only if there actually was an overlap. You don't need to reveal that, hey, I'm looking for a new thing. It'll only surface if like the candidate's interests and salary requirements actually fit what the recruiter has in mind. So you can imagine the candidate putting like some super high salary requirement just to see what's out there. And this actually reduced the number of rounds significantly, but there's still 4 rounds of communication, which means there's still kind of this weird back and forth where if Alice puts her phone away, then Bob is kind of like blocked from receiving any results. But overall, this is a significant improvement upon a lot of other MPC schemes, especially in a consumer setting. And again, it's really nice because the server can handle all this compute as well. And so like the user on their compute limited device only has to handle generating a public key and doing encryption and decryption. One huge downside of FHE schemes in general is, especially in the multi-party setting it seems like, is the uploaded public keys are huge. So to get like 128 bits of security, you usually require like keys in like the tens to hundreds of megabytes. And if you're kind of trying to set this up in like an app experience, this is a huge load for someone to upload, even on good Wi-Fi, but especially on like something like a conference Wi-Fi or like on data. And there's also a huge blow up in the data you're encrypting as well, because you're adding all this noise and other stuff to make it fully homomorphic. So that brings us to Trinity, which is a scheme that we've researched in-house that we think answers a lot of these different requirements. In particular, there's kind of one round necessary of computation with one kind of initial preprocessing phase that can be used for many different MPCs. And it also comes with verifiability out of the box. The inputs that are going into this multi-party computation, you can basically verify that they correspond to other data. It's called Trinity because it's a combination of 3 different powerful cryptographic schemes. The first is garbled circuits, basically the same one from Yao in the 80s. KZG witness encryption, which is a relatively new result from 2024, and good old Plonk. Actually, any sort of ZK snark that uses KZG works, but we've chosen to use Plonk because it has great tooling and great performance. I'm going to go through each of these quickly. I'll keep it pretty high level. But for garbled circuits, this is essentially a general purpose 2-party computation tool. You can make it multi-party, but it really shines in the 2-party setting. And the problem, or the reason we haven't used it before, is like this oblivious transfer section here classically requires like usually 3 rounds. There's ways of like kind of lowering that to 2 rounds with some other techniques, but in general, there's basically a bunch of back and forth that needs to happen. And so again, it makes it really difficult to use vanilla garbled circuits in consumer settings. KZG witness encryption comes to the rescue here. The high-level API of KZG witness encryption is basically you have a normal vector commitment, you have different indices from 1 to n, or like roots of unity, and you're committing to some dictionary. And what you can do is you can essentially encrypt to this KZG commitment at a specific opening. So if this KZG commitment at point like index I opens to d of I, then the sort of like committer can decrypt a specific encryption you make. But if that opening proof doesn't exist, then you can't decrypt. So it's basically like you can sort of basically do these sort of like committing to a vector. And it's all very efficient, just requires like a few pairings and some EC-mols. And the main application that the authors of this paper built it for is something called laconic oblivious transfer. And so this is also kind of very detailed, but the rough idea here is that you can essentially batch a number of OTs into one round of preprocessing, which only shares a like constant size KZG commitment. And then you can use that constant size KZG commitment across many different oblivious transfers. And so if you kind of include this oblivious transfer data alongside your garbling, you just have 1 round total of computation, which is really, really nice for consumer settings. Finally, Plonk comes in because this KZG commitment, you can essentially attach a succinct proof of validity. In the settings we're operating in, this KZG commitment corresponds to the various parties' like inputs into a garbled circuit. And by default, there's no verifiability on this. It's kind of like you're trusting the parties to put in the right data. But you can essentially, for very cheap, attach a proof, like a Plonk proof, where your KZG commitment at a high level can just be this first column. And you can attach a bunch of other data like ZK email, ZK TLS data to prove that your commitment is valid. And this is all very efficient and very succinct. And so altogether, basically Trinity enables this sort of like 1 round of data transfer to do a 2PC. which again, in consumer settings is like super useful because people put their phones away basically. And in addition, you also get validity proofs of your data for very cheap and also very small proofs, like small enough where you can feasibly put them on a blockchain. The upshots of this are that Trinity, actually, we're still working on implementing Trinity, should be up in a few weeks at Edge City and DevCon, so these are more kind of what we're looking forward to versus reflections. But we think Trinity will enable really simple developer experience and user experience for building and using consumer GPC. Because yeah, when you don't have to think about all these rounds of computation, that's actually a huge load taken off of both the developer side and also on the user basically interacting with this app. Next, the cool thing is because we're building off Plonk and in general any KZG-based ZK snark, you can actually build off other ZK-proven data that users have posted, whether it be in blockchains or in other settings. Trinity can plug into this very naturally, which is really, really neat, especially in a world where hopefully people are generating more and more proofs about themselves. And maybe the overall sort of like mental model to think about with Trinity is that you essentially, for Alice and Bob, Alice can send Bob this encrypted email with basically a set of criteria and some sort of hidden information. And Bob will only ever get to see the hidden information if he actually matches this criteria. And so it's kind of this combination of like witness encryption and multi-party computation. And it just enables, we think, a bunch of new kind of affordances that we will go through now. Because we think we finally sort of, through these explorations, gotten to some really exciting views of what future coordination communication could look like between different humans. The first one is this idea of unbreakable consent. And this actually is kind of flipping what's often thought of as a flaw of MPC, which is that parties can exit a protocol early, which basically means that for everyone else involved, they might not get the result of the computation, they might not get to decrypt in the case of like FHE-based multi-party stuff. But at least when you consider the 2PC query response setting, this actually is like a real feature in that for Alice to learn anything about Bob, Bob needs to sort of participate or consent to participating in this kind of decryption process for any information to be revealed. And so it's kind of like mathematically required that both parties or all the parties involved consent to what is going on before anything is revealed. And this is a very, very different model from existing situations where we just kind of hope servers do right by our data, which oftentimes, they're training their own models, they're selling it to whoever, they're selling it to other people to train models. So this is an exciting new sort of way of existing digitally. The next is this idea of digital pheromones. So for anyone who's unfamiliar, a pheromone is a chemical substance produced by an animal to signal to other individuals to engage in some kind of behavior, other individuals in the same species. And one way we've been thinking about these sort of Trinity KZG commitments, which again are sort of commitments of different people's like input data, is that there's these very lightweight, they're like constant size and also like undetectable in that there's, computationally hiding signals that we can start putting out into the world. And then using this sort of like encrypted email kind of like querying, we can just sort of freely discover synergy in a way that is like safe, consent is like deeply baked into, and potentially just like discover a lot more sort of serendipitous synergy between people in a way that the sort of current model of social media with like public billboards really just does not facilitate very well. Finally, this idea of narrowcasting. So narrowcast is the opposite of broadcasting, and this kind of really builds off this sort of like encrypted email idea, where instead of just being dependent on like public feeds or group chats, you can sort of just narrowcast information to the people that it would be most relevant to, where you can be sure that only if they match the criteria that you've set for this data could they actually see it and interact with it. And we also think this will enable lots of interesting ways of connecting and coordinating with people that aren't easily available right now. So where can you experience this technology? All of you can experience it right now. The app that all of you have, built off the NFC cards in your badge, have a bunch of these experiments. And we want to reiterate, there's some fun prizes for people on the leaderboard. And right now, the first 5 people who get to, I think, 33 was the number we decided, get to take home some NFC rings as well, which will be sort of early access to different experiences we're building. So at ZK Summit, we've basically kind of just like thrown a bunch of fun cryptography apps into one experience. But for Edge City, DevCon, and onwards, we're building a more cohesive single app called Cursive Connections, where you can sort of take your social graph from many different events, import data from many different places, and essentially discover new connections, learn more about different people in your community, get recommended events, and sort of a kind of holistic platform for a lot of these different ideas we're exploring. If you're at either of these events, please come see us or come find us. We would love to get you a chip, get you started on this, and yeah, happy for any and all feedback. Finally, we're very lucky to be hosting a really large booth at DevCon, right near the entrance of the venue, and it's going to be modeled as a museum exhibition focused on cryptographic connections. So this is both like past uses of cryptography for connection, like ciphers, encryption, even like Ethereum, demos from some of the sort of cutting edge projects in the space, as well as a bunch of different art exhibitions on just, for different artist friends of ours, like how they interpret cryptography, connection, and this sort of thing. And we are actively trying to find collaborators to do demos, to make art pieces, so please reach out to us if this is something that interests you or your company. We would love to collaborate and make this cool. A little bit about Cursive. We're a research and design lab focused kind of exclusively on these directions. And yeah, this is a place that's very near and dear to our hearts, and everything we've described here has been the result of many, many collaborations, and we want to continue that going forward. So yeah, if this is a research or product area that is of interest to you or to your group, we would love to try to figure out ways to work together, get this tech into the hands of more people. And finally, we owe a big thank you to Privacy and Scale Aspirations. Cursive is grant funded from PSC, which is a sub-team of the Ethereum Foundation. The grant support is amazing. It's allowed us to do very free exploration, but the network of collaborators and sort of positive sum public goods work we've been able to put out while being supported by PSC has been nothing short of miraculous. So huge shout out to them, and yeah, these are places to follow our work going forward. Thank you.
Thank you very much. Do we have any questions? Otherwise, I guess we're at time. Oh, here we go. Let's give you 1 second.
Thank you. Really interesting talk. I'm just curious, what is a like a ZK consumer product that you would like to see in the world that maybe you in particular don't want to make but think should exist?
That's a great question. Do you have a good answer? Do you have a good answer to this?
ZK consumer product. I prefer MPC consumer products.
I think, well, this is more of a shout out. Like, I think some of the stuff that the folks at ZK P2P are doing is really interesting. I think that's really focusing on the verifiability aspect of ZK, which I think is a lot of sort of room to, or like a lot of value to get from that. Yeah, basically enabling sort of more verifiability on data exchange and that sort of thing. Also, especially around high sensitivity data, like financial data, passport data, that sort of thing. I would love to see more ZK on. And yeah, I think in many ways we have chosen not to focus on ZK because a lot of the stuff we're working with is more social and personal in nature, and we think doesn't benefit as much from ZKPs as some of this other stuff. But yeah, we think there's a lot of cool stuff to explore.
I think last question and then lunchtime.
Great talk. Was wondering if Trinity can in any way counter like the raiding attacks that you have with PSI. Like you just create a lot of sham accounts and try and see how you intersect with someone like with triangulation.
Yeah, that's a great use case of this sort of verifiability, and it's a big sort of bug of the current PSI. Actually, one thing I'd like to shout out is a project called Greco, built by Timofey, is now working on new iterations of it, off of work from Enrico and Janmajaya. That's one that is basically doing a similar thing where it's proving that data has been encrypted correctly as inputs into a PSI, into an MPC. So yeah, ZK is a super important tool in like all of these crypto systems in basically ensuring that the integrity of this stuff is strong, because you can basically just do more meaningful computations that way. But yeah, that's a great use case.
Number 2, thanks. Let's thank our speakers once again. Thank you very much. And we now break for lunch. I believe lunch is served upstairs. Remember that there's also a bunch of merch that you can take. We've been getting messages that it's all for grabs. And we'll be back at 2, I believe.
YouTube Premium é YouTube sem anúncios e reprodução em segundo plano para ver vídeos enquanto lê, pesquisa, compra, experimenta o mês sem custos.
Muda as coisas com a Wallapop. Livras-te os livros que nunca mais vais ler e ganhas dinheiro. Começa a vender.
Hello. Okay, everyone, we're going to get started with our talk after lunch. We have Stefanos here from
Imperial College and Ziggy Security. So today I'm going to present a joint work with Itamar, Adria, Jens, Akis, and Ben on analyzing and benchmarking Ziggy rollups. So I will start with a brief introduction on what is blockchain scalability, what are rollups, and what are Ziggy rollups, and then I will describe what we did, our analysis, some preliminary benchmark results for Zk Sync Era and Polygon Zk VM, and also then I will discuss a bit the implications, in particular for transaction fee mechanism design for Zk rollups. So blockchain scalability is often framed in the context of the blockchain trilemma, which is basically, which highlights that we can't have simultaneously scalability, decentralization, and security. And blockchains such as Bitcoin and Ethereum have historically focused on decentralization and security, whereas someone might claim that some of the modern blockchains can achieve all three of them, but that's a different topic. So if we want to scale something like Ethereum, what we can do is we can use rollups. And rollups are L2 solutions, scalability solutions, that basically move the execution of chain. They execute transactions, update the states of chain, and then they submit some data, and we will see what data on chain, and do some verification of that execution on the main chain, which is what we call on chain. And in particular, Ethereum, in the last couple of years, it has a very roll-up-centric roadmap. There have been improvements that are mainly focused for improving the efficiency of rollups. The most important example is proto-dunk sharding, APE 4844, which basically introduced blobs that makes DA much cheaper in Ethereum. So how a rollup works is that we have a completely different blockchain, which we call the rollup, or L2, or off-chain computation. And in that rollup, we get transactions. We mine the transactions into a block or validate them into a block. And then we batch together multiple blocks that we will then submit the data for that batch on the L1. And later, we will actually verify the correct execution of the transactions for the batch. And we have two main types of rollups: optimistic rollups, which basically they secure their transactions with fraud-proof in an optimistic way. So they assume that all transactions are valid by default and only run some computation, a fraud-proof basically mechanism in the event that some observers says that some of the execution was not correct. And they have to submit all the data, and typically they have a quite long finality period because you have to give, at the moment it's 1 week for observers to make sure that have checked all, the bots and to basically finalize completely the transactions of the bots. The other option are ZK rollups, which are basically using succinct proofs of valid execution that can be verified on-chain without re-executing them. Verifying a validity proof submitted on the old chain has become much cheaper the last couple of years. We have more options on compressing the data we need to publish all the L1, and also time to finality. It could take some minutes or at most some hours nowadays. So now I will give a more thorough overview of how explicitly ZK rollup works. So we have L2 users that interact with our L2 blockchain, the ZK rollup in that case, and they submit transactions to the sequencer. At that point, their transactions are pending. Then the sequencer creates some blocks and batch together all the transactions into a single batch. And the size of a batch could be from some dozens of transactions up to some thousands of transactions. And at that point, we say that our transactions are pre-confirmed, have been executed in the L2, and then we commit to that batch in the L1. So we create an L1 transaction that publishes the data of that batch, the data of all the transactions of that batch in the L1. And at that stage, we say that our transaction is committed. In the meantime, the L2 will send the batch to a prover, and the prover will actually create a succinct proof for the batch. And when that succinct proof is created, we will submit that proof to an L1 smart contract that will actually run the verifier and verify the correct execution of the transactions. And at that point, we can say that our transactions have been finalized and we are safe to proceed. So we had a few research questions for ZK rollups in particularly, and we wanted to investigate what are the fixed costs. And fixed costs are the cost of a batch independently of the transactions that have been included in the batch. Marginal cost has to do specifically with transactions. And then we have, we want to explore the trade-offs between fast finality and cost minimization. We will present a complete breakdown of the different costs for ZK Sync Era and Polygon with some custom, pretty naive payloads. And finally, we will discuss a bit the impact of blobs. So here are some of the ZK rollups that have been implemented. We have Polygon Scroll and ZK Sync Era, which basically use a ZK EVM as their VM, and they try to be either EVM compatible or Solidity compatible. And then we have some other options, for example, Starknet. We have Aztec, which is more like a privacy-oriented rollup. So we chose to go with Polygon and ZK Sync Era because we wanted to focus in scalability solutions. We wanted to focus in systems that are in production. And we also wanted to have solidity compatibility to be able to compare kind of apples to apples, although that's not completely true, as we will see. And those were the only two solutions that, at that point, at least, were fully open sourced. So some notes here is that both use two-proof systems, one for the initial proving, and then they want to convert a larger proof, a Stark proof typically, to a smaller, more succinct proof that will submit to the L1. And another main difference is that Polygon submits transaction data in the L1, published transaction data, whereas ZK Sync Era uses state diffs. And finally, Polygon uses a large CPU-based machine, at least at that point. And ZK Sync Era has a more complicated hardware specification where basically they use many GPU-based, kind of smaller machines. So here is another way to see the landscape and basically the compilation process. And as I said, we want to start from the solidity part to be able to compare similar payloads. So what are the costs? First, we have fixed cost, which is composed by settlement and proof compression. By settlement, we mean two things. First is the transaction to commit to a specific batch on the L1, and that includes all the gas cost, but not the DA cost for that batch. And secondly is submitting the proof and executing the verification logic in an L1 contract. And secondly, another fixed cost is the proof compression of proof transformation, which is going from a Stark proof to a Snark proof. That's also fixed independently of the size or the type of transactions in the batch. And for marginal cost, we have DA, which is how much does it cost to publish some data on the L1. We have the proving cost, which is how much does it cost to prove some transactions. And we also have some other L2 costs that, for that work, we will say are negligible. So here is our methodology. So we start with some payloads, and we opt for some very naive and simple payloads because we wanted to have full control. We wanted to be able to run our methodology for both rollups. Ideally, you would like to experiment a bit with get some historical blocks from Ethereum and run them through both, but that's a bit more complicated. It's something we want to do in the future. And then we have our metrics. So when we run the payloads through the rollups, we get a batch. And then in the batch, we extract the DA we will need to publish in the L1. We also extract the settlement cost, the L1 gas we will have to pay for both committing and verifying the proof. And then we have the prover. So for the prover, what we decided to do is to keep track of seconds per proof and also USD per proof and USD per proving a transaction. And I will present some results later on. And finally, the configuration for both machines is this one. Here I should note that both prices are a bit, not a bit, like 2 or 3, maybe even 5 times more than what Polygon and ZK Sync Era and Mater Labs are paying because they have better deals with Google and AWS. We just got a machine for a month, and that was it. So you can bring those costs even lower. So here we break down the fixed costs. And I want to start with describing the first major change between the two approaches. ZK Sync has really huge batches, whereas Polygon works in smaller batches that then actually aggregates multiple bats into a single proof, and it works in that way. So we can see that zk-sync batches are in terms of some thousands, whereas Polygon are some dozens of transactions. The theoretical match batch size was at that point, maybe it has been improved, and it's also simple ETH transfers. So if you want to do more complicated transactions, then that it's much smaller. Then we have all the fixed costs, and the numbers here are pretty comparable. We can see, again, the difference in Polygon's case that you have multiple batches included in a single operation. For example, typically they submit 5 batches when they perform 1 commit transaction, etc. And what we wanted to focus here is the normalized cost per transaction. And we can see that it's pretty low. And as we will see later on, fixed costs are the main cost for ZK rollup transactions at the moment. And we will analyze a bit more how that might change if DA becomes more expensive, if proving becomes cheaper, etc. And also we had the normalized cost in the theoretical case where you have as many transactions as possible. And we can see that the number is pretty low for both rollups. So here we have the first results for the marginal costs, and we have how many bytes we require per each of those payloads in terms for DA. Our payloads are super biased towards state diffs, and that's because, for example, if we have many transactions, that means that if we have many transactions, all those transactions will kind of touch similar state. So it's the perfect situation for state diffs. And I want to highlight that result because we will see later how that might affect how you want to actually sequence transactions. But we can see that in extreme cases, you can achieve pretty good compression, I will say, by using state diffs. Next, here are some marginal cost results for Polygon's ZKVM. And we can see on the left figure the proving plus compression time and how it evolves when we have bigger inputs. This is, I think, for transfers or ERC20 transfers. I don't remember. And we have the time it requires to do the proving. And that's important because basically our finality time is bounded to our proving time. And on the right side, we can see the cost per transaction. And we have 2 lines. The first line is when we use cold data as our DA, so that's why it's more expensive. And the second line is when we use blobs. So we can see that, especially for blobs, if you manage to fill a batch, then it doesn't make sense to wait more time and to detriment your finality. But it's another trade-off, and there could be different options on how to handle that on the ZK rollup side. Here is the total costs of Polygon's ZK VMs. And so, first of all, DA at the moment it's virtually free for rollups in general. So all those results should be taken with a bit of salt because that might change in the future if changes happen or if there is more usage of blobs and more demand and prices go up. And that's why we also captured what will have been the cost if they used cold data with prices before the introduction of proto-dunk sharding. Which you can see when we have a larger size of bats, then DA it's our main cost in case of using cold data. Here we have basically our main fixed cost. We can see that proof compression is pretty cheap already, and I think both teams have done an order of magnitude improvement in their proof compression. And we can see on the left side is the percentage of commit cost when we use blobs as DA, and on the right side is when we used cold data. And we can see that the fixed cost actually decreases as we increase the size, and that's because the fixed cost per transaction, it's lower because we have larger batches. And also we can see that proving starts to become relevant only if we try to actually minimize our costs, which is the case when we try to have huge batches, and only in that case it starts to be a bit relevant in the cases where DA it's not expensive at all, it's virtually free. And also here is the cost per transaction, and we can see that as we increase the batch size, then the cost per transaction decreases, but that comes at the cost of longer finality times, which might be important for some users, might not be important for some other users. So what are some main trade-offs? We have the some main takeaways, sorry. We have the trade-off between fast finality and cost efficiency. And that's especially important when you don't have high volumes of transactions, and maybe you want to delay a bit, so you provide cheaper prices to your users, or you might have to have different mechanisms there. So some people might opt for fast finality, and some others are okay with waiting a bit to be included in the next batch. Then we have state diffs efficiency, and here we show the extreme case of how much better state diffs could be. What I want to mention here is pretty close to the next point, importance of sequencing. So for state diffs, normally in L1 I would say which transactions are going to be in the next block. It's more about MEV. In rollups at the moment we don't have MEV. But even if we had, it's a nice question, especially if DA is your main cost, to try to put in the next block, in the next batch basically, transactions that will maximize your state diff's impact. And similarly, what we noticed is that we have a similar case for provers. So for example, in Polygon's case, if you have a transaction that does a single KESAC hash, you will have to pay the cost for proving KESAC hashes. So what you want to do to amortize that cost is to include as many transactions to fill that KESAC space in the prover to minimize your proving cost per each of those transactions. And finally, we also saw that basically the impact of APE 4844, what's great for ZK rollups. There is a lot of discussion if that should change, if that should not change. But we guess that some strategies, it will be nice to be developed in case that blobs start becoming more expensive. Then you might want to move temporarily to cold data, or if you don't have many transactions and many data to post for your batches, but you want to have fast finality, you might want to try to share blob space with other rollups, if that's possible, etc. So some open research questions we have identified is basically what is the impact of this decentralization on the cost? What happens if we start having more costs in the L2? Now we said those costs are negligible, but that might change. What are some strategies for batch size and sequencing optimizations, and how you can basically take the best out of your prover and out of the state diffs, or what other else compression you're applying? We also want to do some metering mechanism evaluation, because in some cases the proving cost may not completely captured by the existing metering mechanism. And also we want to try to develop a proving market mechanism, specifically for ZK rollups that take into consideration all the results of this work. So that's it. You can find our paper in that QR code, and we also have published all the scripts, all the results in the GitHub repo that you can find through the paper. Thank you.
Are there any questions? Everybody understood everything? That's impressive. All right, thank you again. Cheers. Just quickly, we just wanted to announce quickly, if you guys want to join the ZK Summit after party happening tonight, the link has been shared in the ZK Podcast main Telegram group, and we'll put up the QR code during the break. So up next, we have Ilan from Bar Ilan University discussing hash-based multilinear polynomial commitment schemes. Wow. Maybe we just give it a minute so we give people the shuffle in, shuffle out. Yeah.
The title has slightly changed.
If you want to give it. Okay, everyone, welcome. Next up, we have Ilan from Bar Ilan University. Take it away.
Okay, thank you. Hi. So first, this is joint work with my student Galo Renon and Alessandro Chiesa and Giacomo Fenzi. And I'm kind of very excited to be here, and this is a kind of present WIR. This is the premiere presentation of WIR. Last ZK Summit, we presented the STIR, and this is kind of a new improvement on top of that. So WIR is a Reed-Solomon proximity test, and it has superfast verification. And so I'm going to go slightly into technical details about that. And we're also going to see benchmarks. And yeah, so let's start. So first, we're in the ZK Summit conference, and what are our goals? We want to construct snarks. Okay, these are succinct, non-interactive arguments of knowledge. So we have a prover, we have a verifier. The prover wants to convince the verifier that he knows the solution, right? He knows a witness to this instance. And in our case, the prover and verifier are going to share something called a random oracle, as Anna discussed this morning. So they both have access to this random oracle, which they can query and get back a completely random answer. And we want the proof, of course, to be kind of very small, okay? In particular, much, much smaller than the size of the witness itself. Okay, so we're gonna only have a random oracle. There's no other assumptions, okay, assumed in this talk. Once you have such a scheme, you can replace the random oracle with some concrete hash function. Okay, so you instantiate the random oracle with a hash function, and what you get is a snark that you can deploy in practice. And the advantages of such snarks are that they have a transparent setup. Okay, so the only setup that they require is choosing this hash function. They usually are quite highly efficient. So there's no public key crypto, there's no elliptic curves and stuff like that. There's only hash functions, and usually over small fields and stuff. And so they're quite highly, they're fast. And they're also post-quantum secure, if you care about that. Of course, today, these snarks are used to secure billions of dollars in blockchain transactions. I guess you know about this. This is just a small subset of the companies using this stuff today. Okay, so how do we construct hash-based snarks? What we do the following. We first construct an IOP. An IOP is an interactive proof between a prover and a verifier, where the verifier does this small number of queries to the proof. These are the green locations here. Then you take this proof and you compile it using something called the BCS transformation. Okay? Roughly speaking, every message of the IOP, you're going to Merkle tree. Okay? You're going to create a Merkle tree and commit to it. And then when the verifier wants to read something, you're going to send the authentication path. And all of these long rounds of interaction, you're going to use fiat shamir to compress to one message. Okay? And the efficiency of the snark is mainly determined by the efficiency of the IOP. So the prover is roughly the same. The verifier is roughly the same with additional hashes. And if you have some proof lengths of length L and Q queries, okay, usually the proof length is kind of big. This is the size of your computation, let's say 2 to the 24, and you have some number of queries. This is going to affect the argument size at the end and the verifier running time and so on. Okay, so we want to construct more and more efficient IOPs, okay, for the relation you want to prove for R1CS or something like that. How do we construct these IOPs? And this is the last slide before we go to WIR. What you do, you construct these polynomial IOPs. Okay? So a polynomial IOP is just an IOP where we restrict the honest and malicious prover to send only polynomials. Okay, so they have to send polynomials, and the verifier, what he can do, he can query these polynomials, and can evaluate them at any field element that he wants. Okay, so the prover is going to send some polynomial Q, and then the verifier can query this Q at some point X, and then you have maybe some polynomial P and Q and so on. And once we have this polynomial IOP, what we do, we compile it to a standard IOP. okay? That is then later going to go to the BCS transformation. And how do we compile these polynomial IOPs? What we do, we either use a polynomial commitment scheme, which is just a cryptographic way of enforcing the prover to really commit to a polynomial. But actually, more generally, I just want to take this slightly higher view as any compiler that takes a polynomial IOP and outputs an IOP. Okay, so one way to do it is using a polynomial commitment scheme and then doing this function by function, but any such compiler is what we want. And any such compiler is in particular actually a polynomial commitment scheme. Okay. We have many examples. Many of the snarks we know today use this blueprint to construct snarks, and there's many examples. I'm not going to name all of them. The polynomial commitment scheme that you use underneath could be KZG or something based on lattices or something like that. Or it could be something based on hash functions, so a hashed-based polynomial commitment scheme. And this is going to be the focus today. And I'm just giving a few examples. This could be Fry-based, or Stir-based, or Basefold-based. And these are the 3 examples I give because we're going to mainly compare to them because they're the most relevant to this work. OK. So the way these hash-based polynomial commitment scheme work, we ask the prover to kind of, instead of sending a polynomial, evaluate it at many points. And then we kind of need to test what the prover do. So this leads us to a result. So in this work, we introduce a new polynomial commitment scheme that has a really super fast verification. Okay. So more technically, what we do, I need to define what the Reed-Solomon code is. So we recall what the Reed-Solomon code, we had some finite field F, okay? We have some evaluation domain L, and we have some parameter M. M is going to be the degree. And then we're looking at the Reed-Solomon code, so these are all functions F from this domain L to the field, okay? So all evaluations of functions, such that the function is univariate, low-degree polynomial of degree at most 2 to the m. Okay, so m is going to be log the degree in this example. So this is the Reed-Solomon code. And equivalently in this work, we kind of have this dual view of the Reed-Solomon code, where you can look at it as a univariate polynomial or a multilinear polynomial. So you can take the 2 to the m coefficients, and you can view them as coefficients to a univariate polynomial, okay, of the degree 2 to the m, or a multilinear polynomial, okay, that has m variables. Okay, so we have this duality between the two. Either we have m variables, or just one variable with degree 2 to the m. Okay, so what we do, we're gonna define a constrained Reed-Solomon code. Okay, and this is gonna be very helpful for us. And this will allow me to tell you exactly what WIR is. So a constrained Reed-Solomon code is just a subset of the code words of Reed-Solomon that has this additional sum constraint. So there's some checkline-like constraint that you add upon it. So my code now is not on all code words, okay, but just a subset that satisfies some additional constraints. So this W is going to be some polynomial, and sigma is some target sum. And then I'm looking at all the polynomials in the multilinear notation that satisfy this additional sum. And this additional sum in particular is expressive enough to express a constraint of an evaluation of this polynomial f. So I have f, and I want to say, oh, but f on some point z equals sigma. And there is a way to translate this to such a constraint. Okay? And this is what allows us to use WIR as a polynomial commitment scheme. Okay. So what is WIR? WIR is an IOPP, an IOP of proximity, for constrained Reed-Solomon codes. Okay? Where Fry, if you know Fry is an IOPP for Reed-Solomon code, and Stir is also an IOPP for Reed-Solomon code. WIR is going to be an IOPP for this constrained Reed-Solomon code. okay? Or in other words, in words of higher marketing words, it's a polynomial commitment scheme for either univariate or multilinear polynomials, okay? So it works for both. So for degree 2 to the m, okay, in the univariate case, or m variables with some security lambda and folding parameter 2 to the k, this folding parameter is some parameter, some trade-off that we can play with. It means that, like in the Phi protocol, in every query, you kind of read 2 to the k field elements, okay? The query complexity of WIR is this expression. This is lambda over k times log m, okay? And forget about this complicated expression. We'll see it in a second, and we'll have benchmarks also soon. We kind of set k to be roughly log m, and then what you get is the query complexity is actually O of lambda, which is actually optimal. The verifier running time is this query complexity. Well, the verifier needs to do something per query, right? Times 2 to the k plus m. So again, 2 to the k is going to be the bigger term here. And for every query, the verifier reads 2 to the k field elements. This means that in terms of field operation, the verifier is actually linear in the number of field operation it reads from the proof, okay? This is what makes the verifier very fast. And not only that, actually the verifier performs 0 divisions, okay? So not divide by 0, but it doesn't perform any divisions. Okay, the alphabet is what I said. You read 2 to the k kind of field elements in every query. This is the rounded complexity. It's m over k, and the proof length is linear. Okay, so what does this mean? How does this compare to prior work? And what does it mean with actual numbers? Okay, so first let's compare the query complexity to some prior work. So basefold is a multilinear polynomial commitment scheme. The query complexity is lambda times m. Phi, if you know the Phi protocol, has query complexity lambda over k times m. So basefold just doesn't have this folding parameter built in, so it's kind of fixed to 1. Stir is a polynomial commitment scheme that we introduced last ZK Summit that kind of improves the Phi, so you can see the improvement here. So the query complexity is lambda over k times log m instead of times m. So it gains a huge factor there. And WIR just borrows the same query complexity as stir. Okay, so it has like the small query complexity. Now, in terms of the running time, basefold is actually linear in the number of queries, so it's O of Q basefold. Okay, that's good, but it kind of has a lot of queries. Fry does this, has a running time, okay, this is the verifier running time, of O of Q Fry times k times 2 to the k. This makes a lot of sense because Fry needs to do like this small FFT of size 2 to the k for every query that it reads. And so this k 2 to the k is just the time of an FFT of size 2 to the k. Okay? Stir has this slightly even worse running time, okay, has this plus lambda square, okay, which sometimes is actually, could be quite big. And the running time of our verifier is actually Q WIR, which is the smallest query complexity, times 2 to the k plus m. Okay, so we even shave out this factor k. Okay, now it's really linear in the number of queries and not quasi-linear. Okay, an extension field of the Goldilocks field. I really want to thank Remco for helping us, Remco from WorldCoin for helping us with like optimization of the prover and verifier. What the benchmark you're going to see today are like partially parallelized, so there's a lot of room for improvement for the prover running time if you have a lot of CPUs. And we compared it with Fry and Stir and Basefold as a polynomial commitment scheme. So let me tell you about the results. So let's start. So the WIR verifier typically runs in a few hundred microseconds, okay? Other verifiers, even those that have a trusted setup, KZG and other, usually take several milliseconds, if not more, okay? And we do this without like compromising or without some bad trade-off between the running time of the prover and the argument size. Okay, so it's like a true improvement and not a trade-off. As an example, okay, as a polynomial commitment scheme for degree 2 to the 22. You can think of this as like roughly equivalent to 4 million constraints. With 100 bits of security, I ran this last week on my laptop. I have a MacBook Air. The prover time took roughly 1 second. The commit and open together were roughly 60 kilobytes, okay? And the verifier time to verify this opening was 207 microseconds, so roughly 1/5 of a millisecond. Okay, so this extremely fast verification, sorry, here's a slightly more comparison with other schemes. So we have KZG here, and Ligero, and Breakdown, and Hyrax, and you can see the numbers. So usually these numbers are either large or a few milliseconds, where WIR is the only one, depending on parameters, kind of go below the millisecond barrier. Okay, once you have such a fast verifier, you can kind of think of new applications that open or improve. So I just want to really, sketch two things that I think are interesting. So first is on-chain verification. And all of these are kind of, this is the back of envelope computations that we did. And, to get exact numbers, you have to really implement this and see exactly how much you get. But today, we verify Groth16 proofs, okay, on-chain over the BN254 curve. And this takes roughly 280K gas, okay? Possibly, one future is where we use WIR to verify this stuff over smaller fields. And kind of some estimates that we did said if you take a degree 2 to the 22, you're going to get roughly 50K gas, okay? And even if you go up to degree 2 to the 60, 2 to the 26, this should be 80K gas. Okay, so this could be a big improvement in the gas cost of verifying proofs. Okay. Second, of course, is the recursive verification. So if you use WIR as the first step, in a recursion, in the second step, the prover is going to run and prove the code of the verifier. And here we did another set of computations. So here we went for 128 bits of security with degree 2 to the 28, so kind of a large computation. Then because the query complexity of WIR is small and the verifier is fast, kind of what the WIR verifier is going to do is roughly 3.4K hashes, okay? This is to verify the Merkle tree hashes. And if you kind of assume that this hash is Poseidon, or most of it is Poseidon, which is roughly 400 R1CS constraints, then you're going to get that the recursive circuit, okay, that you need to prove is of size 2 to the 20. Okay, so you start with a computation of size 2 to the 28, okay, and then you run one WIR iteration, okay, and the next step you have something of size 2 to the 20, and then you can, much smaller computation, and everything is much faster, and you can run whatever you want. Okay. Comparison. So here's a comparison to Basefold. I want to be fair and say first that we are inspired by Fry and Basefold and Steer, and kind of this work accumulates many ideas and new ones from all these works. And also that, to my best of understanding, these numbers from the Basefold paper are kind of not optimized in the most significant way, and probably can be better. But okay, let's see how we compare. So red is Basefold. In blue, we have WIR UD, which is the unique decoding radius. This is kind of without any conjectures. And in green, we have this WIR capacity bound. So this is with this list decoding type conjecture that is not the same, but kind of similar to what happens in Fry and Steer and all these kind of schemes. So we start with the argument size. You can see that the Basefold argument size is kind of very big compared to both the WIR unique decoding and capacity bound. Okay, so even for quite large computations, the argument size really is less than 100 kilobytes. The poover time, you see, so we didn't compromise in poover time, so the poover time is roughly the same as basefold. Here it's slightly better, but I imagine you can also improve the basefold poover, okay, to make it better, and you can also improve the weir poover to make it better, and so this is kind of a competition. But for the verifier runtime, there's kind of, there's not a lot to improve. It's kind of a small piece of code, which is usually kind of optimal, and that's just what you get. And so you can see that both versions of weir are kind of nearly the 1 millisecond, sometimes below, maybe sometimes above if you don't assume the conjecture, while the basefold one is kind of high, around 20 milliseconds. Let's compare if you are familiar with fry and steer. Maybe I'll say at this point that weir is a drop-in replacement to places where you use fry or steer or basefold as a polynomial commitment scheme. Okay. So again, if I compare that, we can see that, so steer, what we introduced last ZK summit, okay, is in blue now, and in red is fry. So the argument size is much better than fry. That was the main point of steer, and weir just gets roughly the same argument size. The poover time, you can see, is roughly the same in all schemes. Okay, mainly the bottleneck of all these schemes is to do some big FFT, and this is kind of what they do anyway. The verifier hash complexity is much smaller in steer and weir. Okay, but in weir also the field operations complexity is much smaller. So you can see here, okay, so the green one is weir, okay, and both steer and fry have like a much larger verifier time. Okay, how am I on time? I have. Okay, so a little more results. Okay, so because weir was not just a Reed-Solomon proximity test, but actually a constrained Reed-Solomon proximity test, what we can do with it, we can compile not just a polynomial commitment scheme, but actually this sum-check polynomial commitment scheme, or as I denoted here, just a sigma IOP. So a sigma IOP is going to be like a polynomial commitment scheme where I force the prover to send polynomials, okay? Here, I'm going to allow the verifier not just to do evaluation queries to this polynomial, but actually sum-check queries to this polynomial. Okay, so the verifier can specify a polynomial W, okay, this weight polynomial W, and he can get back this answer sigma, which is this sum. Okay, so you can kind of do a sum-check like a query to these polynomials that the prover specifies. Once you have this power, then a lot of the effort is reduced from the polynomial IOP itself, okay, because the verifier is much more powerful. And all of this is encapsulated anyway into the weir low degree test that we run. And so what we do, we actually give a sigma IOP for generalized R1CS, which is kind of has much more efficiency than other polynomial IOPs that you get. And all of this is compiled and batched together to one weir invocation at the end for some polynomial and for some constraint, okay, that kind of is a combination of all the constraints that the verifier queried. Okay, so this gives an efficient way to go from ROCS to IOPs. We kind of didn't implement this yet, and so I don't have really like benchmarks for this part. Yeah, okay. So I think I have just one more minute, so we have something new called mutually correlated agreement. I have just a quick minute on that. So kind of the main technical tool that we use is this proximity gaps, which roughly says the following. Oh, I have many evaluations of functions, okay? And I don't want to test each one individually, so I'm going to take a random linear combination of them. So I have C1 up to CL, and I have this C star. And I have this theorem by Ben-Sasson et al., okay, in this proximity gaps paper, and also Dan Carmon, this should be here in the conference, saying that if the C star is close to Reed-Solomon with high probability, then all the CIs were actually also close to Reed-Solomon. So you see C star, the green spots, it's where it's close to Reed-Solomon, and every CI also has to be close to Reed-Solomon. But actually what they proved is something much stronger. They proved something called correlated agreement, okay? So they proved that this is not the right picture. Actually, all the CIs are going to have a correlated agreement. They're going to agree with Reed-Solomon at the same domain, okay? So the picture is not like this, but actually like this. Okay, so all the CIs, not only that they agree with Reed-Solomon, but they have some shared domain where on it they agree with Reed-Solomon. And kind of what we do, we introduce these new proximity gaps, where we say that it's not enough that the CIs have shared correlate agreement, but the C star should share the same domain as well. Okay, so the picture should be like this, where C star and all the CIs have, so we call this mutually correlated agreement. So we prove that any time you have correlated agreement, you have mutually correlated agreement up to the unique decoding radius, and we kind of still leave it as an open problem to prove it beyond. Okay, conclusion, we introduced WIR. WIR is an IOPP for constrained Reed-Solomon codes. I think it can have other applications, but the main one is, of course, using it as a polynomial commitment scheme. We have verification time within milliseconds, prover time within seconds, and the proof size is really tens of kilobytes. We introduced this new mutually correlated agreement proximity gap. We have this sigma IOP, where we combine it with our WIR, okay, and then you apply the BCS transformation, and all of this together gives you our hash-based SNARG. This fast verifier can gain new applications such as, efficient on-chain verification, recursion, and other stuff. Yeah, that's it. Thank you.
Okay. Do we have any questions in the audience? Question. This is where I get my cardio in.
So surely I'm just not understanding something. I'm trying to understand why this mutual correlated agreement doesn't follow for free from correlated agreement. Can't you, in other words, assuming that the CIs have correlated agreement on some domain, can you not always just take the underlying code words, combine those in the same way, and then you get the same error domain for the C star? Why does that not come for free?
Yeah, good, excellent question. So you're right, so the CIs have correlated agreement, which means that C star, which also be close to the code word. But what I don't get as a guarantee from the proximity gaps paper is that C star might have additional domain, which is close to the Reed-Solomon code, where the CIs do not agree on that domain. Okay, so I want every place that C star agrees with the Reed-Solomon, the CIs have correlated agreement on that domain.
I see. So that needs to be the only domain
It could be more than one. Could be more than one.
But then the others have to also be close.
Okay, yeah, if C star has 10 domains where it's close, that's fine, but all the CIs also have 10
They need it too, okay.
Okay, it's kind of an if and only if.
Got it.
Okay, thanks. That was a great question.
Any other questions? Okay, round of applause for Ilan. So we have a quick break right now, and we're going to share the after party information up on the screen. Oh, it's there. There you go. Scan it. Come drink. All right, everyone, we'll be starting in 1 minute. Alrighty, so up next we have Nicholas from Lagrange. Yeah, take it away. So.
Hello. Ah, perfect. Yeah. Okay. Hi. Hi. Hello. Okay. Thank you, everyone. So, hi, everyone. Today I'm going to speak to you about what we're doing at Lagrange. I'm going to talk about a bit of SQL and more technically what we are doing behind the scenes. So, let's go about it. So why do I mention SQL here? Basically, we are building a verifiable SQL VM. So that means you can query the database and get a proof and the results, that the result is correct. So how does it look concretely? Then, okay, it looks like this. Basically, we are focusing first on the historical blockchain data. So basically, if you have, for example, take a ERC20, so think about USDC, for example, where there can be millions of entries from the user address to the balances. Then you can actually register your SQL query, where you say, give me the average balance of this user for the last 2 weeks. And for this address, you can use placeholder as well. And we're going to give back the results and the proof on chain. Okay, that's more like the product-facing point of view. And I'm going to explain to you how we are doing it during this talk. And I'm happy to talk more about the product side after my talk, because it's going to be 15 minutes, so very short. Cool, so what do we do here? We are talking first about indexing historical blockchain data. So that means that every block, we're going to insert the values of some slot of interest in the contract. For example, if you have the mapping, we're going to insert all the mapping entries into our own database. Okay, that's called the indexing part. And we're going to do this at every block because we want to keep the values and want to do the average, for example, or over more complicated SQL queries down the line. Then comes the query part. Okay, so this first part is just insertion. Think of it as a time series database. And the second part is the querying part, where we actually run the SQL query across a subset of this database, and we prove the results. So what is our database? I've been mentioning this since the beginning, but we need a database which is, well, proof-friendly, okay, because we want to give a proof. So that means we can't use things like, I mean, it's not very nice for us to use things like Ketchak and RLP encoding for those who know how the MPT trees works on EVM. We want also to be horizontally scalable. Just to give you an order of magnitudes, if you want to do an average across a full week, just like on EVM, on L1, on Ethereum, it's like 50K blocks. If your mappings have, I don't know, 1 million entries, you're already 50 billion entries. Okay, so we want to be horizontally scalable to be really handling large-scale computation. The third point we want is also efficiently updatable. That's a very, very important point for us. Imagine between block I and block I+1, there's only one swap of token. I sell some of token and give to another holder. Then I don't want to have to reprove the millions of entries for this block. I just want to efficiently update my database such that we only insert this new value for me and the recipients, okay? So how does it work? Like I hinted before, at every block, we are looking at the storage level of interest for some contracts. So for the variable mapping thing like this, we can do strict, we can use single variable thing like this. Later, we're also working on the transaction try, receipt try, and everything. And we are extracting this value, we're proving that all these values belong to this contract, and we are inserting the same values, but in a more ZK-friendly format, so no RLP, no K-check, thing like this, with a nice, think of it, of database as a nice BST Merkle tree with Poseidon. Okay, it's a fairly bit more involved than this, but I'm going to skip the detail for this talk. And we do this at every block. And so we insert all this value into our database. And then comes the query phase. Okay, so the query phase, here it's a very simple example where you can imagine you want just to compute the average. So you compute V1 plus V2 on the left node, on the left side, V3 plus V4 on the right side. You can compute this in parallel. So this is where the parallels property comes into before. And then you can aggregate the proof to get the final proof at the end. So here for the query phase, we use recursion as well a little bit. I'm going to focus a little bit more on the indexing part because this is like really the crux of what we are building here. Let's skip this one. So how do we build this database? So we need two major ingredients there. First, we need what we call record trees, which is a paper invented by the research team Lagrange. So let's take the problem of we want to prove a membership proof for many leaves inside a tree. Okay, it could be a Merkle tree, it could be MPT tree. Let's take the naive approach. Okay, if we use a regular proof system like Growth16 or, for example, any ZKVM, the usual way you would do it is like you feed all the witnesses, so you feed the value 1, 2, 3, 4, and you directly prove that they all are inside this tree. Okay. What happens when we update the tree? So, for example, from block I to block I+1, there is one value that changed. Let's say now instead of 3, it's 8. Okay. Well, basically the path changed, okay, but the rest didn't change. But inside the proof, you still need to give all the values still. So the computation is linear in the number of entries here, because remember we are appending things. So we are copying all the values from block I to block I+1 and only change the one that changed. Here, I still need to run a proof across all the values. So that's not good for us, because again, think of a large-scale contract with millions of mappings entries, that's not scalable enough for us. So what we do instead is we go more into the MapReduce paradigm. Instead of doing one big proof over many data, we do many proof over a small subset of data. So now we turn the thing around and we say one node of the tree is equal one proof. Okay, so we have one proof for the node 1, one proof for node 2, 3, and 4. Each proof exposes the hash of the subtree that is rooted at this node. Okay. So, for example, in the left orange one, then we're going to have the hash of the concatenation of the hash of 1 and the hash of 2, okay? And so we're going to have two proofs at the middle and one final proof for the roots. Here, we use a lot recursion. You can see that the proof in the middle needs to verify the proof for 1 and verify the proof for 2. And the top group proof needs to verify the children proof as well, okay? So we use recursion all the way here. So we pay a bit more because recursion is not cheap. The nice thing about it, though, when we update, well, we don't need to recompute everything. Now we only need to recompute the proof from the value to the roots that change. Okay, so this slide is wrong, it should be 8 here. But imagine 3 is 8, then you just recompute the proof for 8, its parent and its parents. And here for the 4, you can just load it up from the previous block. You don't need to recompute it, just take the one that we had before, okay? And so that allows us to have a complexity logarithmically in terms of number of updates now. So our assumption is like the block entropy, the entropy between blocks is fairly low, so there's going to be a few updates between few transfer between blocks, and so that allows us to be very fast in proving updates now. And so what we do is just copy the whole database, and we just recompute the proof that we need to recompute, and we leave it as it is. That's the first tool, okay? The second one is the digest translation. So this has been hinted already by Jens Grove this morning. We are also using multi-set hashing. So the problem here is in MPT, the order is complicated, let's say. It really depends on the key you're putting in the mapping, things like this. EVM and Solidity, there's very special rules. And so you don't have a nice structured order. For example, we could have the value 1432 in this order if you just enumerate the leaf like this. And we have very much different kind of branches and things like this, and extension node and all this stuff. These are non-proof friendly at all. And also it imposes a certain order into it, okay? And we don't want this. We want to build a database which is efficient for querying. So that means we want indexes, we want a BST property as well, proven thing like this. So how can we turn this weird ordering into our own nice database? We can't just use a hash function because the order is important here. And this is where the multi-set hashing comes into place. So basically it's, as explained this morning, you just take your message, you hash it, and you map to a point in the group. For this, right now, we're using Plonky2, and we're using the EC-GFP5 curve. And so we do a hash2 curve on this curve, which is based on an extension field, the fifth extension field of Goldilocks. And we just compute the digest in the MPT. Okay, so we have digest D here. We compute the digest on our own database from the same value. So you can see D1 plus D2 plus D3 plus D4, this is the Merkle tree in order. The D2 is from the MPT, but then the result is the same. And so we, at the end, we recursively verify the true proof and to make sure that both have the same digest. And if both have the same digest, that means both contain the same data that we extracted. And that's the second tool. So basically, when we put things together, at each block, we are extracting the value of interest from the APT, extracting the value of interest for own DB. We show that they contain the same digest. We only update the proof that are needed during the updates, right? And that's it. We do it at every block. Then now comes the query part of it. So I think I have this slide. So the query part of it is fairly short because of this talk is quite short, but basically, we treat each node of the tree as a logical SQL row. So think of it, each node can contain your balance, the total balance, and the user address, for example. How we going to do the query? Well, our tree is kind of a BST tree, so we're going to look right in the portion that satisfies the predicates on the index. So for example, if we had an index on the address, then we're going to sort the tree, we have a BST tree on the addresses. And so we're going to look at all the rows that satisfy the predicates. We're going to show in circuits that they satisfy the predicates, and we're going to compute the results. And then we simply grow up the tree and accumulate the results one by one. Okay? So at the end, when we reach the top of the tree, we got the aggregated proof, aggregated results, and we can just submit this on chain. And we, of course, we do a wrapping gross-sifting off chain to submit on EVM chains. That's our main target right now. Went a bit. Okay, got 5 minutes. So the other thing I want to quickly mention to you today is also the fact that, as you saw, we are using recursion a lot. So that means we are generating a lot of proof. Like I'm talking about 200, 300, 400 proof per minute easily. So we're dealing with thousands and thousands of proof. To generate all this proof in parallel, we need a strong proven network. So we're also building our own proven network, basically. So we're building the proven network and the application building of it, dogfooding. And so here it also requires quite a lot of changes. So we are an AVS with restakes security from EigenLayer. So here the economical security only comes for the liveness property. So if I send a task to a prover and it doesn't reply with me with a proof in certain timeout, before a certain timeout, then it's going to be penalized. But the guarantee that the proof offer is still relying purely on the cryptography assumptions. The stake is only there for the liveness issue. And yeah, that's really basically the oversight of Lagrange, also what we are building. Again, the proof network and the application building on top of it. Just a final quick slide to just show where we are right now. We we shipped on April the Euclid testnet with a basic set of query where we can only extract mappings. We implemented the proven network in May. And we just recently launched our ZK group processor 1.0, where we have the basic of the SQL VM now fully implemented. And now it's just a matter for us to implement more and more SQL functions. For example, we're going to be working on joins, order by, group by, all these things. Simple select. And also more and more data that we want to extract. We want to extract the receipt tries and the transaction try as well. And then coming up for ZK Processor 2, this is when all the features will be there. And I guess that's about it for me. I have 2 minutes for question if there is any questions.
Do we have any quick questions? We have 2 minutes. Over there.
Sorry, great presentation. Can you do zero gas transactions with Lagrange?
Can we do zero gas transaction?
Yeah, what's the cost usually for a query?
Okay, so right now the cost first is to verifying a gross 16 proof on chain. So it's like 280 gas or something, 200 gas, depends on which type of gross 16 we're using. And there's also the cost of querying. So for example, if you are querying a month-long average or a week-long average, if this is 50K blocks, for example, for a week long, if you're only querying for 2 hours, if it's 600 blocks, so it's not the same range of computation as well. So also the price model is to be determined as well according to the size of your query. And there's also the part, this is for the query part, there's also the indexing part, because we automatically index some tables, so we need to also to take that into account, that we are, at every block we are automatically making some proofs, so we are doing also some work there. So there's also we have to pay for the indexing and for the query. But the cost there is not that significant if we can use our proven network efficiently, and so, because we are not paying the cost of proving them directly.
Okay, that's all. Oh, wait. Is it a fast question? It's ZK, it's not good.
Thanks for the presentation. The values that you're storing in these record trees are like usually public values or like a representation of like the storage of a smart contract on chain, or they can be also private values?
Yeah, so here I presented our main use cases, which is on-chain historical data, but again, we are building a verifiable SQL VM, so we could put any data into our SQL. The nice thing about blockchain is we can prove that we correctly extracted this value from this contract, from this slot storage, from these variables, from this block header, with this chain ID even. We can be cross-chain compatible and things like this. But we can totally also upload just NFT metadata, which are not proven at all, and we just put a hash as a kind of commitment, and that's about it. But we can't, the client will have to trust that it's done correctly, because we can't prove it's come from. Thanks.
Okay, thank you, Nicholas. Round of applause. And up next, we have Ali from PSC and Y Academy.
Hi everyone, my talk is quick and high level, and the tools and ideas that I'm talking about, they have been around for some time, but I think sometimes we may not be aware of something because we are in it. I think collectively they're part of like an emerging paradigm. So we have been at this blockchain thing for a while now, right? And what we have been saying to ourselves for a long time now is that grandma is coming on chain any minute now. But obviously we can all agree that she hasn't. She's not here. And we can't blame that on scalability because that has been solved. That has been solved already, so we can't use that excuse anymore. So things are getting awkward, I think. And I think we have to come to the realization that grandma is not coming. We have to go to her. Grandma is not coming on chain anytime. Not now, not ever. And the thing is, in my view, the blockchain, what we call the blockchain, has been isolated. Has been really isolated from the real world. People will bring in oracles, but I think oracles are not it. Oracles cannot possibly support everything. They can't oracleize private data. And obviously, also, they come with a garden variety of assumptions, which defeats the whole purpose. We are all here to disintermediate things, not to insert new intermediaries. So oracles are not it. But programmable cryptography may finally be the thing that removes some of these barriers. So with the advances in proof systems, for example, we can take anything now that has a signature and just shove it in a circuit, and then we use it. And what we are now able to do is what I think of as recycling and repurposing of any and all cryptographic artifacts, whether they're coming from the blockchain or coming from Web 2, we can now recycle them, repurpose them, and extend the life of them into fresh new use cases. We also have new primitives, and these have been around, as I said, for a while, for grouping, signalings, and many other things. But they have existed in isolation, and mainly I think it's because of this barrier, this isolation from the real world. You can create an anonymous group with super resistance, but on its own, it's not really that interesting. What are you going to do? You created a group, you're part of a group, now what do? You need something, it needs to be part of a whole experience. Obviously, we have the advances in proof systems. Now, regular expression should not come to us as a surprise that we can prove it in circuits. And some excellent developers have done exactly that. And since emails have patterns that we can describe with regular expressions, and they also have a signature coming from a private key that belongs to a certain entity that we can verify publicly, together we can get something called ZK email. So you can get a proof that I have received an email from a certain organization or something. And with that simple primitive, you can do a lot of things. In fact, you would be surprised by how many use cases you can do with just this primitive. We have semaphore, which has been there for a while, but again, I think it hasn't been used to its full potential because it lacked an environment in which it can grow as a seed. Anonymous grouping and signaling, you can signal and vote on multiple things in a fully anonymous and without double signaling. The same way that we in Zcash they prove you cannot double spend a note. You use a nullifier. You can do that as well here. If the voting is high stakes, you can use a tool called Macy, which has been iterated upon many times, and get some excellent features like collusion resistance. So basically, if you vote for someone, you have possibly no way of proving to anyone else what you have voted for. So if someone bribed you, you can take the bribe, but still vote for your conscience, for example. Now, these things can already in between themselves without looking at the outside picture and some of the things that I'll talk about. You can already take some of them and use them in a useful ways between each other. So semaphore could be a gatekeeper for Macy, and ZK email itself can be a gatekeeper for semaphore. So you have to have received an email in order to join the semaphore and so on. In fact, I should mention the gatekeeping feature itself. There is a whole new project at PSC that is launched this week just around this idea of creating as many, a garden variety of gatekeepers, but also allowing you to create your own gatekeeping. And then we have also MPTLS, which has been gaining some traction. There is a bunch of projects working on it. Basically, you log into your bank, and the TLS session is split between you and a verifier or a notary. And the neat thing is that the verifier doesn't need to know the content or the server identity, but you can still prove to them part of the data. Obviously, that comes with some trust assumption in the notary if you're using it rather than verifying directly. And the performance, you have to be mindful of the performance as well of the MPC, but it's usable. And some of the new emerging projects are improving upon that idea. And finally, the ZK coprocessors, obviously, my friend was just talking about Lagrange. We can now recycle and repurpose historical cryptographic artifacts from the blockchain. So something happened in the blockchain a long time ago. The blockchain states or contracts do not have access to them, but we can reuse previous truths, basically. I won't speak too much about this because I'm sure you're already familiar with it, but the exciting thing about the coprocessor is how different approaches have emerged. People are coming at this from different directions. And you know, one of the things that we heard over the past year is that we have enough infrastructure. We don't need any more infrastructure. We need apps. We need people to come. We need use cases. But actually, this is one area where I think we need more. We need more, not to mean we need more projects and so on. Yes, we need more projects, but we need more people to think about abstraction. How do we abstract the chains? How do we create the right abstraction? So if you are a software developer or architect, I think this is one of the most exciting areas you could be looking at. Obviously, ZK coprocessors do not have to be limited to historical blockchain facts. You can use them or integrate them as well with proofs from Web 2, from artifacts from Web 2. And together, they can start creating a collective, a holistic, non-trivial, and fresh experience. Yeah. So one of the ways we can reuse or recycle, repurpose some of the things is Discord. Like in Discord, a lot of us exist on Discord. We have roles, we have communities. So you can prove that you have a certain Discord role, and based on that, you are giving certain tokens that you can vote or allocate to someone, and that voting could happen through Macy for collusion resistance. And to start voting to begin with, you would have to have a ZK email proof that you are part of the organization, or a ZK email that you use to join a Signal group. So this use case alone, giving appreciation tokens to colleagues, you can see that it already employs all of these primitives together. Obviously, this is a simple example, but just to drive home the idea that the whole is extremely exponentially larger than the sum of the individual parts. Semaphore in its own is really not that interesting. It's only when you integrate it with other things. Because this is the lightning talk, I didn't have time to go through all of them, but you'll have them on the slides. There are so many. There are at least 36 projects, some of them proof of concept, some of them actually in production now. The folks at ZKPTP are creating marketplaces from only one primitive, which is the ZK email, which is exciting. So there is a bunch of projects there to look at. So all of these, what I have talked about right now, I mentioned at the beginning of the talk that we might be part of something, but we are not aware of it. And I think all of this together, looked at together, the recycling and repurposing of cryptographic artifact is sort of like here in the middle. It's happening in the middle. They coexist with other also exciting things, the lower level things like pre-confirmation markets and the super building and all of that. And so what if I may speculate, like what I think is going to emerge over the next years is that this middle is going to get much larger than what it is now. And what we have previously thought of as the blockchain, I think is going to, go a bit farther to the back. Blockchains will be similar to what, the relevance to the average developer will be the same as the relevance of database management system. Not all developers are writing SQL store procedures or things like that. So this layer, I speculate that is going to get much larger, and this is one of the reasons why I say ZK Go processing. We need a lot more projects, a lot more ways of abstracting things, a lot more out-of-the-box things that people use. If you look at the ZK coprocessors, you will notice that some of them, they try to provide out-of-the-box solution in their SDKs for things like D5, for example. So now, if you're familiar with the Uniswap v4, for example, they have hooks, and there is nothing stopping this hook from consuming an off-chain computed zero-knowledge proofing something about the history or the track record of this address. So this guy is an OG. We're going to give you a discount to trade on our DEX and things like that. So this is something like project like Previs is doing, for example. Yeah, this is the same thing. So we'll soon think of smart contract developers. Even I would even say that smart contract development itself is going to go all the way in the back, and most developers will be dealing with this big here, which is something like the equivalence of Lambda functions and cloud solutions. So this is the bazaar cloud of the blockchain compared to Cathedral, Google Cloud, or Amazon, or so on. So yeah, with that, I included a link, but I think I forgot in this slide. I'll find me after if you want a link to the slides, but that's my talk, and thank you.
Thank you. And we have time for one question, if anyone has any questions. Nobody? Okay, thanks again, Ali. Okay, 2 minutes ahead of schedule. Congratulations, Jacob. You can take them, yeah.
All right.
Okay. Jacob from Risk Zero up next. There's a microphone up here. Yeah.
Test. All right. Hello, everyone. My name is Jacob Waitman. I'm a compiler engineer at Risk Zero. And today I'm going to be talking to you about Zergen, our new DSL for writing efficient ZK Stark circuits. First, a little bit of context about Risk Zero. We recently announced a new network called Boundless, which we envision as sort of the full stack solution for zero-knowledge application developers. So this is everything from how you actually get your zero-knowledge proofs on-chain for use in real applications, all the way down to the ZKVM layer where the execution actually happens. So today we're going to be zooming in on that ZKVM layer as we're talking about how circuits actually get built at Risk Zero. So back in the old days of ZK, applications were built with custom circuits per application, and you would pass in some sort of input and you'd get your proof out at the end. The primary innovation of the ZKVM model is that application-specific circuit gets replaced with a general-purpose circuit that implements a general-purpose architecture. At Risk Zero, that is RISC-V. So now the program itself becomes part of the input, such that when we want a proof, we can just hand it a program written in a conventional language compiled with something like the Rust compiler or anything that works with LLVM, along with the input, and get our proof. But in pursuit of higher performance, it seems ideal to have some additional accelerators. So in parallel, or in sort of analogy with the way that conventional software engineering works, where you write a program in a general purpose language and run it on a general purpose CPU, over the last few decades, we've seen the emergence of heterogeneous computing, that it's beneficial to offload intensive computations to specialized hardware that can do them faster, things like GPUs, FPGAs, DSPs, things of this sort. And so the model that we're pursuing here is to have our general purpose RISC-V CPU in this model, as well as a series of accelerators for specific operations that we could do a little bit more cheaply with a custom circuit. These are things like accelerators for the catch-check hash function, or alternate commitment schemes, elliptic curve operations, things like that. So when you go to do a proof on Risk Zero, typically it's useful to have sort of unbounded duration of computation. And so in a Stark-based proof system like ours, we have to subdivide this into fixed size segments. But after we've done that, we can roll them up together with recursion. And so the traditional picture of what you can do today without accelerators looks like this. Now, when we introduce accelerators, the picture stays pretty much exactly the same, except that the third line here changes. We can swap out some of these segments with accelerators and roll them up in exactly the same way to a single succinct proof. So with this in mind, right, this architecture calls for a lot of different circuits. We have the ZKVM itself, which implements RISC-V. We have a recursion circuit that is able to verify these receipts. as well as an unbounded number of accelerators that might be useful to plug into different applications depending on the application developer's needs. And so with all these circuits, it would be really ideal to have a really great experience when designing these in order to be able to effectively design, implement, test them, and be confident that they're secure and efficient. So it turns out, though, that a lot of the ways that people have written Starks comes with a lot of drawbacks. In particular, each of these drawbacks comes with an opportunity to do something better. So one thing that we saw was that a lot of Stark description languages really split out different parts of the implementations. You have separated constraints from witness generation, and it's all separate from, for example, the logical structure of the circuit that you might use to achieve some notion of composability when writing your circuit. The other is that composability options are often quite limited. And so it would be really nice if we had the ability to describe a small fragment of our circuit and then glue these pieces together and test them independently and do all of those things that we get to do in traditional software development. And lastly, there's a lot of boilerplate and complexity that comes along with writing circuits. For example, for every circuit that we wrote, we found ourselves re-implementing things like permutation arguments and lots of other things of that sort. So let's zoom in and look at some real Zergen code and see what it looks like. So we have a single concise representation that captures everything of interest here. So for example, let's take this bitreg component. It's going to take as input a value called x. It's going to write into a register. A register is an abstract view of a column in the Stark trace. This reg component comes along with an implicit constraint that that register value is equal to x. Then we go ahead and add another constraint here. So this polynomial is satisfiable if and only if r is equal to 0 or 1 in order to make these terms 0. And lastly, we return this value r. This is not exactly a return statement, but it's quite similar. And it indicates that this bitreg component can, in any context, be used as if it is a register, that register r in particular. So you can kind of see how we've commingled all of these things together into this very short representation. Next, let's talk about composition. So you see here implementations of 4 distinct combinational logic gates that you'd see in traditional hardware design, right? You can negate a bit register by subtracting its value from 1, because 1 minus 1 is 0, which is not 1, and 1 minus 0 is 1, which is not 0. And similarly. So you could go in and check all of these expressions, but the thing that I want to call out here is that we have this very nice, almost functional sort of composition that you can do with this. The other major type of composition that we have in the Zergen language is called a mux, or a switch, where we can multiplex over a set of selector values. So with this component, full adder, we're implementing a add with carry component using the components that we just composed out of bitreg in order to do a 1-bit adder with a carry in, C, and a carry out. So the sum should be true if at least if an odd number of x, y, and c are true, that is, our sum is 3 or 1, which can be done in this way, which should be a familiar expression for people that have studied hardware implementations of adders. And the carry bit should be true if at least 2 of them are. So we do this by cases. If C is true, that is, C is 1, then this selector becomes the array 1, 0. And so this first mux arm becomes active. So if C is true, then we only need x or y to be true for the carry bit to be set. And if C is not true, we need x and y to be set for the carry bit to be set. In fact, when I look at this, I actually think it feels a little bit simpler than the combinational logic expression to do this in traditional hardware design. There's a lot of other niceties that sort of come with this that are a little bit harder to fit in slide-sized examples. But one of them is that permutation arguments are built into the language. That is, you can simply declare a component with the argument keyword, and we will automatically synthesize a logup sum for it in order to do a logup style permutation argument, and all of the layout constraints that come along with that will be implicitly enforced. Similarly, we have an abstract way to describe the structure of a circuit, which enables this sort of composition. That is, you can abstractly describe the logic of the circuit that you want without having to bother with the particular column offsets or how things are precisely arranged in the concrete Stark implementation, and then the compiler can go and generate an efficient layout using a constraint solver at compile time. Lastly, it has some built-in facilities for testing, such that you can write unit tests, integration tests, whatever you feel like, directly alongside your circuit implementation, which ends up saving a lot of work and eliminates the need for test harnesses and extra tooling in order to test fragments of a larger circuit. Now, you might be thinking maybe this comes with some significant performance trade-offs. That is, we're losing a lot here by accepting all of this abstraction. And it turns out that that's not entirely true, in the same way that most of us don't write assembly anymore. If we want to do low-level programming, we write something like C or even Rust with some extra restrictions. So in particular, there's a lot of room to optimize circuits with this representation because we have so much information about the structure of the circuit in this approach. For one, we have all of the traditional compiler optimizations that you might think of when you think of a C or a Rust compiler even. You get constant propagation, dead code elimination, common sub-expression elimination, and all things of that sort. As well as some more circuit-specific things. So in particular, there are some layout optimizations that can be done automatically. For example, if you were to generate two separate registers that are constrained to be equal, you can coalesce them such that they land in the same actual column of the execution trace, which saves you a register. There's also a lot of room to do optimizations directly on the constraint sets. For example, if one constraint implies that another constraint is satisfied, that second constraint can be eliminated altogether. And so it turns out that there's a lot of things that can be optimized to get us pretty optimal. So Zurgen was released as open source software just last month. And we have a couple of exciting things coming up for it. In particular, we have some accelerators in the works written in it, namely a Keccak accelerator to speed up proving of Ethereum, among other things. And we're also excited to provide some better support for users of the RISC-0 platform to write accelerators for the operations that they care about, even if we haven't written accelerators for them ourselves. And lastly, there's also an interesting opportunity here to use compiler tooling to assist formal methods on circuits. So you could think about doing things like emitting a lean specification from the actual source code, or based on the circuit definition, or even doing things like emitting the constraint set in a format that would be amenable for consumption by a tool like Picus to do determinism analysis. Ultimately, we're not entirely sure what we're going to pursue in this vein, but there are a lot of opportunities for this. So with that, I'd like to invite you all to check out the website for Boundless, the new RISC-0 network, as well as to check out the Zurgen open source repository through the QR code on the right. Thank you. It's 4:10. I think we have 5 minutes for questions.
Okay. Thank you for that great talk. What are the current backends that you have? I guess, first question.
Yeah, so are you asking what proof systems we support?
Well, I mean, like, I don't know, Plunky 3 or whatever else.
Yeah, this is purpose-built for our own proof system. So RISC-0 has its own Stark-based prover, and it targets that.
Any plans to support other ones or make it configurable somehow?
Well, it's open source, so we would certainly be amenable to people contributing that. I don't think RISC-0 is likely to invest in that.
Okay. Thank you.
Questions?
Yeah, thank you. If I recall correctly, there was a talk in CK Proof 5 that was talking about Surgeon, but I think it was a product that was very different. It was more about backwards compatibility with the circuits, if I recall correctly.
Yeah, so Surgen was the old internal to slightly external name for this compiler infrastructure, and that name was largely used to describe sort of an earlier version of that, where we were really only doing the compiler-based, like traditional compiler optimizations on custom intermediate representation for the circuit. So the language front end is totally new, as well as most of the optimizations. So that's what we've been working on for the last 2 years.
Yeah, thank you.
Yeah. I think we had another question here on the left.
Thank you for the talk. It's just what kind of constraint optimization techniques do you plan to apply?
Yeah, so one in particular that's really obvious is if you have two identical constraints, you can prune one of them. One that's a little bit less obvious but not hard to explain is that if you had a constraint like x times x minus 1 times x minus 2 equals 0, and another constraint like x times x minus 1 equals 0, yeah, one of them is implied by the other. That's the kind of thing that I'm talking about when I talk about that.
Any other questions?
So, do you allow to write your own pre-compiles in a sense, can I write my own Ketchak implementation, for example, in this language?
I'm not sure I heard the question.
Do you allow to write your own kind of pre-compiles in a sense with this language?
You as a user of RISC-0?
Of Zircon, yeah.
Yeah, it's not well supported right now, but that is on the roadmap. Yeah.
Okay, thank you again, Jacob. Okay, you have some extra time. Next up, we have George from Powder Labs. And this is our final lightning talk before we take a break. So yeah, welcome, George.
Hello, hello. Working, nice. So this talk is about how can we build a ZKVM in a way that's agnostic of the proving system, which is something that we're concerned with at Powder. So let me give you a very quick introduction. So at Powder, we kind of have a DSL to describe a VM, and it looks like this. The user can declare some registers and some instructions, and then provide an assembly program using these registers and instructions. And then that compiles to a ZKVM. But we want to do this in a way that is agnostic of the proving system. Obviously, this ZKVM is extremely simple and kind of useless. But we also have an implementation of RISC-V, for example, but you could also imagine ZK-EVM. Yeah, and that would take a few hundred lines of code in this language. But this talk is going to be more about the low level, so let me walk you through the compiler pipeline. So on the left-hand side, you see the high-level description, and the first step would be to compile to PIL. PIL stands for Polynomial Identity Language, and has originally been developed by Polygon, and describes some low-level constraints. And then from PIL, we can compile to different proving systems. An obvious choice is Starks, because that was the original use case by Polygon. But this talk is going to be about how can we also go towards folding-based backends or GKR. So in order to explain that, let's go through some of the details of PIL. So this, of course, I'm going to explain this using Fibonacci. And so on the left-hand side, you see a very simple PIL program that describes a Fibonacci computation. On the right-hand side, you see the corresponding execution trace. So in the first two lines, the program declares two fixed columns. And fixed columns are columns of the execution trace that have a fixed value. So the values are fixed ones at setup time, and the prover cannot change them. And in this case, they're only used to indicate whether we are currently in the first column or the last column. And then there are two witness columns. And witness columns can be filled with any value by the prover, but they're subject to some constraints. And so if we look at the constraints, for example, the first two constraints essentially force the prover to initialize the Fibonacci sequence correctly with the values 1 and 1. And you can see that we have to multiply with this is first column because one property of constraints is that they always have to be satisfied in all rows of the execution trace. And then the next two constraints basically force the prover to update the Fibonacci sequence correctly. And you can see that we have this next operator, which is kind of this prime operator, which means that we're not referencing the value of x in the current row, but in the next row. So that's mostly the abstractions that we have. So just to recap, there's columns, which can be fixed or witness columns. There are constraints, which involve additions and multiplications, and they can have a next operator. And they need to be satisfied in all rows of execution trace. And one thing I haven't yet talked about is verifier challenges, which are just random field elements that are sampled by the verifier after some witness columns have been committed. And this is useful to implement lookup implementation arguments and other things. And here you can see an example of how you would implement a permutation argument. So let's go through all the proving systems. And first up, Stark. As mentioned before, this is the most straightforward one because that's kind of what Pooh was designed for. And I don't want to spend too much time on it, but basically a Stark is going to interpolate a polynomial for each column of execution trace. And this is my attempt at drawing these polynomials. And then the constraints just become constraints on these polynomials, and Starks are designed to prove that constraints on polynomials are satisfied. And next up is folding-based backends. So what are folding schemes? So one thing they do is they provide for incrementally verifiable computation, which means that you start out with some initial state, which you can think of as just a small vector of field elements. And then you keep repeating the application of a function, which is fixed function. It's always the same function in each step until you end up with some final state, and that's the result of your computation. And this function, at least in the simple cases, should be the same in each step of the computation. And that is kind of similar to PIL, which has the same constraints on all rows of the execution trace. So if we look at a simplified version of this Fibonacci program, here it's the same program as before, but I left out these is first and is last column because folding schemes kind of have a native way to represent the first and last state. But given these constraints, we can essentially extract a function f that computes the next row from the current row. And so we can view the execution trace as a collection of intermediate states where each row has been computed by the function f from the previous row. And so if we view it like this, then it fits into this IVC scheme, and then we can compile to a folding-based backend. And last but not least, GKR. So GKR is another protocol that proves correct computation of a shallow layered arithmetic circuit. So let's go through each of these terms. So an arithmetic circuit is a circuit that computes something just using additions and multiplications. And a layered circuit means that each node in the circuit can be assigned to a layer number, and then you can only receive inputs from the previous layer. And by shallow, we mean that the number of layers should be small, which is important because the verification time is going to depend, it's going to be proportional to the number of layers. So in particular, the number of layers should not depend too much on the size of the input layer, for example. And another property that's desirable if it's a structured computation, which you can see here. So you can see here it's not an arbitrary circuit, it's many copies of a small subcircuit. So it's kind of describing a data parallel computation. It's applying the same function to different inputs. And eventually, all these layers, the value of these layers are going to be represented as polynomials, and the verifier needs to be able to evaluate these polynomials, but only for the input layer and the output layer, which typically means that for the input layer, there's going to be some polynomial commitment scheme, and for the output layer, it could also be committed, or it could be easy to evaluate by the verifier for some other reason. So that's it for background. Let's look into how does it all relate to Perl, and how can we take a program and compile to GKR. So in this extremely simple program, we just have 2 columns and 1 constraint. And the idea is kind of to just put a concatenation of all the rows of the execution trace and put them into the input layer. And then the constraint needs to be satisfied in all of the rows, so we can instantiate a small arithmetic circuit many times that just evaluates the left-hand side of this constraint. And if and only if all the constraints are satisfied, the output layer would just be the vector of all zeros, which is encoded as the 0 polynomial, so it's trivial to evaluate by the verifier. And that's it. So just to recap, I kind of view Perl as a language to express constraints on vectors of field elements, which is kind of a data parallel way to describe computation. And yeah, like a structured computation that is exploited by different proving schemes but in different ways, but we can kind of compile to all of them, or at least the ones I've mentioned. And yeah, that's nice because then you can describe your ZKVM once and decide on the proving system later, or even prove different parts of the ZKVM with different proving systems. Time for questions.
Any questions? Okay, these lightning talks are getting shorter and shorter. Thank you again, George. All right, we have a 15-minute break coming up now, and then our final talk, and then followed by Anna Rose and Friends panel. So join us back here. Welcome, everybody. Welcome, Zach. You made it. I thought you were in the back loading the T-shirt cannon. I thought you were in the back loading the T-shirt cannon.
Oh, sorry. No, didn't bring it.
All right, everyone. For our final talk, we have Zach from Aztec, and then stick around after for Anna and Friends panel. So take it away, Zach. There's a microphone up there.
Cool. Hello, everyone. So, do I have a clicker? Ah, here it is. I'm just blind. So yeah, I'm Zach. I am the CEO of Aztec, and I'm here to bring the good news about Honk, Mega Honk. So, who here has heard of Aztec? Okay, I'm still going to explain what Aztec is, though, for like the few of you who don't. So Aztec is a privacy-preserving programmable layer 2 for Ethereum. So we do snarks, but we also do privacy, private state, all of that jazz. I can't do technology. Is this, hello, help? Okay. Hey, okay, great. So, yeah, so we've been around for almost 7 years now, which in Web3 years makes us geriatric. So I'm about to retire to a home. But yeah, so we've been pretty busy all that time. So I was learning about ZK snarks and all of that jazz in 2018, and ever since then, the goal has really been for me and our team to create programmable, privacy-preserving smart contracts. So, as a regular Web3 engineer can write a smart contract like they do on Ethereum, like they do in Solana, but you have private status first-class primitives, and you can do all sorts of fancy things like identity controls and hidden state, hidden information games, basically allowing the real world to interface with Web3 by creating trustless oracles, ZK email, the works. And so, yeah, this originally what we're now calling Aztec was called Aztec 3 because we've released several private roll-ups and various pieces of tech over the past 6 years. But this is the culmination of all of our work. This is the grand plan and the grand project for Aztec to create that fully programmable, privacy-preserving L2 and to ship it sometime next year. This is our roadmap. So just want to tout this. We put this together and announced it the other day. So we have a plan. We have a concept of a plan, even. And this is that. So yes, if you want to know more, that is the website link. I don't think I've ever seen anyone actually follow a website link from a slide presentation. So if you'd like to be the first person in the world to do that, please feel free. Okay. Well, the laser pointer's more jet lagged than I am. Maybe it's just me. Yeah. It doesn't like me. Who needs slides anyways? Well, if you can get it working, that would be nice. Oh, yes. Oh, fantastic, amazing. What a wonderful modern world we live in. So, yes. By the way, you might have noticed, or may not have noticed, Huichi, one of our event managers, has made some wonderful Taylor Swift-themed friendship bracelets. So we're all friends here. This is the 11th ZK Summit I've been to, I believe. So who would like a Aztec-themed friendship bracelet? Yes. Who else? Any more? OK, right at the back. Let's see if I can do that. Almost. OK. All right. You ready for some plonk? I didn't hear that. Woo! You see, I like to raise the expectations of everyone before crushing their dreams with boring cryptography and maths. So, what do I want to talk about? What the hell is privacy? What the hell is and okay, so I want to talk about a few things before getting into what the hell is Megaplonk, because the ZK snark landscape is extremely diverse these days, and a lot of previous systems are very much becoming like tailored to quite specific use cases on the various trade-off space. And so at Aztec, we made some pretty specific choices to satisfy some specific requirements that I want to talk about, and also maybe shill Aztec slightly as well. So, privacy. What do we even mean by privacy in a blockchain context? You know, like, do we mean like, what is a hidden transaction? So, there are 3 types of privacy. I think this came from Anna, and I've been stealing it ever since. Basically, you have data privacy, user privacy, and transaction privacy, contract privacy, code privacy. Data privacy is, you know, you can see who's transacting, but you don't know what they're doing, what data they're transferring. User privacy is obviously you don't know who the senders and the recipients are, and code privacy is when you do not even know which smart contracts are being executed. And the goal of Aztec is to achieve all 3. And that's something that we are doing with the current Aztec network. So this can kind of be summed up as basically saying, if you have all 3 privacy properties, if you look at a blockchain, you look at the list of transactions going through, you look at the transaction data, all you can conclude is something happened, and that's about it. How do we actually create privacy-preserving state models? I don't know why I'm even looking here. I can see it here. I'm just blind. So there's a problem with privacy. Well, there's many problems with privacy, but it wouldn't have taken 7 years otherwise. But one of them is that if you have private state that's encrypted, it's effectively owned by the people that can decrypt that state. And that can be a problem with things like shared global states. How do you create a decentralized exchange with a total liquidity supply if that thing is encrypted? Because, well, who owns the decryption keys? And you can solve that kind of thing with very, very complicated multi-party computations, or you can just be a bit lazy about it and have a hybrid system where you have individual user state, which is private, but you also have protocol state for things like decentralized exchanges, which can be public. And you have composability between the private and public aspects. Basically, things like in this example, you'd have a public token transfer function and a private token transfer function. And so basically, you can selectively disclose information if you want to, but you can keep it private. Like the way that we refer to this pattern is very much the concept of privacy for the user, but transparency for the protocol, which generally we think is the best of all worlds, because when you have decentralized protocols, you do want to be able to apply oversight to them, and if they're hiding their data, that's hard to do. So the Aztec contract model is you have these private functions and public functions. They modify different state trees in the Aztec network. So you've got this unspent transaction object tree that handles the private side, and on the public side, you have a more regular Ethereum-based account tree. And of course, we want to abstract pretty much all of the messiness around handling UTXOs away with using Noir's very advanced semantics. But this is fundamentally what's going on under the hood. So the idea is that you have a data tree that is encrypted notes and a data tree that represents account-based state. And yeah, that's how you do privacy. So yes, hang on. Oof, let's not see that again. So architecture. How does the Aztec network function broadly? So this was our original kind of first attempt at creating the architecture diagram. I don't think you can see it, but it says, this diagram is Mike's baby. Please do not edit it without first consulting Mike. Smiley face. So very complicated, very messy. So let's try to break it down. A user transaction in a network like Aztec is what an observer actually sees when they send that transaction to the transaction pool is that you have this concept of a kernel proof, which is a bit like the Zexi protocol. A kernel is a program that validates the correctness of individual transactions. So you have a kernel proof, a list of state variables to create, a list of nullifiers, which represent state variables to destroy, a list of public functions to execute, and the world state that was used to compute the kernel proof. That's all that an individual will see when they look at a user's transactions. And from that, you can acquire very little information. If they are not executing public functions, and the number of UTXOs and nullifiers that they're creating conforms to some kind of standard, say 2 in, 2 out, then this transaction, you can make this transaction look uniform with thousands, tens of thousands of other transactions. So the transaction flow is very much, you have this concept of a kernel proof, which is going to be validating client side, a lot of the ASIC protocol, hiding a lot of information. That then gets sent to the proof gets sent to a sequencer network, peer-to-peer transaction network. The block producer, which is selected through a decentralized mechanism called FINET. When they include your transaction in a block, they will send that block off to a prover network to make a proof. That's when the public functions that you're calling in your transaction flow get proved. And then it goes to a L1 rollup contract. Simple, right? So how do we build privacy-preserving abstractions? Well, we use a language called Noir. It's very much based on Rust and very actively under development. So we've been working on it for about 3 years now. And it's a very different beast to what it once was. Pretty advanced and sophisticated. And we could use Noir to create very bespoke abstractions around how to handle privacy-preserving information, how to efficiently encode programs as snark circuits. So data is represented as encrypted notes. So you have a contract address, a nonce, your storage slot, some storage data. It's a bit like how Ethereum does it, except this stuff is encrypted because there should be a secret in there. No, we forgot. And then you have this concept of a nullifier. So who here knows about nullifiers? Wonderful. That's a lot of hands. I'm very impressed. So for those who haven't raised their hands, the problem with privacy-preserving transaction networks is if let's say I send I want to send an Ethereum to Jens, and I want to do this in an encrypted way. Well, if I have like a note that says Zach owns 1 Ethereum, even if it's encrypted, the act of deleting that note would leak information naively, because on the blockchain network, you'd have to say, okay, that note's destroyed now, and so you could see the transaction that created that note, you could see the transaction that destroyed that note, you see the transaction graph, that's a problem. Nullifiers solve this because nullifier is effectively a way of recording a note as being deleted without revealing that information. Effectively what it is a nullifier is the note, but encrypted under a different encryption algorithm. And so in order to spend a note, I need to prove that the note exists and the nullifier does not exist. And I prove that locally client-side in a privacy-preserving ZK snark, so nobody else leaks this information. And because the nullifiers are encrypted with a different algorithm, if I create a nullifier and post it on the chain, nobody can link that nullifier to a note that I originally created. So basically, you see, if I wanted to send 1 ETH to Jens, I would create Jens' note, and I would create 1 nullifier, but nobody would know like the owners of those 2 entities. So yeah, encrypted notes in Aztec, they're not, I say notes, because I'm using the Bitcoin nomenclature of UTXO, unspent transaction. Wait, they don't use note either. I don't know where note came from, maybe Zcash. Basically, in Aztec, notes don't represent cryptocurrency values, they represent abstract, arbitrary state that a smart contract gets to define how it's used. A bit like storage data in an Ethereum smart contract. So here, we're saying basically encrypted notes, they live in storage slots within a contract. So instead of having the idea of, in other privacy-preserving architectures, the concept is you have state that exists on a blockchain, and you define birth and death predicates on that state. Very literally creating state transition functions for single state variables. We're taking more of the Ethereum approach of you have a smart contract, and that smart contract controls a bunch of arbitrary states, and you can define like the modification rules in a much more abstract way. Private transactions can have public effect, so you can emit an event if you want. You can call public functions. Obviously, this will leak some information, so you be careful with it, but sometimes it's necessary. So yeah, ta-da. And then provers and sequencers create this concept of recursive rollup. So once you have all your user transactions, every user transaction has a very chunky zero-knowledge proof attached to it. That's not cool, expensive to verify on-chain, so we don't. We had this rollup architecture, basically this 2-to-1 compression function where you recursively verify 2 proofs, make that 1 proof, and then you create like this tree hierarchy of recursive provers, which basically means as long as you have arbitrary compute, which for a prover network you basically do, then the overall time required to make that the full rollup proof is logarithmic in the number of transactions in the block, which is nice. Allows us to get, in theory, high transaction throughputs. Okay, so I know this talk was titled Megaponk, and I haven't talked about honk or plonk or anything yet, so this is why I do that. 1 second. Okay, cryptography. Cryptography. Right, so what do we want? What do we want our cryptography to do? So based off of everything I've said, we have a few requirements. Because we are focusing on privacy, we need to do fast client-side proving because we don't want to have users share information with other people. That client-side proving needs to be low memory because if you're working on a phone and you're interacting with a web application, then your phone's browser is going to nuke any tab that uses more than 1 gigabyte of memory, which is fun. And we need extremely fast recursion and folding. Client-side. Partially, this is how we architect our transactions, because if you have a smart contract that calls another smart contract that calls another smart contract, and you want to represent that all in a single transaction, well, all of the smart contract calls are basically representing the execution of arbitrary, untrusted code. And so recursion creates a very nice abstraction where you can basically silo those programs into individual snark circuits, recursively verify them together, and then apply some additional logic to validate the snarks are doing what they should be doing in our kernel circuit. But that needs recursion. We can also use recursion to get past memory bottlenecks by recursing before you use too much memory. And we need relatively small proof sizes. This one is a little bit oblique. Why do we need small proof sizes when all our proofs are going to be combined in a rollup? It's because Aztec is going to be launched as a fully decentralized network, which means every user transaction is broadcast through a peer-to-peer network. And so if every user transaction is large, let's say, for example, it's 100 kilobytes, then in order to get 100 TPS, that means you have 10 megabytes a second. You need 10 megabytes a second throughput on your peer-to-peer network, which means you need considerably greater latency to get that much throughput. So small proof sizes are kind of important for us. So how do we do this? So we have a rather complicated cryptography stack now. Back in the day, you used to just have a proving system and you were done. But nowadays, we have lots of additional high-level abstractions to handle things like the concept of incrementally verifiable computation, which I'll get into a little bit. So our main thing is honk. Honk stands for highly optimized plonk. It's an iteration of the both the Plonk protocol from 2019 and the Hyperplonk paper from a couple of years ago. Basically, it's take the original Plonk paper, replace the check, the quotient testing check, where we check some quotient polynomial is zero modulo vanishing polynomial, and replace that with a sum check protocol. Why do we do that? Well, I'll get into that actually. Add a lookup protocol, add a bunch of custom gates, and boom, Bob's your uncle. Proto-Galaxy is an incrementally verifiable computation scheme produced by Ariel and Liam. It's an iteration of Protostar, and it's very, very efficient at folding honk instances. Specifically, it's efficient at folding arbitrary honk instances. By instance, I mean circuit. So you can have 1,000 different circuits, you can fold them all together, and it does the job perfectly, which is a very rare property of folding schemes. But then we have something called Goblin Plonk. So if you subject your brain to be rotted on crypto Twitter, you might have heard this phrase before. So Goblin Plonk is a computation deferral scheme, acceleration scheme. Basically, Proto-Galaxy requires some expensive computations to be proven inside a circuit. These things called non-native elliptic curve operations, they're very painful to do. We don't like to do them. We like to be lazy. So we have this protocol to basically transform these difficult computations into easy computations, which I'll get into a bit. And then we have this thing called the data bus, which is how to transfer information efficiently between multiple steps of an incrementally verifiable computation scheme. So this one's a little old. We're working on it a year ago. I think Jens has a very nice memory checking scheme, which is better than this. But yeah, we're focusing more on security these days. So, honk. What is honk? So why do we use a sum check protocol? Sum checks are a much older technology than this concept of quotient testing. I think they were around in the 1990s. They formed the backbone of the early proto-ZK snarks. But it fell out of favor because back in the day they had some problems. Specifically, in order to efficiently prove and verify sum checks, you need a multilinear polynomial commitment scheme, which is a more complicated beast than a univariate polynomial commitment scheme. And until the last couple of years, we didn't really know how to both efficiently encode a multilinear PCS whilst acquiring important properties needed for a Plonkish circuit, specifically this concept of a shift. If you have basically we use polynomials as vectors, more or less. And so if you're committing to a vector, how do you do a off by one shift of that vector? That's really important. And until recently, we didn't really have a good way of doing that with a multilinear polynomial, because if you're representing your vector as a multi-dimensional Boolean hypercube, then there's no uniform transformation you can do on that hypercube to get a shift. So yeah, there are a few reasons why sum checks weren't used until recently, but those problems have been solved. So now sum checks are lovely because they have linear complexity in proof of time, and they have very, very low relative memory consumption. Because you don't have fast Fourier transforms, you're not blowing up your witness trace. So for ASTEC and the fact that we have a very, very, very small memory footprint to play with, this is very important for us. And we have a draft paper that's hopefully going to turn into a real paper before the end of the year. So just teasing that now, honk.pdf. So we've had to be relatively opinionated about the specific configuration of honk that we're using for Noir and Aztec. This is because we want to make sure that in the Aztec network, every proof that's being verified has some common structures. For example, the number of selected polynomials is the same, the algebraic statements being checked in the SNARK are the same. And so this is basically what we settled on, is in how do you compile programs to circuits where you can do pretty advanced arbitrary computations without a VM. Because client-side virtual machines add quite a big overhead to memory consumption and recursion costs sometimes. So yeah, basically we have elliptic curve operations, arithmetic gates to do non-native field arithmetic efficiently. If you've ever worked with this stuff, you'll understand why. We have these kind of memory checking gates for these what we call ROM and RAB abstractions, basically read-only memory, random access memory. So in Noir, if you're creating an array, and then you're reading from that array at arbitrary points, or you're writing and reading into that array repeatedly, this is what's happening under the hood. And then lookup gates originally it was the lookup protocol, it's now the logup protocol that we use, so that should be changed. And then we also have a modification to our permutation argument, which allows for implicit efficient range constraints for small range values, and the subset equivalence check concept. Basically, in your circuit, in your witness trace, you can basically define, imagine you color a bunch of wires red, you color a bunch of wires yellow, you can prove the set of red wires is equal to the set of yellow wires, but the ordering of the two is undefined. And that's very useful for memory abstractions and range checks. The paper will reveal all. Maybe if we have time for questions, I can do that too. So here's an example of what's in the paper, sorting gate. This is really basic. How do we do range checks? I'll go into it. So because of this subset equivalence check, what you can do is if you have a bunch of wires in your circuit, you want to range constrain. Let's say you want to put them all to be within a, well, for us, 14-bit range. At the end of constructing the circuit, we add additional dummy gates at the very end. And then what we do is we tag all the wires that need to be range constrained, and we copy them into the additional spare gates we created. And then we apply a subset equivalence check. So we say, the copied, the cloned wires, their values are equal to the original range checked wires. Why is that useful? Because in the cloned version, they're sorted. They're sorted in incrementing value. And so with the addition of a few additional dummy gates to make sure that you can transition across the range, what we do is in the sorted list, we assert that the first wire is 0, the last wire is 2 to the k-1 for a k-bit range check, and the relative difference between two adjacent wires in that list is 0, 1, 2, or 3. So as long as you have 2 to the k divided by 3 dummy wires in the circuit, you can guarantee you can always traverse that range. And what that does is it basically gives you constant complexity range checks. Instead of having to do bit decompositions, you can, well, in our case, basically get a 14-bit range check for a quarter of a gate. And then you can obviously combine those for larger range checks. Why 14 bits? It's because we optimize for small circuits because we're doing client-side proving. And The larger the range table, the more dummy gates you need. IVC. So yeah, this is where things get really complicated. Who here has heard of incrementally verifiable computation? Gotta say, the level of literacy in this room is amazingly high. You should be very proud of yourselves. Incrementally verifiable computation, what the hell does that mean? So imagine you have some permanent state, some database or something, some input state, and then you have multiple SNARK proofs that are modifying that state. So you have some input state, output state, and then the output state becomes input state to a new circuit, and on you go. It's called incrementally verifiable computation because you're just basically updating some blob of data over and over again repeatedly. And an Aztec transaction can be considered an IVC. Basically, every single time you're calling a function, you're modifying some state. And so it's a fancy way of basically saying recursion, and recursion is a fancy way of saying verifying a proof in a proof, but not fully verifying a proof because that's expensive, basically doing as little as you can to mostly verify a proof. And yeah, so folders came to this current state of the art, and they allow for ridiculously efficient recursion. The idea here is in Aztec, each private function compiles to a distinct circuit. And we need an IVC scheme that can compose, what we say by compose a sequence of arbitrary functions means basically we have a function call stack represented in our circuit. And in the kernel circuit, we pop a function off the function call stack. And then we verify a proof associated with that function. And then we examine that proof's public inputs. And depending on what they do, we may push additional functions onto the function call stack or emit other effects. And that's basically one iteration of the kernel circuit. And so to fully execute a transaction, you need to repeatedly prove the kernel circuit over and over and over again until the function call stack becomes empty. So back in the day, this was basically like a pipe dream. When we launched Aztec Connect in 2022, it was one of the first uses of recursion on Ethereum, and it was 700,000 constraints to recurse. To do like 32 recursions took 5 minutes of a 128-core server and 128 gigabytes of memory. So the idea of doing this client-side was a pipe dream, but a lot has changed since 2022. Now this is relatively easy. This is our IVC scheme. Can anyone see that? I can't even see that, and I'm like 1 meter away. Okay, so basically, let me try and walk it through. I can use the laser pointer. So the idea is all these Fs are functions that represent individual like smart contract functions, and K represents the kernel circuit. So the idea is what we're doing is every iteration coming in as a function statement and a proof, and the previous kernel instance. We then VIVC is basically folding. We fold F2, the F function and the previous kernel circuit into some kind of accumulator, and then we spit out basically all the side effects that have been created from the transaction, as well as the newly created accumulator. And the idea is you repeat that process over and over and over and over again until we get to this concept of what we call a sealing circuit, which is basically where we add in the zero knowledge. Because zero knowledge is somewhat expensive. We don't want to do it unless we have to. So here is where all the information that used to be public becomes private. And all you get out of this is the pure side effects, basically those encrypted notes to create the encrypted nullifiers to destroy the public functions to call. Everything else gets hidden away. So you don't even know who's sending the transaction. And then that gets sent to a rollup, which verifies this absolute nightmare in something we call a tube circuit. What's Goblin? Oh dear. How much time have I got? What? A few minutes. Wonderful. So what the hell is Goblin Plonk? So I think at one point it was basically a fever dream that turned into a sort of a protocol that is, I think we're getting a paper out end of the year. I call that a computation accelerator. The idea is when you're folding, when you're doing this thing, every time you want to do a fold, basically you have commitments to your circuits. You have commitments to your incoming functions proof. You have commitments to your incoming previous kernel iteration proof. And those commitments are elliptic curve points, and in order to fold them, you need to do scalar multiplications on those elliptic curve points, which is annoying, painful. We don't want to do that because it's a very like infamous problem in ZK snarks where if you're working over a single elliptic curve and you want to do elliptic curve arithmetic in that elliptic curve over a snark defined over that elliptic curve, the prime field you need to work with is not the same as the prime field available in your circuit. So you need to do emulated prime field arithmetic Very expensive, very painful. We don't want to do it. So we use Goblin Plonk instead. OK, so how does it work? I should know, I designed it. So we have this concept of an operations queue. So let's say you're in your circuit, life is good, you're doing folding, and then, oh no, you need to do an elliptic curve scalar multiplication. How about instead you don't? What you do instead is you have basically a table that you can write information into. And in that table, you write in the elliptic curve instruction that you need to do, and your claim as to what the result is. And then you move on with your life. You just assume the claim is correct. Obviously, that is very efficient because you're not doing any work. And that table that you're writing stuff into basically becomes a commitment to what we call a transcript, a commitment to all the elliptic curve operations that you need to prove but have not yet proven. And the idea is in our IVC scheme, as we are folding, what's happening here is in some of the in this side effect output, we're getting an incrementing list of elliptic curve instructions to perform. So basically, it's a bit like maybe when back at university we have a lot of assignments to do, lots of responsibilities piling up, and you're just ignoring them, trying to drink the pain away until at some point you finally have to deal with it. And then how do we deal with it? So I think we borrowed, stole, were inspired by the Ethereum Foundation and their blob work with this, which is basically, so you have a commitment to elliptic curve operations over, let's say, curve A. And we know that elliptic curve B can very efficiently evaluate operations over curve A. So in ASIC's case, these two elliptic curves are called B and T54 and Grumpkin. And so we have a bunch of B and T54 operations we need to do. We'd rather do them on the Grumpkin curve because it's really efficient. So how do we do that? Well, the idea is you have this B and T54 commitment to all the stuff you have to do. What the prover does is they just magic out of thin air a commitment over the Grumpkin curve to the same information. And then you need to do two things. One, you need to prove that the commitments are commitments to the same information. And two, you need to actually prove that the elliptic curve operations are correct over the Grumpkin curve. That second part is what we have a circuit called the elliptic curve virtual machine, because it is the world's most unique, bespoke, artisanal virtual machine, because it only does elliptic curve operations and nothing else. That part is very efficient, because now you're working with the Grumpkin curve, so B and T54 operations are really, really cheap. So that's great, lovely. But how do you prove the commitments are the same? Well, that's fairly straightforward. We have this thing called a translation circuit. I say it's straightforward because I didn't write it, but that chap over there wrote it, so he might have a different opinion. So 2 minutes, okay, good. So in the translator circuit, we basically, so you've got these two polynomial commitments, one over B and T54, one over Grumpkin. Use a regular bog standard normie polynomial commitment scheme over the Grumpkin curve to open your polynomials at a random point, evaluate them. And then what you want to do is, for the B and T54 commitment, you want to pretend that they're Grumpkin commitments. You want to imagine what it's like to be a commitment over the Grumpkin curve and pretend that you are one. And then, using emulated field arithmetic, evaluate the information committed to in the B and T54 curve, evaluate it as if they were coefficients over a Grumpkin polynomial. And that's actually relatively easy to do. You just create a snark circuit that does some non-native field arithmetic to do that step. And what it effectively does is it translates non-native elliptic curve group operations, scalar moles, into a constant small number of non-native field operations, which is a concretely asymptotically better thing to do. Like asymptotically you can prove it's less work. I think it's like something related to the security parameter of the curve. Anyway, it's very efficient, really efficient. It means that we can recurse in about 12,000 gates, and that's not even very optimized. So we're talking milliseconds there. It's really good. And so this is the full completed thing. I did not make this diagram. It's far too good for me. This was my colleague, Mara, who did it. But the idea here is you have F and you have G. So G is basically elliptic curve operations over the Grumpkin curve. Is it? And F is your accumulated folding instance. And as you're folding, what you're doing is you are, my laser pointers. Yeah. As you're folding, you are adding more information into this list of elliptic curve operations. You're growing this list. And then you basically you kind of deal with this by creating these elliptic curve virtual machine and translator proofs. And so basically the output of an Aztec user transaction is the proof of correctness for all of this IVC stuff, which is where all the real logic of what you're doing is encoded. And then these two proofs, ECC VM and translator. Yeah, it's pretty efficient. At least it's efficient on the client side. Verifying this stuff on the server is less so, but we're working on that. It's not really a big problem because we have a lot of resources at play there. And so, yeah, that's basically a very brief overview of Mega Honk. Papers coming out soon. Thank you for listening. If you want to get in touch, join the Discord, look at the roadmap, look at our research, download Noir, tinker around, and yeah, thank you very much for listening.
Alrighty, we have some time for questions. Does anyone have any questions? Okay.
How's it going? Thanks for the talk.
Hello.
Just to check whether you're aware that the idea of shifting a polynomial on the cube is solved.
Yeah.
Yeah.
Yeah. That's why we use sum checks now. But back in the day, it wasn't a solved problem. Like you go back 3-4 years.
Okay. Yeah. Cool.
Yeah.
Any other questions? Okay, thank you again, Zach. And now we have the finale of the conference, which if you've attended other ZK summits, it's a tradition. Anna and Friends panel. Is this going to be like park bench style? No, that's just a standard panel. Okay, forget what I said. Also, Zach, I'm waiting for my friendship bracelet. You have to take. So who's on the panel? Anna, who's on the panel? Who wants to join? Panelists, if you know who you are. This is the honor system of.
Hello, hello. Hello. Is it working? Can you guys hear me on the mic? Okay, good. Cool. How are you all feeling now that you have reached almost the end of ZK Summit 12? Have you learned a lot? Yes? I need some reactions. Have you learned something? Yes? Okay, good. Yes. Did you have fun? Did you use the card, the NFC card? Who used it? Who used it? Hands up. Oh, yeah, okay. Very good. I'm glad that you guys gave it a shot. So what we're doing now is we're kind of wrapping up the main stage with a panel. Kind of like every time I do a summit, this panel comes together as the day progresses. What we wanted to talk about, oh, nice. Thanks, guys. What we wanted to talk about today, if you were there for my intro talk, I was talking about the map of ZK. And I had this area on the map of ZK, which I had just called miscellaneous tools. Basically, it's categories that have not yet been defined. And what we wanted to do with this panel was just kind of like explore, brainstorms, what some of those categories might look like. I think we're going to start really with the panelists, and we're going to have a conversation about what might be coming. But I do also want to open up the floor to you to think about what those categories might look like, or maybe you're working on a project which you think could define a future category, and so we want to hear from you in this talk too. All right, let's kick off with some intros. I introduced myself at the beginning of the day, but my name is Anna. I'm the host of a show called Zero Knowledge Podcast. I'm the co-creator of a project, an educational hub called ZK Hack. and I'm a co-founder of a company called ZKV. ZK Podcast is also the producer of this event, and we are now on our 12th edition. I kind of can't believe that. We've done a dozen. Anyway, that's me. What about you?
Sweet. I'm Ayush. I have mostly been thinking about ZK email for the last year and a half, but I've spent maybe a little bit over 2 years thinking about general ZK applications. So things like anonymous group signatures or data provenance and things like that. So yeah, I'm excited to jam more on weird new applications.
Nice.
I'm Andrew. I work on Cursive, and we build cryptographic apps for human connection. And I've mostly been exploring how we can turn cryptographic tools into social primitives.
They're all very succinct. I'm a bit shy. I'm never so succinct when I introduce myself. But I'm Ashling. I'm the head of privacy at Tatseo. We're building MPC tooling for ZK at the moment, but hopefully soon general purpose. My background is in cryptography. I care a lot about privacy. I love Web3. I love crypto. I want everyone to use it. So I now think about all the ways in which we can make it so that people actually do use it.
Nice. I want to start us in sort of discussing what I think of as some of the new categories. So you mentioned, ZK email, sort of the ZK TLS, maybe what Cursive is working on. I want to sort of define what has started to emerge, kind of those categories that I think we are seeing teams line up in. And then from there, I want to talk about maybe some new primitives, new concepts. I mean, even the co-snarks, like what that actually opens up. It's quite interesting. But let's go back, when would you say the ZK TLS category happened? Was this in the last year?
I mean, the Deco paper was like
Yes,
more than 5 years ago. So but fair enough, practically we first saw maybe TLS proxy style implementations like a year ago, and then finally the notary style implementation started getting a lot more traction, I think, this year.
Let's define for the audience and who may not be as familiar, what is that category? What kind of teams? What are they doing, ZK TLS?
Yeah, I think there's generally two main approaches these days. There's the TLS notary approach, which I think was originally an external project, and then PSC picked it up and revived it. It was super old. So that's notary-based approach. It uses MPC, and the other approach is TLX proxy. I actually don't know who originated that. Not sure. But I think now that's become a more popular approach. It's simpler to set up, and there's quite a few teams working on this. Off the top of my head, Pluto, Reclaim, Opacity, ton of teams exploring this space. So that's really good. Get a bunch of builders here.
When you talk about TLS notary or TLS proxy, what is it what can you actually do with these things? You're proving something about what?
About any HTTP TLS response. So you send a request to a server, and then either this request is initiated through an MPC session where your session keys are shared with a notary, or it's routed through a proxy which assigns the direction of the traffic. And that allows you to actually prove things about the API response or the TLS response. And you can also use ZK to basically hide certain things from this proxy, or use selective disclosure to prove certain things.
And as I've understood it, you're kind of tapping into the web. All of a sudden, you're making proofs about something that's out there on the web, websites. ZK email, it's funny because I've sort of put it under the ZK TLS category, but I'm curious how you place it, and also maybe let's explain what ZK email is.
Yeah, sure. I'm happy to dive in a little bit. So I guess, I don't know if I would agree with categorization under ZK TLS, but there definitely is a lot of overlap in the sense that you can kind of, and maybe I even disagree with ZK TLS as a name, but you can think of it as all the data in your email, you already have signatures on them, and you can now make proofs of them. And it's kind of separate from the TLS work because TLS, you have no signatures, it's all symmetric, and so you're kind of fundamentally trusting, okay, there's some party in the middle that's going to be centrally permissioned. It can't be a decentralized thing, or else that person could collude and then drain whatever it is you're trying to prove. And so the way I think about ZK email ideas is like, it's kind of just the first example of, oh, this is one really interesting piece of signed data that we can make really interesting ZK proofs about. But it's just like, just one of like a category of many, many of these like pieces of signed data. Like passports are also signed, and you see projects like Open Passport or Raramo doing really cool things with selective disclosure on signed passports. And then you have ID cards are starting to get more and more signed around the world. And then you have even like sometimes web front ends are signed with like signed exchange. And so there's lots of signatures if you kind of go hunting for signatures, and then you can make ZK proofs of these things. And then people like to use the word like vampire attack in Web3, but I think of it more as like adding features to it. Like we're like helping the Web2 services, like add little features to their little products. And all they have to do is add a signature.
Nice. I want to come back a little bit later on in this conversation about signed data and like what that could look like. But now I want to hear a bit about co-snarks. We did an episode pretty recently where we went very much into detail about it, but maybe you could just quickly explain what those are and some of the use cases that those open up.
Sure. I mean, they kind of add to a lot of the stuff that you're talking about, and it's so cool. I mean, I'm thinking also a lot about the ZK use cases at the moment, and it's so super nice to see that there are actual things that people are using now that I can say, oh, look here, I can actually point at things. But co-snarks generally are collaborative snarks where you generate a snark in an MPC circuit. So you have a distributed setting where you want to do some private computation and you want to generate a proof in a private way. So one example I think that was at the workshop earlier was, suppose we want to determine who has a higher salary or who is richer. We can engage in this MPC protocol. But suppose now, Anna, we reveal the result to you, but you're not quite sure if you trust us. Maybe you want us also to provide, or the circuit at least, to provide a proof that, yes, indeed, the computation was done correctly. But because we're in this MPC setting, you need to do this proof in an MPC way. So this is essentially a co-snark. And maybe like with ZK email and ZK TLS and all of this stuff with the ZK passport, this works quite well now if you want to just generate a snark in a small circuit, this kind of stuff. It works pretty efficiently. But if you start now talking about these types of cards and you have smaller devices with lower memory and you don't have lots of RAM and you don't have lots of power and you don't have like memory space, computation power, it becomes much more difficult to actually compute something, especially in a ZK, to compute ZK proofs in an MPC way. So maybe you want to do some outsourcing, and there are all these proof markets now showing up. Maybe you want someone else to generate your proofs, but you don't want to send your witness in the clear because you're talking now about private data. It's your passport, it's your emails, it's whatever. So yeah, this is where co-snarks fit into the sort of things that are emerging now as the kind of more human things where it's like, okay, we want to share some data, but I'm okay sharing it with you guys, but maybe not like publicly for everybody.
Cool. I also want to come back to that and what kind of use cases could come off that. But let's talk about cursive. In the map of ZK that I presented, you're currently in miscellaneous tools because I don't know exactly how to define what you guys do. So can you share some of the experiments and sort of areas that you're experimenting with?
Yeah, definitely. So we're still figuring it out.
Yeah.
So that explains a lot. I think the one way we look at this is thinking about problems with existing social apps and problems users have and how we can solve those problems with cryptography. So these were the 3 points that Vivek mentioned earlier during his presentation. The first one is unbreakable consent. And this relates to the issue that a lot of existing social apps are push-based. So advertisers or platforms or big algorithms will impose what they want you to see, and that's just kind of what you get. You don't really have much choice there. And cryptography allows you to do the opposite. In a lot of these MPC setups, you have to consent, you have to opt in order to actually have computation run on your data. The second idea here is digital pheromones, and this relates to the issue that a lot of existing social apps are closed platforms. So your data stays within a platform, and you can only use it within that space. And digital pheromones is this concept that your data can be open. It can be anywhere. It can just exist, and as I'm walking by Ayush, like, our digital pheromones can somehow interact, and it can do so in like a safe and privacy-preserving way.
It's a great metaphor. It's kind of creepy when you explain it, but it's also you understand it. It's sort of like, usually if you try to do this sort of like two people walking by each other, it's because you both have some app that's owned by a third party that's doing tracking on both of you and then matches you. Here you're sort of imagining it being from something that you have yourself that's not owned by a third party, I'm guessing. Like something where it's like something on your device that it might be provided by a third party, like the ability to create this thing, but then it's just living on your device and it's like being triggered if you walk by someone else.
Yeah, I think
I like that.
That like initial response is exactly why cryptography is so important. That's why, like, if this idea were to work or make sense, I think having safety and privacy would be a critical component of it, because otherwise it would feel like super weird if someone was just like spying on you the whole time and you walk around and they like match you with this specific person that's like really targeted. That would feel like kind of creepy in some ways.
That actually exists right now with like ad tech, where it's like you walk by a certain store and then, I remember this is from years ago, there's like ad tech platforms where they would like, they knew your Spotify data and somehow like mapped where you were, and then it was like, you'd walk by a store and you'd just get the advertisement for that store while you walked by it in your Spotify feed. And I don't know if this is a company that was like pitching me, so I don't know if that actually worked, or that if they ever got it into the hands of people, but they're trying to, and it's very ad tech, it's very Web 2, it's very not privacy friendly. It's scary.
It's related to that idea of like you whisper something into your phone, or you're like just having casual conversations, like, oh, like thinking about buying a cat, and then the next day you get a bunch of cat ads, and it's like, oh, how did this get here? I don't know.
Yeah. So that was digital pheromones. Yeah.
And the final one is this idea of narrowcasting. So narrowcasting, opposite of broadcasting. This addresses the issue that a lot of social apps are public billboards, where you just post a bunch of information. It's generally accessible. Think Twitter. Instagram is somewhat public, half public. Tinder, everyone sees your profile. And this idea of narrowcasting is being able to specifically target who can see your data and who can interact with you. So you want to be able to say, hey, like, I want to find out who's going to this concert, but I only want to ask people who are maybe like 2 degrees away from me, or people who share the same music interests as I do and would be interested in going to this concert as well. So you get more targeted queries, and the idea is that leads to safer and more intimate connection.
Is there a connection between the co-snark idea and narrowcasting? Is that like a use case? Because you sort of, you mentioned something around like, having, at least it sounded like it was a smaller group getting access.
Yeah, well, it's something that we're thinking about a lot because it's a problem that we kind of can't really solve right now with MPC. We can't really do this, well, I shouldn't say can't. It's like we don't immediately see how this can be done in an efficient way with MPC right now, or like in a very privacy-friendly way. Because this is a bit this transitive trust problem. So you're saying that, okay, I trust you and you trust him, and like there are a few people that are a few degrees away from me, and then you have this social graph, and if you want to sort of traverse this graph in a privacy-friendly way, you need to touch every node, and then it becomes like super expensive to try and actually do anything. If you want to say, okay, I want to know what concert or like what music taste we have in common or whatever, you need to just check the whole graph. And so if your graph is big, then it's hard. So it's definitely something that we're thinking about a lot. It's my favorite topic at the moment, so I really like that you brought it up. But yeah, I think like for me, this is one of those things that should be on this board next year. Like it's definitely one of those topics, I think.
Will it be called narrowcasting or what?
If someone has a better name, please let us know.
Is that the word? Is that the term that you were using when you were thinking about this?
So I was thinking about it in the context of more in the trust context. So like, how can I tell you that I trust him so you can have some relationship with him as well? And like, if you trust me, how can you inherit some trust from him knowing that I trust him? This kind of stuff. So it's a little bit different, and this is the transitive trust problem. So it's a little bit different it's a bit different to narrowcasting, but narrowcasting is...
Yeah, I didn't want to, the name is not bad. I didn't want to challenge the name.
But the pheromones also makes me think of like some sort of digital smell. It's kind of, it's quite descriptive. Like
But it's also, I don't know what else, it's actually quite good.
Yeah, it's great.
Like, if you think about it, what it means. But yeah, at first it's sort of like digital smell.
Everyone in the 90s wanted like smell-o-vision. They were thinking about how do we digitize smell and how can we like, there you go. I mean, I think this is a nice way to do it. Congrats on your smell-o-vision.
Nice. I want to go back to what you were talking about, Ayush, with the signed data. So you talked about like ZK email being, like it's something you can get signed data from, and that's sort of why you started there. What other kinds of signed data are there? You mentioned passports, but maybe share some others that you're thinking about.
Yeah, there's so many. I know Andrew also has a list of these up. I mean, we've seen, I know like credit card transactions sometimes have signatures on them. I've seen, what else have we seen? We've seen, so the NFC chip in your passport has it, but also when you download like a digital version of your, for instance, your state ID, if you're in the States, and that'll often also have a digital signature on it. When you sign documents, like on DocuSign, they'll often send you back like a signed copy, which is actually also often like digitally signed with a cryptographic signature. I know in India, the Aadhaar team, or one of the teams like adjacent to the Aadhaar team, basically all of your documents, like your elementary school certificate and your high school diploma and all these things, are all digitally signed and put into, like the Indian government has asked all these organizations to sign it, and that's the only way you can get added to your kind of central registry of all your documents. And so now you have like 1 billion people with like crazy amounts of signed documents and data, which is very interesting.
Do you, when you're thinking about the signed data though, are you also thinking about ways that like data could be signed in the future? Like what you've described is sort of like where you can now get signed data. But like, yeah.
Absolutely. I mean, I think the ideal case is that, for instance, like I spent some time at like the IETF conference, like the standardization conference for all these internet standards, and I was like, hey, we should go sign stuff. And people didn't really seem to buy most of the use case, but when you say, oh, you can get provenance, you can stop fake news, then they like really light up. And so I think if you can pitch like even traditional web folks on, hey, look, like you can get more provenance on data, you can stop fake news, and therefore you should add signatures to TLS, you should add signatures to everything.
Photos.
Exactly, whatever
Audio.
it is, exactly.
Yeah.
Then it'll allow you to verify it in the future, and there's a lot of like really weird ways that people are doing this kind of like authenticity. Like I saw a paper the other day where, so like one of the problems with signing like photos or audio is that you can often like put something, like there's some connection between the thing getting the input and the thing doing the signing. But there was this paper where it was like, oh, you can use a like variation inherent in like an FPGA to detect the correlation between something like temperature, which should affect in a correlated way, and you measure this FPGA so that you can say, oh yeah, it is correlated in the correct way, therefore yes, I'm actually live measuring the temperature. And you can get this really weird like interactive ZK proof out of like a hardware defect, which is like crazy to me. So I think we're going to see a lot of like crazy, weird new like attested sensors where something on this side is doing a hash, something here is doing like FPGA noise detection, and like you get these really weird new attested sensors. But I'm very curious to see where that field goes.
That's cool. One of the points you mentioned was unbreakable consent, but we didn't actually go into what that is. So let's dive into that one.
Yeah, I think it's just the idea that this consent of using your data is actually enforced at the technology level. So when you, let's say, run multi-party FHE on your data or run some MPC, like you actually have to participate in this computation to be able to have the computation execute correctly. So I think there's roughly 2 different scenarios here when we talk about like FHE, MPC, security. This terminology, I believe, comes from Enrico from PSC, but it's delegated versus direct security. So delegated security means I want to outsource some computation, so I send it to a bunch of different parties, and they run this computation for me, and then I get the result back. Direct security is what we mean when we talk about unbreakable consent. It means you are actively securing the computation because you are participating in it. And so if you don't consent to this computation, if you don't like what's going on, you just don't participate and nothing will actually happen.
Like, is this currently, though, very conceptual? Or is this like, have you seen something like this in practice?
I think this is how we implement MPC stuff in practice right now.
Okay.
Our MPC schemes, like these PSI implementations, are based on this idea where you actually have to like say yes to this to decrypt.
I think this is, yeah, like, suppose, I mean, even with these cards, suppose we're in a 4-party MPC protocol, and we're all the nodes, and we're all computing on our encrypted data between us. Suppose you, at some point, become uncomfortable with the computation, and you don't want the result to be revealed, or somehow, I don't know, whatever. You can pull the plug, and before like the result is computed, then the network breaks, and essentially you don't get the result. So unless everybody stays in till the end. And I mean, yeah, this is a bit different to the delegated case. So.
That's cool. So I feel like we've started to tease out like a few of the future ideas. I do want to sort of get the audience slightly primed. I don't know if you're ready to jump in, but I'd love to like start thinking about these use cases or the things that we're talking about. I'm kind of hoping to hear from members of the audience if you've been thinking about these things, or if maybe you've been thinking about something else that comes off this. Tanya, do you have the mic just to be ready? And so just put up your hand even if we're in the middle of talking, if you have something you wanted to add or if you're thinking about anything around this. Do you have any, like, especially maybe you in the miscellaneous category, do you have any, like other than these three, do you see any applications emerging? Maybe people, like things coming out of PSE, like kind of other application categories?
Yeah, I mean, I think for me, the big topic is around trust. And like it covers, I mean, for me, this is a whole new industry that is kind of bobbling a bit now. And like it comes up in pretty much every single conversation that we have, like that I've had today. And like, even just a few examples. One is, let's say you want to set up an MPC network. How do you trust the nodes that are in the network? How do you trust the data that goes into, how do I trust the result of this computation from the two of us? How do I know? And so like one conversation, like also with the signatures, okay, I can sign some data, but how do I know that the data put in there was fine? So there's all this kind of stuff about trust. And like a nice conversation with Jens earlier was a bit like, how do we know we've won, actually? Is it when your granny is onboarded to Web3, or is it when the government trusts that your ZK passport is valid?
Yeah.
And like, how then does your granny trust the government, or does she trust the cryptographers? And like, you know, how does all of this play out? And I think like it's really hard. Like we're all kind of trying to figure this out now. Who do we? It's not.
Who do we trust?
Like it's not trustless.
Yeah.
And so somehow this needs to emerge, and somehow, and then even with the code, like what about, you know, how do we trust the code?
For sure.
Do we need now more like, there's just so much about trust, like from the technical aspects, like both like, okay, proving and formally verifying code, to forming these like mini governments or institutions that sort of say like, this is a good protocol, this is a bullshit protocol, whatever. So yeah, there's like, on the technical side, there's a lot about trust. On the human side, there's a lot about trust. On the like fun side, there's a lot about trust. So for me, that is the kind of key topic that covers and touches everything, both in Web 2 and Web 3. It's like, for me, that's the topic that ZK, like, starts the little spark, and then it's just going to explode, I think. Wow.
Yeah, I think one concept related to trust, I think this is from our node, but I might be wrong.
Yeah.
Talking about trust infrastructure, I think the quote is something like, crypto allowed us to build stadiums, programmable cryptography allows us to build bars, or something like that. But it's this idea of like, not just having trusted spaces that are like building global trust or global consensus, but programmable cryptography really enabling more local areas of trust. So there's this team called Tonk that's building this concept called speakeasies. And I think the idea is like you have to provide some ZK proof that you meet a certain criteria to join this private gated space. And within that space, you can talk freely to other members of your community.
Yeah.
But the purpose is it's more of like a small, cozy space rather than a large-scale venue.
I just want to highlight what you were saying there too, because the word trust. I mean, we use I trust this, I don't trust this, but I think the concept of thinking about trust now is in contrast to the promotion of that trustless mentality, which I think actually dominated the conversation in our space for many years, like as long as I've been in it. I think I was introduced to this, like trustless sounds like untrustworthy when you first hear it. And then you have to learn that trustless means you don't need to trust anymore because everything is built by engineers and it works perfectly, and you can just trust the cryptography and the engineering and don't worry. But then, in that conversation with Arnaud, he kind of brought back, and I think it's been talked about a lot in certain circles, is that idea of like, still, there's going to be someone who makes that code, and there's going to be someone who maintains it, and like, there are other places, there's like, you may still need institutions or something human that creates trust for those trustless systems to be trustworthy. Anyway, yeah. I know we have someone from the audience.
Yeah? Okay, amazing. What I said, don't trust, verify. It was always...
Yeah.
But I think on that, I think, not from a non-tech perspective, I always find this system fascinating because it helps us to remove human error and create better ways to relate to each other. But going back to, what was it? MPC pheromone? What was it? Right.
Digital pheromones.
Exactly, digital pheromone, catchy name. I was recently looking at an app, right? And they are kind of Web 2 / trying to move more in Web 3. And they had those kind of ads, exactly, that you have to look at. And I checked a little bit what was the issue or the perspective that certain DevRels had about this app. And one of the things that popped up was I shared a lot of data with them, and I don't think I got what I was expecting back. And so I think it's a really important use case because a lot of times we have, problems in our space with user engagement. But imagine a Web 2 app, trying to cross over into Web 3 and being able to utilize MPC or, ZK to allow at least that layer of privacy or consent. It could definitely be a great use case, and we would love really to see more of that.
Nice, thank you.
Yeah, I think something interesting there is this question of most existing social apps are based on ads and require ads to run. And inherently, this idea, or the way ads have been implemented, is based on this like marketplace model. It is based on this auction. And so this question of like, can we create pull-based ad systems? Does that even make sense as a business model? Is there any setup there that these like new projects that are based on consent, based on user ownership, like what are the business models there for ads? Or do ads just not work at all in that model?
Just going back to, is there another question? Yeah, let's go.
I was going to go into a different line of questions, so if you want to. Okay, yeah, so I've been thinking about web proofs a lot in zk-TLS, and it seems like the main focus of those projects is building like an identity product first, and to me that seems like it's one of the features of a wider product that eventually will come in sort of like an internet of trust or an internet of truth, whatever you want to call it. I think I understand the end vision, I think I understand the identity products. I'm struggling with the middle and what comes next. Any hypotheses?
Can you say that it says the ID products and the?
Yeah, like it seems like a lot of like the zk-TLS or like those types of projects are focused on identity-looking products right now. And eventually I understand that, like, yes, of course you need an identity product in order to engage with like an internet of true statements or something like that. But I'm struggling with like the next thing to get to like that eventual internet.
Well, I think, I mean, I think like a lot of the ZKVM stuff that's going on at the moment is maybe a first step towards that, because at least there you're doing computation that's verifiable. It's maybe not fully private. It's like this sort of going towards scalable, verifiable computation. Not necessarily private, so maybe not so good for like all the use cases. But like, I guess that's the first kind of step towards it. It's one of them at least, I think. But yeah, like that's the hard question. Like okay, we're here, we dream of being here. How do we get there? It's like, that's why we're here. That's the job.
And maybe one note on the like broadening of possibility from like things that we've already intuited is combining ZK with other cryptographic technologies, like starting with ZK and MPC, or ZK and FHE, we've also seen like, oh, you can now FHE things verifiably. And then I think also some of the stuff that Kurt's explaining is like, oh, now what if you combine that with witness encryption? Like, oh, you get some really interesting stuff. And even though we don't have full witness encryption, we have partial witness encryption actually that gives you like enough that you can now do really interesting things. And I think it's kind of like, okay, we've now had like almost like 8 years since like Broad 16, since like practical ZK proofs to be like, okay, like what can we do with these things? But we've had only like less than 6 months since practical like witness encryption could be combined with like ideas from ZK, et cetera, for us to think about what can we even do with this technology. And so I think as we see more of the cryptographic infrastructure getting built out, then it'll allow us to be like, okay, we can verify this kind of like weird cryptographic computation. What does that let us do? And it's kind of a different mental model necessarily than the kind of narratives we've seen play out repeatedly in ZK or Web3 or whatever these existing spaces have been.
I think just to follow up, I think this is like exactly the nice way to think, because if you think about TLS itself, like security on the internet for communication, there were all the building blocks, like people were building like, okay, public key encryption and signature schemes and deploying them and making them efficient and like all sorts of stuff like handshakes and like, you know, reducing latency and all sorts of things and reducing communication. And like, you know, it was always this kind of like, here, this bit, tweaking this bit, you know, and like, the cryptographers would complain that maybe this is piecemeal engineering, whatever, but at some point, enough tweaks here and there lead to the whole thing just kind of working, kind of not overnight, but like just working. And the same with Bitcoin, like all the pieces, there was eCash and there were like Merkle trees and there was like all sorts of stuff. And eventually someday they're just kind of put these pieces that, these weird pieces that you plug in together somehow just form the right configuration and it works. Bitcoin's there, TLS is there, and then, yeah, maybe this is the way forward.
I want to, like, what you mentioned there, this, like, ID to web proofs, it just made me start thinking about the ID products that we have and programmable privacy, and something that Web 2 stuff gives you. I'm gonna do it. Here's my slight case for what Web 2 is good at, is that you sign up for something, you live on that thing for a little while, and then at some point, you kind of get bored of it, and you move on. And as an identity, so usually we are in our space claiming the problem with leaving your identities fragmented, but I think there's like a freedom in leaving a platform behind. Like, I think of my like MySpace account, and I'm like, I'm okay with that not being attached to my current person. Do you know what I mean? Like, in a weird sense, the siloed effects of Web 2 allow you to leave identities behind, which can be good, I think, to grow and change. In what we're building, like, do we have the ability to leave your identity behind? Like, I mean, I guess so, but this is something where it's like, if you own it and it's attached to you, we can carry it with us everywhere. Like, can we still opt out?
Well, I
Sorry,
think,
random.
yeah, I think that's a good point, but I would say, like, in this data ownership model, we can do something even cooler, which is that we can have multiple simultaneous data profiles at once. So you can own all your data, and at any given point in time, you can choose who you want to be. So you can set certain profiles of like, oh, I'm at ZK Summit, I want to be this person. Like, let me show this data, let me surface this data when I interact with people. let's say like I have this like digital pheromone setup. My digital pheromones are tied to my ZK conference profile, right? But then I go home, I go back to my friends, and I want to go like hang out with people. Maybe I put on a different profile. And because I'm in control of my data, I get to choose who I want to be in any given moment. And to me, that's like a really exciting primitive.
That's cool.
I think the key word there is choose. Like you have the choice. With the Web 2 platforms, like you don't have the choice. You don't have the choice to leave and take your data with you. Okay, maybe you can create a second account, but like you don't really have so much choice. And in Web 3, like you have the choice to, first of all, change, but you can also choose to kill them. I mean, you can burn them, burn an address or like burn whatever. I mean, it's hard to kill something completely, but yeah, choice is the key word.
Cool.
And maybe one small rephrasing of the identity is like, I feel like historically identities have been, oh, I'm going to collect all of these little badges that show who I am, but I'm not sure that necessarily encapsulates like how we want to think about identity moving forward. It can be like a weirder thing, like, oh, like I'm going to add aspects to profiles, or I'm going to pull this piece of data from here for this one action I'm going to do, so that one action can be more relevant. It's not like a badge I keep on my profile forever, but it's like, oh, this one thing I attach to this one piece of anonymous speech so that can become more relevant or in context or whatever. And I don't necessarily think identity has to be this like long-term thing. It can be something short-term that you apply. It can be like, oh, I just did this thing yesterday, and therefore I'm going to tell you this thing about today, and then I'm never going to think about it again.
I think it's when ID becomes attached to immutable ledgers, though, is where you start to think, can you choose? Like, isn't it somewhere? And I guess if it's private, it kind of is not visible, but it is also there forever. Then again, I mean, no, my MySpace account might actually be gone. I mean, is MySpace still around?
Well, maybe one pitch is that if you have an immutable ledger, this is just one of like many cryptographic tools you can use to build your applications. And maybe the ledger doesn't need to be the place where all these attestations live publicly for anybody to see. Maybe you just put commitments there, and then if you want to delete it, you just delete the pre-image of the commitment, and now nobody can reconstruct it. Or you use the ledgers as a place for everybody to share the verifying keys or to come to consensus on the public keys or whatever it is. And like that's what these chains end up being used for, and not for actually the way people currently conceive of, oh, let's like throw identity into this little like token and have everybody keep it. Like that may not be the way that we actually use them.
That's cool. Any other thoughts from the audience? Curious if you guys are thinking about anything like this. Are you working on anything that you think is sort of in a new category? Or if you want to talk about anything we've talked about?
Do you think that giving people choice, like at some point people don't want to choose, right? They just want to go through a flow that like simplifies their user experience. Do you think this will be like, how do you go about that? How do you think about something like that?
That's interesting. Just to rephrase, are you sort of almost like, is there sort of like too much power given, too much control given? Like sometimes you just want an experience to guide you and you just want to do.
Most people will not like
I think that's correct. And I think the like ideal situation here is you have multiple choices, but each of those choices is quite opinionated. And so you can choose your path, but your path is still like determined on a certain personality or a certain opinion or a certain perspective, worldview, whatever you want to call it. But you can still switch if you don't like that.
Although that still has a lot of agency. I think maybe what you're talking about is like situations where you want less agency. I feel like we're in a room full of people who want agency, but maybe you're right. Maybe there's.
I think these are a special group of people, but there are reasons why there's like Bitcoin ETFs or like why certain banks, store your Bitcoins, because people don't want to manage their keys or they don't want to manage their investments, and that's fine. Like I totally agree that sometimes these services are needed for helping people so that they don't have the choice. I mean, but it's nice to have the option. Like if you want to hold your keys, you should be able to. And I think this is the thing that the people in this room are sort of working towards.
Another way that I might look at this is that this layer where you have choice doesn't have to be the application layer. It can be the infrastructure layer below it. And now instead of currently the world of applications, you have to build in a world in which you have no choice. Oh, you can build one in which you have choice, or you can say, my users don't really seem to be like that, I don't want to do that. And you can now build on top of the infrastructure and have one in which there's no choice for the users, and that's totally fine. But at the base layer, like, there should be an option to have that, and I think the world can look very different if users have that option at least simmering in the background, even if it's not directly exposed to them in the way that they interact with the applications.
But then going to that application idea, like if you think about how applications tend to get built and how also they tend to get funded, one of the questions will always be like, what is the moat? So like they're building to hold you there. That's what they're trying to do. It's part of their business model. It's part of like what makes them competitive. So I wonder if like, yeah, it's almost like as a crowd, like there'll still be a gravitation towards applications that make a lot of it easy, and then there's power in that, and there's some sort of moat, and you can always go around it. But the same way you could always run your own, what is it? You can run your own website off your own server sitting in your house or something. I think you can do that. I've never done that, but you know what I mean? Like, I think you can do those things, but they become so unpopular, and like everyone else is over here now, and there's more power in being in that closed garden. I just wonder how we really break out of that. Like, it is crazy that Twitter and like those platforms still, like they still capture us, like all of us. I gave you hashtags to tweet. Like, we're not away from it yet. We don't like it. I mean, we're not like into it, but we can't seem to jump to anything else.
But I think this is, like, again, the stadium versus the bars. Like now, if it's easier to build something like, you know, if it's easier to build a bar than it is to build a stadium, then people are going to build bars. And, you know, if you can tear it down quickly, people will do it. And I think because of the sort of open source nature and whatever replicability or composability of programmable crypto generally, this makes this sort of, the bar building easier. And so, and I think like it should be, I mean, a lesson for all of us to build the tools that allow people to build the bars and not, like, I mean, always in cryptography, when people talk, I mean, like again, another conversation earlier was like how, like even if you have a PhD in cryptography, you can't verify that all of this code is correct. Like, I mean, so at some point, you need to make sure it's open and composable and that people can build.
Yeah. I would also say that if these things are easy to build, they can also become, like the default path can then be technological to resolve these and not legislative. Like we noticed, you know, oh, now there's all these cookie banner rules. And the solution to these cookie banner rules can either be add a bunch of banners to your page, or it can be use MPC for analytics so that you don't actually see the analytics or the individual user data. And now, even though you have cookie banner legislation, it's solved the problem by pushing us towards a more cryptographic, technological friendly solution. And we could do the really hard path of, okay, let's like really get super screwed by all of these things and then build legislation to stop it and then come back to the technological solutions that allow us to keep the flows we want. Or we could skip all of that legislation little loop and then just say, okay, what is the actual technological end game? Can we build this now? Can we at least build the tools that allow us to build that later?
I want to go back to what you were saying about the bars, because actually, as you were saying this, something I realized is like, I think there needs to be something, like the social aspect, the fact that, what is a bar? It's like, it's a group of friends that meet often, but there's a size to it. It's not like, yes, you could have like the 3-person bar, the dive bar, or the, I don't know, Dungeons & Dragons game or something. Like it could be the smallest group, but I think you think of those, it's community, it's about like, where are people? And that's kind of going back to that idea of like, if everyone goes to the big app, even if it's a D app, even if it's on a decentralized thing, it's all owned by something somehow, or could be captured. Like, I think what you have to build are these alternatives, but they cannot just be like solo webcaster, solo blogger. Like if you look in history, you know, yes, you had power, you had agency, but if you were sort of stuck on your own in a desert, like eventually most people just sort of drift off. But if you could keep some sort of community, like if you could keep people still stuck together around something or in something or at a bar, then it might work. Anyway,
I think that relates to one of the most important questions here, which is how to fund these types of projects, right? That's the elephant in the room. It's like, how do you provide a sustainable funding model for apps that provide a ton of value to maybe a smaller group of users, traditionally funding is designed for apps that just target everyone. And we've seen how that turns out. And I think like a lot of teams have still yet to figure out if you want to build the bars, if you don't want to build the stadiums. But for the people who go to the bars, like that is really important to them, and that matters a lot to them. How can you still build a sustainable entity around that?
I think there was a question over here, or a comment.
Is this one on? Hi. This is a general question. Like, how do you see ZK interfacing with AI now? I'm investing in AI infrastructure, and I've done a lot of investing in ZK in the past. I'm interested in your thoughts. It gets thrown around a lot around things like proving computation on graphs, proving provenance of data, and ZK is like thrown around a lot in that space, but you guys are the experts. I want to hear, where do you see the real applications today?
ZK AI.
Yeah.
Yeah, I think the kind of canonical examples you see are usually around like proving that a model executed correctly, or proving that you trained on some private data correctly, or proving that you ran inference on somebody's private input correctly. But I think there's like also another side to these, which is not actually about the like training or inference of the model, but is about the like verification of the outputs, which is like, oh, like how do I verify whether this thing, this image that I'm seeing online came from an AI generated model or not? And then, oh, now like the thing that cryptography does best, which is like provenance and adding unforgeability. Like one of the things that AI cannot generate, like you cannot generate a fake digital signature. You can generate almost anything else. You can generate pretty convincing looking text, but you can't get 256 bits of entropy out of a 405 billion parameter model or whatever. And so this becomes then one of the defenses that we have against, oh, like, can we verify whether this text came from an AI or a human? Can we verify whether this image came from an AI or a human? And you can bake a lot of this cryptographic techniques into the models and then help ensure, or into the model outputs and help ensure that, okay, like, a camera is going to sign this thing came from the camera, and therefore I know that it could not possibly have been generated by the AI. And so you can, I think a lot of the thinking around AI also can be around like, not just, oh, how do we like get privacy around the training or the inference, but oh, how can we like get clarity around the provenance?
Yeah, there's been, I mean, I think it was in early 2023, there was like a group, like a ZKML group that was founded, and a lot of ideas were thrown around. And I think there was a moment of a lot of excitement around it, and then it sort of chilled out. But I've been left with this, but I don't know if I can define it that well, but it is that like things like ZK and MPC, they almost add this like human protection thing, like against some of the AI stuff, maybe for a while. I don't know if it's forever, because AI is pretty smart. Maybe they'll figure out a way around it. But like in the short term, it seemed like just coming out of those conversations that ZK could be a guardrail. Maybe cryptography, certain kinds of cryptography could be guardrails to what this thing could do, just to help the human brain decipher, like in the case of provenance, or to help look inside what's happening when it's a very opaque system.
At a fundamental level, like if you think about AI as an extremely enabling technology, it allows you to do all these, especially generative AI, being able to like just create things on a whim. Cryptography, in the spirit of adding hardness, directly is a remedy for that.
Hopefully. All right, I think we're getting the nod. We're getting the signal that I think that the event is meant to wrap up really soon. Thank you guys for this panel, talking about some future ZK applications. I have a bunch of notes, things that I want to explore. Thank you all for joining for ZK Summit 12, and for coming, for speaking, for being part of this. Thank you all. Thank you. Yeah, a dozen. Maybe just a quick note. I think we don't have it up on the screen, but there is this after party happening tonight. There's a ton of side events happening tomorrow. Please do sign up for them. I think the teams are, like, they're kind of calculating how many spots they have based on who's signed up. I know there's also sort of an assumption that people are just going to show up, but it's better if you do sign up, actually. Cool. Okay, thanks everybody. See you soon.